Aquarius, you come supplied with Aquarius. The actual Aquarius. With one of our regular. Is she a regular? She is a regular. She's been on 4 times, something like that. Easily, yeah. Yeah. The one and only Kim Arcan. Kim, welcome back to Star Talk.
Thank you. I feel like I need a jacket or something, like they do at Saturday Night Live, you know?
She puts the pressure on this, a 5-timer. We're going to have to get her a master's jacket. It's a yellow or gold tag. All right, all right, maybe we got to do something like about that. Yeah, thanks for that idea. So, Kim, you're a visualization scientist, emerging technology lead for the Chandra X-ray telescope, which is that run out of Harvard-Smithsonian Center for Astrophysics?
Yes, the Chandra Observatory is a NASA mission that is run for NASA by the Smithsonian. So I am up here at the Center for Astrophysics in Massachusetts. Well, though I'm not technically there right now, I am. That's my usual base.
Apart from the cool stuff you do, what has made your career unique, you have pioneered data sonification. Just remind us what that is. We spent a whole show on that in our archives. People can dig that up. But just for now, just remind us what you do there.
Yeah, so my whole job is just about thinking about our data differently and figuring out other ways that we can visualize it, translate it into sound, which is sonification, bring into tactile or otherwise like amplification type movements through 3D printing or vibrational response, and just trying to really dig down into how we represent our data, whether for scientific analysis or for communication and public engagement, both of which are very, to me, worthwhile things to do.
Yeah, so if you're shifting the sensory experience, it would be highly useful for people whose sensory physiology doesn't match that of what is average.
Exactly. We work very closely with the blind and low vision community, particularly on the data sonification materials as well. But all of this grows out of, like, these are valid tools of scientific expression and analysis, right? So sonification is actually a tool used in the sciences to work with data. It's used by scientists who are blind or low vision, but also by sighted scientists, because you can just think, right? If you're a sighted scientist and you're looking at an image all the time and it's very familiar to you, you can almost become numb to it, right? The data is the data, but you can, when introducing new senses or new experiences, new modalities, it can just like rewire your brain a little bit different, right? So something that you might have looked at a lot or felt familiar with, it can kind of like open a new window. And I love that possibility for additional exploration.
It's not an accident that you're working on a telescope that specializes in X-rays. None of those bands of light are visible to the human eye. But in principle, someone such as you could exist for every telescope that's out there. Because even for visual imagery that we all just take for granted, that we can see color photos, but people who are low vision or blind can't see them, and that could still benefit from sonification, correct?
Correct, yeah. So, I mean, Chandra really has been the impetus for this for me, because I started thinking very early on in the mission, this is all invisible data, right? Humans cannot naturally see X-rays, and the same goes for the infrared data that the Webb telescope looks at, and for radio data, and even the data that the Hubble Space Telescope is gathering, right? We are not taking space selfies of the universe, like we are translating that data into visual representation through extreme magnification, through the translation of these different kinds of light. And so that sort of possibility that this data does not only have to be visualized, but there are other ways to explore it. It just gives you a new kind of like sandbox to play in. And when you're particularly attuned to how other people understand data, process data, think about data, it just allows you to try some things that can be really cool.
Goes off forever.
It's like that cut curve effect. You cut a curve and you can use it if you're a parent with a stroller. You can use it if you have a wheelchair. You can use it if you're on crutches. You can use it if you're on a bicycle, whatever. Right? It benefits multiple people, and I think that's one of the really exciting things about thinking of your data differently and trying different multimodal approaches.
It also gives you an opportunity for different manipulation of the data when you're working with it. So what came to my mind the first time I read you sent us an article last year, and when I was reading it, I thought about And sound editors don't edit using sound. They actually look at the wave pattern of the sound on the screen, and that's where they make all their decisions to make their edits. So that's kind of in reverse of what you're doing, but at the same time, it's the same principle. It's like you can manipulate the data differently because you're quote unquote looking at it.
I thought in the old days they have these really real soundtracks, and they were listening for where the sound would drop, and then they splice it, cut it, and tape it back together to make the final product.
Right.
Yeah.
So it's very cool.
Yeah, and we've actually had an artist take sonification and reconstruct an image from it. That piece, I think, is in a museum outside London right now, and I just thought that was so creative, right? To take the sound that was produced with that data, but then to
Almost out of the desert
step
biome.
it until they had an image, and their resulting image was meant as an artistic interpretation, but it was not super far from the original. Like, it had strong elements of that original data, and I love those kind of ideas of just play and creativity, which seem like they would be bad words on the workspace, right? They're really not. It's just about opening up your brain a bit and just trying to think about things a little differently.
So I have one issue with you, if I may.
Uh-oh.
Here we go.
There we go.
Not your fault. So in the movie
6,
Yeah,
7.
I love that movie.
Oh,
by Carl Sagan, the protagonist, Ellie Arway was her name, the character's name. She was an expert in the search for extraterrestrial intelligence, which is normally done with radio telescopes, and she would sonify the radio signal into headphones, and she'd be listening on headphones to the
2,
radio signal.
3,
Here's my
4,
issue.
5, 6, 7.
People think
And
that
break.
radio waves is
I
electromagnetic
can't wait
action.
till I get my new
And so
joystick
people think that the aliens were
replacement,
sending sound, but they were
or
not.
thumbstick.
Radio waves
2,
to be converted to
3,
sound.
4,
We end up making a one-to-one
6,
response between
7,
the word radio and sound. And that didn't help disavow people of that association. So I blame you for that.
That is one of my favorite space movies, but that is one issue that has always stuck out for me as well. However, I will also say, it is very commonly thought that these images are like direct snapshots as well. So it's just about being very transparent in what you're doing, really describing what you're doing in a way that's clear and makes sense, and just kind of reiterating, we are not capturing space selfies, and we are not capturing like space recordings. These are translations. Like, you might translate English to Mandarin, right? You have to have a way to interpret.
So, this is a cosmic query, so I want to make sure we get to the questions. But catch us up again on what the Chandra X-ray telescope does, which is one of the great observatories, along with Hubble and a few others, each in their own band of light. Remind us what Chandra does that other telescopes can't do, and what it sees that other telescopes can't see.
Yeah, so Chandra's kind of like part of that super friends team, if you will, with Hubble, with Webb, with these other telescopes. And Chandra is our sharpest X-ray view, right, of that high energy universe. It has, still to this day, after 26 years of being in operation, it's looking at things like exploding stars. It's looking at things like clusters of galaxies and the hot gas that envelops them.
Yeah, this is actually easier at night.
Stars and the sort of X-ray temper tantrums that they can have. It's looking at all of these very energetic phenomena across the universe. It's exciting because Chandra has such exquisite resolution. It's half of an arc second, and an arc second is just like a tiny unit of angular size. It'd be like 3,600 arc seconds in a degree, essentially. You're just looking at one half of an arc second. It's kind of the equivalent of if you're looking at a dime from a few miles away, right? It's really amazing. So
Can't wait to
that
get rid of that
helps
drift.
Chandra be, if I could refer to my past as a biologist, as a microbiologist,
2,
it kind of
3,
allows Chandra to be like the X-ray microscope of the universe. It really can dig down very deep, very sharp, right?
Yeah, love that analogy.
It's like Chandra's resolution is comparable to Hubble's, but it's looking at high resolution. It's looking at those high resolution, the X-ray photons in the universe, of which there are not as many as there are. The stars, for example, though they give off X-ray light, tends to be a slight, dearth of X-ray photons in the universe, which just makes it really challenging to do. And Chandra's engineering was such that, you can't use normal mirrors. You have to use these barrel-shaped nested mirrors, of which Chandra has 4 pairs, so that you can just kind of skim the X-rays down. It's phrasing instance. It's like skipping a rock across a pond, right? And that lets you then focus on now X-rays to be able to capture that.
That itself was an engineering discovery, perhaps, right?
Oh yes.
That you can focus X-rays that way. We have a lens. You put light through it. You can make an image on the other side. That's what magnifying lens is. X-rays don't do that in glass. You got to be more inventive about it.
I just like the fact that you said it was part of the Super Friends.
Oh, the
And
telescope.
and you made a DC reference, and the only DC character that has X-ray vision is Superman. So that makes you guys the Superman of the Super Friends.
2, 3, 4, 5, 6, 7, break.
Black holes that are in binary star systems.
Yes, Chandra is really a black hole hunter.
What?
Finding black holes.
Well, the exquisite resolution and the ability to peer through that dust that can clog
Yeah,
the
no,
heart
thank
of
you.
galaxies that Chandra gets to see. So Chandra is looking at things like Sagittarius A star, the supermassive black hole in our own galaxy. It's looked at that over and over and over again.
I thought things couldn't spawn on glass.
Vision with such longevity is that you get to look at something over time and like build that data for a really deep snapshot. And so with like Sagittarius A star, like we've seen it snacking on small snacks, like a little asteroid here and there, an after school snack. We've seen it like, devouring a larger Thanksgiving sized meal with a big fat star, right? We've been able to see that different things happening over time, which is, I think, really lovely. Yeah, black holes are one of my favorites. I mean,
But it's rendered visible because as it gets very hot, spiraling down, it radiates X-rays. That's the mechanism, correct?
exactly. And again, that's that high energy phenomenon, right? There's not as many high energy phenomena, things that are, burping out super high energy particles, things that are exploding, things that are colliding, as there are, say, normal stars. But there's still an awful lot to look at throughout the universe in X-ray light. So there's just always something new.
The cosmos is expanding, and so is Star Talk. We're beyond excited to share that our official merchant apparel store is launching early next year, and we can't wait for you to see what we've been working on. The cosmos science-inspired accessories, a perfect collection for everyone who loves exploring the universe with us. And while we're thrilled about what we're creating behind the scenes, we couldn't have done it without our friends at
1,
Shopify,
2,
who are helping
3,
us bring the entire
4,
project to life.
5, 6. Break, break, break.
Maybe you've wondered, what if I don't have the skills? Or what if I can't throw a
Still in the ocean.
What ifs become?
Be a long trip.
Shopify powers millions of businesses worldwide, including 10% of all U.S. e-commerce. From major brands to creators just starting out. Not a designer? Don't know how to code? Shopify's beautiful ready-made templates make building your site simple and seamless. Need extra help? Well, their AI tools enhance product photos, write descriptions, and even generate Turn those dreams into dollars and give them the best shot of success with Shopify. Sign up for your $1 per month trial and start selling today at Shopify.com.
That cooler gas and dust that's kind of created this bipolar structure called the homunculus nebula right around the star system. And so we do have a 3D model of that folks can take a look at on the Chandra website, chandra.si.edu/3D print.
Oh, interesting. Can we rotate it on the website as well?
Yes, you can. There's a little video that plays it going around, and so you can kind of see there are these 2 loads of material, and then the Chandra material, which is not in this 3D model, kind of hugs it. It kind of looks like a giant space croissant of high energy material wrapping around the homunculus, and then the 2 stars, or maybe 3, are very like inside.
Did she just say space croissant? I know. I'm so hungry right now.
I know. I'm kind of hungry too, which is why I can't do it. But it's like a hug. It's like a hug around the homunculus, which I think is very cool. But so these types of 3D models, like these are actually done for scientific analysis, and then we're able to 3D print them so that scientists can study them and understand them and display them. But also importantly, so people who are blind or low vision, or people who just really like to study tactilely or learn tactilely, have access to a different viewpoint.
Okay, so I think let's get on to some Q&A here.
Right.
So you got the list.
And guess what? They are ready to go. Our listeners.
I'm so impressed with the questions that people ask.
Listen, these people are not playing around.
Yeah.
It's right.
Uh-oh.
Yeah. All right, let's start off.
And they've been cued that Kim is our guest.
As a matter of fact,
You know this. Okay.
these are specifically questions for you, Kim. So,
Love that.
yeah, the audience knows who you are, and they're very excited to ask you the questions.
All right.
So this is Russell Harvey. Russell is from Colorado, and he says, how does sonification of X-ray data from Chandra help us understand cosmic phenomena like black holes or supernovae in different and new ways?
Ooh.
So what are you doing and finding that is proprietary to you that you can say, oh yeah, that was Chandra.
That's an important question because otherwise you're revealing just what is already known that a sighted person would see.
Right.
So do you have some insights there that?
Yeah, like some gossip, like, girl, I heard from Chandra. You know what I heard from Chandra?
Well, I can say, let me start out generally, right? So sonification helps us pick out patterns in data that can be hard to see. So they're often particularly helpful in things like studying gravitational waves or understanding variable stars and that sort of thing, where you have to pick out patterns in a lot of data that can be hard to see in only an image. So you can think of like rhythmic flickering. So for black holes, at least, there have been like additional thoughts about things like the Perseus cluster, because when that result in the Perseus cluster that showcased that there was this massive, supermassive black hole at the core burping out into the hot gas around it, causing these sound waves, these pressure waves, which are sound waves, and that note is about a B flat, about 57 octaves below middle C. Well, listening to the sonification, like bringing that note, if you will, back up into the realm of hearing by taking the image and scanning those waves in the image so that you can hear them through sound. What I have heard is that researchers have noticed that there were additional ripples that had been missed originally. So that is something that I haven't seen a paper on it or anything like that, but I have heard discussions that that is the sort of thing that could be really useful to do more of. This idea of being able to find small details that either wasn't as obvious in the visual or numerical data, or exactly. And that's the thing, like when you look at something a lot, or if you're just staring at something, you're getting all of the data at once. When you're listening to it, you're actually given the gift of time, right? So you have your brain responds in a different way because you're getting that data sort of parsed out to you based on the tempo of the sonification. And I think that's kind of an exciting space to do more experimenting.
And just to remind us, the sonification is basically a scan of the image where each row has some acoustic. As the scan comes across a star or an object that has X-ray flux, does the pitch go up or just the volume go up? What typically would happen there?
Yes. So it's a mathematical scan across the image or from the center out or all of that. And like pitch, tempo, volume, instrument choice, like all of those are the variables that we'll use in order to describe.
Instrument choice. I love it.
Look at that.
I want a saxophone in space.
Well, we do, yeah. So if you have like a heavy-duty data set that's got a lot of different kinds of light, using disparate instruments to assign to the data that you can really tell what's playing when, lets you to kind of help identify different parts of the image or the information that you're trying to decode.
Is there any use of an oboe or a didgeridoo?
Yes. I would say all instruments welcome, including voices. Yes, I think all instruments are welcome.
What a great answer. And thank you, Russell. All right, this is Hugo Dart. Pardon me, Hugo Dart. Hello, Dr. Tyson, Dr. Arcangelo. Nice. This is Hugo Dart from Rio de Janeiro, Brazil. Anyway,
You know they have one of the largest aerospace industries in the world in Brazil, and all you can do is shake
not know that.
You know why? Because in Carnival, they do not show aerospace.
That is a valid point.
Okay, got me on that one. Okay.
Hugo says, I'm with my 7-year-old daughter, Olivia, who's also a very big Star Talk fan. So, hello, Olivia. Here's our question to both of you. Why will space freak us out?
Oh, because you have a book. Kim has a book coming out.
Yes, that's such a sweet question.
Called Why Space Will Freak You Out. And it's a book that is intended to be like parent-child combo.
Exactly, like a family reader kind of thing.
How much you pay, Hugo?
You got miles of track.
I swear, but these questions are so
I found a giant desert and badlands area, and then this like circular mountain rim. And so I had to build out with glass first. Now I'm building back with the track. Yeah.
And it's kind of, it's meant to be a little fun.
The track?
Yeah.
It is fast, and like you don't like wear down your elytra wings, and yeah, it's just easy to go back and forth. Then you can also, like, you want to ferry a bunch of stuff, you can do minecart and chests, and then put a minecart with the stove in it, and that'll power all the carts in front of it to go all the way back.
It's like, what is weird and creepy in our own solar system?
Oh, you got a car one?
Yeah, like it's the cars and the road. Like you just build the road all the way through.
Oh, wow.
Yeah.
I don't have that mod.
I haven't tried the tracks though.
Yeah. Yeah, definitely easier, though, and creative. Infinite blocks. What mod do you have that has cars?
No, it's a furniture one.
Really? A furniture one? Okay.
You can trade gems for it.
Gotcha. Yeah, I wish we could get like the create aeronautics on Bedrock. That would be great.
Yeah.
I have to get my computer fixed and go over to Java for that. Oh.
Substitute for that baseline.
Yeah, exactly. Like the course of my son's life, essentially. Like we can see changes in that star, and Chandra is detecting like the really powerful stellar winds from that explosive or near explosive event, and then Hubble is capturing some of that cooler gas and dust that's kind of created this bipolar structure called I think it's the Homunculus Nebula. Right kind of around the star system. And so we do have a 3D model of that folks can take a look at on the Chandra website, chandra.si.edu/3dprint.
Interesting. And can we see it on the website as well?
Yes, you can. There's a little video that plays it going around, and so you can kind of see there are these two loads of material, and then the Chandra material, which is not in this 3D model, kind of hugs it. It kind of looks like a giant space croissant of high energy material wrapping around the homunculus, and then the two stars, or maybe three, are very like inside.
Did you just say space croissant? I know. I'm so hungry right now.
I know. I'm kind of hungry too, which is why I came to it. But it's like a hug. It's like a hug around the homunculus, which I think is very cool. But so these types of 3D models, like these are actually done for scientific analysis, and then we're able to 3D print them so that scientists can study them and understand them and display them. But also, importantly, so people who are blind or low vision, or people who just really like to study tactilely or learn tactilely, have access to a different way.
Okay, so some Q&A here.
Right.
Chuck, you got the list.
One, two,
And guess what? They are ready to go, our listeners.
I'm so impressed with the questions that people have asked.
These people are not playing around.
Yeah.
Right.
Uh-oh.
Yeah. All right, let's start off.
And they've been cued that Kim is our guest.
As a matter of fact,
You know this. Okay.
these are specifically questions for you, Kim. The audience knows who you are, and they're very excited to ask you questions. So this is Russell McCarthy. Russell is from Colorado, and he says, how does sonification of X-ray data from Chandra help us understand cosmic phenomena like black holes or supernovae in different and new ways? Ooh. So what are you doing finding that is proprietary to you that you can say, oh yeah, that was Chandra?
That's an important question because otherwise you're revealing just what is already known that a sighted person would see.
Right.
So do you have some insights there that?
Yeah, like some gossip, like, girl, I heard from Chandra. You know what I heard from Chandra?
Well, I can say, let me start off generally, right? So sonification helps us pick out patterns in data that can be hard to see. So they're often particularly helpful in things like studying gravitational waves or understanding variable stars and that sort of thing, where you have to pick out patterns in a lot of data that can be hard to see in only an image. So you can think of like rhythmic flickering. So for black holes, at least, there have been like additional thoughts about things like the Perseus cluster, because when that result in the Perseus cluster that showcased that there was this massive, supermassive black hole at the core burping out into the hot gas around it, causing these sound waves, these pressure waves, which are sound waves, and that note is about an E flat, about 57 octaves below middle C. Well, listening to the sonification, like bringing that note, if you will, back up into the realm of hearing by taking the image and scanning those waves in the image so that you can hear them for sound. What I have heard is that researchers have noticed that there were additional ripples that had been missed originally. So that is something that I haven't seen a paper on it or anything like that, but I have heard discussions that is the sort of thing that could be really useful to do more of. This idea of being able to find small details that either wasn't as obvious in the visual or numerical data, or exactly. And that's the thing, like when you look at something a lot, or if you're just staring at something, you're getting all of the data at once. When you're listening to it, you're actually given the gift of time, right? So you have, your brain responds in a different way because you're getting that data sort of parsed out to you based on the tempo of the sonification. And I think that's kind of an exciting space to do more experimenting.
And just to remind us, the sonification is basically a scan of the image where each row has some acoustic. As the scan comes across a star or an object that has X-ray flux, does the pitch go up or just the volume go up? What typically would happen there?
Yeah, so it's a mathematical scan across the image or from the center out or all of that, and like pitch, tempo, volume, instrument choice, like all of those are the variables that we'll use in order to describe.
Instrument choice. I love that. Look at that. I want a saxophone in space.
We do, yeah. So if you have like a heavy-duty data set that's got a lot of different kinds of light, choosing disparate instruments to assign to the data that you can really tell what's playing when, allows you to kind of help identify different parts of the image or the information that you're trying to decode.
Is there any use of an oboe? Or a didgeridoo?
Yes. I would say all instruments welcome, including the voices. Yes, I think all instruments are welcome.
What a great answer. And thank you, Russell. All right, this is Hugo Dart. Pardon me, Hugo. Hugo Dart. Hello, Dr. Tyson, Dr. Arcan, Lord Nice. This is Hugo Dart from Rio de Janeiro, Brazil. Anyway,
You said they have one of the largest aerospace industries in the world in Brazil, and all you can do is shake your ass. Would you say Brazil?
I did not know that.
Do you know why? Because in Carnival they do not show aerospace.
I found the point.
Okay. Hugo says, I'm with my 7-year-old daughter, Olivia, who is also a very big Star Talk fan. So hello, Olivia. Here's our question to both of you. Why will space freak us out?
Oh, because you have a book. Kim has a book coming out.
Yes, that's such a sweet question.
Why space will freak you out. And it's a book
first like sort of kid family reader type of thing with my amazing co-author Megan Watsky, and it's kind of it's meant to be a little fun. My husband loves horror movies. I think it's because he was born on Halloween, and so I'm not a fan of horror movies, but he watches a lot, and I think it's just kind of gone into my brain. So my humor's a little darker, I would say, and this idea of like finding fun in the creepy and the weird and the strange, the exotic in the universe is something that's just kind of been filtering in. So it's a fun look at things because it's like what is weird and creepy in our own solar system, in our own galaxy, and then like well beyond. So you can think of things like exoplanets, like the exoplanets that we have found. Some of them are so gosh darn weird, like worlds where it rains glass sideways at like 5,000 miles an hour, lava worlds, frozen worlds, dead worlds going around zombie stars. I mean, it sounds like science fiction, and so it was just kind of an opportunity to think of some of those fun things, those weird things, those freaky things, and just talk about them in a way that's hopefully not too scary. But I guess to answer the question, like really, it's just that space is huge and mind-boggling and extreme and weird, and we're very lucky to live here on our cute little rocky planet where things are relatively, well, not weird. Comparatively speaking. Comparatively speaking.
Here's a follow-up from Olivia. Okay, actually, it's from me. I've read this or heard this someplace, but please tell me, what is how far do we have to go towards the sun or away from the sun where we don't have this planet anymore?
I'll stop. Ooh, I see land.
900 degrees. Mars is to our right, once had water and does not. So we're sandwiched in between two wholly inhospitable planets.
Come on, get up here.
What are you asking me now?
There you go. Good girl.
Could we
Lay down, but not on the armrest. Thank you. Good girl. Alright, let me get it at least all the way back to the T junction. Another 2, 3, 4, 5, 6, 7.
Recovery mode that could make up for small changes in the
So much.
we can still function, but not too far. Do you have any insights there?
No, I mean, that's a great question, and I'd kind of love to know the answer, but I mean, I feel like the biology side of me, it's kind of like some life forms on Earth, probably not humans for a long time, could adapt to slightly more extreme temperatures either way. Like we see
This way, you just get in
tardigrades,
and
right?
you can
Water
get up and
bears,
go do
they
something
can
that
live in
goes on.
pretty extreme environments. So there's some possibility that if we nudge left or right, I'm using, which are not the right directions, but you know what I mean, closer to Venus or closer to Mars, that there would be something that could adapt and survive that. But I feel like humans would probably not be on the list for very long because food sources, other things would be affected so quickly. At least I think.
Okay. And by the way, there is no unique left and right in an orbit. Just the same way Rive Gauche, that's the left bank in France of the river Seine, whatever river is there. So the left is the shore that is on your left when you're moving with the river. That's a unique left. Yeah, a unique right. So when I say Venus is on the left, we are the river of Earth passing between Venus and Mars.
Sweet. Only Neil can make yes. Only Neil can make an orbit sound like sex. Alright, here we go. This is Jeffrey C. He says, hello, SMEs. My question, SMEs,
Subject matter experts.
Alright, so he just
Oh, is that land outline I see? Oh, so close.
subject matter expert. Okay. And he says, thank you, Kim, for filling me in on that. He says, my question straddles the line between science and engineering. My understanding is that every observatory is employing crazy incidence mirror designs primarily to minimize scatter and reflection losses, rather than to optimize for a minimal wavefront distortion. To me, achieving diffraction-limited imaging in X-rays sounds wicked awesome, but it seems like current X-ray telescope designs prioritize maximizing the collection of photons at the detector instead. What's the reasoning behind that? Please teach me more. Now, first of all, let me just say this. Don't nobody need to teach you nothing. Who teaches that? Who's going to teach you to that question? Just gave us the anatomy of the telescope in such a way that you show off, you big fraud show like, exactly do we get the photons to the detector? Like, you know damn well. And by the way, I love it. Photons on the detector.
Explain this. She didn't use the word racing, but that's what it is. It's a bit of mechanical and skimming with the rock on the behind. The phone raises a very important point.
Jeff from Boylston, Massachusetts. We're playing with you, Jeff.
Which, by the way, I have to give the shout out to Massachusetts fellow New Englander with the wicked awesome. That was perfectly, I mean, I just love this audience so much.
Yeah, wicked is a very New England expression.
Yeah, very wicked. Come on, kids. Very wicked. She gives me a cat.
But so, I guess I would say, like, there's kind of two issues at hand. I talked about a little bit earlier already, so maybe it's sort of helped. But X-ray photons, very energetic, very incredibly difficult to focus, right? This is high energy. It is bullet going through a wall kind of thing. So because of that, and needing the grazing incidents and having to, like, skip down across a pond, as we talked about earlier, there's two things to consider. The physics and the engineering limits. I'm not an engineer, so I cannot speak to this in, like, detail. But I will just say that, like, we already for Chandra had to have mirrors, like, really polished, incredibly smooth. Like, if you smooth down Colorado, Pikes Peak would be, like, maybe an inch tall, right? Like, it's a really incredible accomplishment or feat that American engineers had to do just to get the Chandra mirrors to, like, you know, near atomic levels, never mind what you would need for that kind of limited imaging, which would be like atomic scale perfection. And of course, like, the alignment in them as well, and then sending it up into space, into that, like, harsh cold environment where it would have to operate, like, perfectly. So there are some engineering limits there that I would say. Yes. Yes, but also, it also goes back to, like, that photon starved universe that I mentioned earlier in the show, right? X-ray sources are typically a bit fainter than all of the optical or all of the infrared data that can be gobbled up by these light buckets, right? And so the idea of building an observatory that would be able to collect enough of them, that is kind of like, that has been the priority, right? So maximizing your collecting area and getting, I don't want to say good enough, because Chandra's resolution is incredible to me, but, like, being able to get there with Chandra's second resolution was an absolute feat. So getting to go beyond that, it really becomes, like, true engineering and physics issues that have to be fixed by bigger brains than mine. So all I can say is wicked awesome question. I don't exactly have an answer, but I love that you asked it.
So, but it comes down to, like you said, you don't have all that many photons to work with. So you can't prioritize resolution. What good is your resolution if you didn't have the photons to collect? You got nothing to collect. So I have to agree, or to what was supposed there, that it's an engineering decision to maximize your access to photons than the resolution itself, even though you still have very good resolution.
Definitely.
Yeah. Okay.
Hey, well, by the way, Jeff, we love you. You big show off.
Definitely.
That was a great question. All right, this is Mario Funes. I think Funes. Mario, I'm gonna go with Funes. That's the spell. F-U-N-E-S. Funes. Okay. All right, Mario Fun. Okay, yeah. This is Mario from Port Lee, New Jersey, way across the river here.
Across the moat.
Oh,
Dude,
That was rough. Now, all you gotta do is
six.
yes, it is. But I love the boat because I live on the other side of the boat too. X-ray astronomy often relies on assigning colors to energy bands that are invisible to the human eye. How do you strike a balance between scientific fidelity and aesthetic impact when choosing color palettes? And have audience reactions ever led you to rethink your visualization approach? Does that also apply to sound? How do you get your baseline for sound?
That's not what the person asked.
Okay, but I'm just throwing that on top of Mario's question.
No, pay the Patreon fee. And then you can ask the half questions. That's $2.50.
Let's do two for one. A two for one. No, this is a great question because I love talking about this topic because it's so useful when you can kind of underline the idea that these are visual representations of data that is invisible to human eyes, right? And we're capturing that information, we are translating it into the visual representation, but those are human beings doing that process using software that's been coded by humans and making choices that human thinks are the best choices. But there's obviously going to be a wide range of possibilities. So for color palette specifically, we have pretty much settled on like an RGB red, green, blue for low, medium, and high energies for our color coding typically. So that means often Chandra images, if combined with say infrared or optical kinds of data, Chandra will often be colored in like blues and purples, and then say the Hubble data in the greens and the web data in the infrared in the reds, right? That's often what we're doing because we have found that that does tend to make an image that is both aesthetically pleasing but does align with that scientific information. However, there are many times when the color palette has to get thrown out of the window because the science says so, right? The data says so. If you're getting a massive data set and you are trying to pick out different kinds of chemical emissions in a supernova remnant and you're codifying where the pockets of iron and the silicon and the sulfur and the calcium and the oxygen are, you have to go into a different type of color scheme. So I guess the shortest answer is that we do have a kind of standardization, but the science drives the story, the science drives the visual, and then we adapt based on the needs of that. Now, to the last part of the question about rethinking visualization approaches, yes. So I've actually done studies because I like people as much as I like space. I like to learn about both of those things because we are not just studying space as robots. Like we are humans studying the universe around us. And so to me, at least, it's just as important to understand human perceptions and human understandings, human meaning making, right, of that type of data. So we have done studies on looking at how humans respond to our visualizations based on different kinds of color codes and different kinds of aesthetic appeal. And the interesting result was that it didn't actually make a difference. Even if some of the color schemes would have been like a bit like, oh, to me, in general, any color scheme that still got across the data that was described like what we were doing, that was the winner. And it didn't exactly matter how.
Are you kidding me? I'm still not off of the water.
Able to understand what the color scheme was, I guess is the point. Now, there has also been a case that I remember so specifically when it came time to do the bullet cluster, which is a cluster of galaxies and kind of like the textbook example with Chandra and Hubble that helped show this direct proof of dark matter. It showed the separation of the hot gas from Chandra.
Come on, get up there.
The normal matter, if you will, from all of the dark matter, which was gravitationally mapped, right? And it was all kind of with the Hubble data showcasing where the galaxies and everything were located. And for that image, typically the Chandra data would have been in blue, the highest energy in the data set. But when we first made the image, we did a little like testing of it, and it just, when trying to sell the story of all of this hot matter, the separation from the dark matter, it just was not vibing for people. So we actually inverted the color scheme, put Chandra in like the pink reddish color, and then put the dark matter map in the blue. And that worked better for people for that specific scientific discovery or scientific, expression, and has since been kind of like a de facto for how we color code those examples of galaxy clusters that are showcasing the separation of normal and dark matter.
By the way, for anybody interested, I don't know the name of it, but Neil gives one of my favorite explainers on how we take any bandwidth and make it so that we can look at it with our human eyes. It is a fascinating explainer.
Yeah, all about that. Yeah, it's in our archives. Yeah,
It's one of my favorites.
actually, really.
Yeah,
I told you that.
yeah, you did explain. You did an exceptionally incredible job of it, which is productive, but it was so clear, and it was something that secretly I never understood. So, I never understood, and then every time I explained it, it was just like, oh, right.
There's what they call explainers, I guess.
Yeah, I guess so.
And Kim, it should be fair to declare that if you assign an RGB to a low, medium, and high energy bands, I think we can, with honesty, say that if the human retinal sensitivity were shifted to that realm, it is the color picture you would see.
Yeah, they do tend to call them true color representations in that RGB setup for that reason. I like to think of all of them as representative color, right? Like, we're not the mantis shrimp being able to see all sorts of colors all over the place, right? But I do think it is fair to say that that is a more true representation, yes.
All right, time for a few more.
This is Neil Cameron. Neil says, Lord Nice, Dr. Arcan, Dr. Tyson. Neil here from Estonia, Connecticut. I'm going to keep this simple. Black hole sonification. Do they sound like or more like and
How do you read that off of this?
oh, because he said, do they sound like Godzilla roar or just a little bloop? So I gave him my best Godzilla roar. I make it work for Neil. And then the little bloop is bloop. Isn't it just the gas swirling that we can sonify and sound exit a black hole?
This is a great question, too. I love all of these questions. These are the best. So, yes, so nothing can escape a black hole, right? Like sound can't escape, light can't escape. So, yes, we are not holding up a microphone to capture sound of black holes. But black holes do have this potential, supermassive black holes in the center of galaxies do have this potential to, as I mentioned earlier, kind of like burp out into the surrounding hot gas around it and make these pressure waves or the sound waves. And so we're taking that information, which we can see in images by the rippling, mathematically mapping into sound. So we are choosing sounds that make sense for it. And we have done one sonification of a large population of black holes in the Chandra Deep Field South, where we actually did apply little boop boop kind of sounds. It sounds a little bit like Imogen Heap playing it, because we were trying to showcase a massive field with thousands of black holes, and we assigned the sound based on the energy level of those X-rays. So we just chose low, medium, and high sounds for those X-rays. So I don't know if that answered your question.
And the pressure waves, they actually are literally sound waves.
They are literally. So the Perseus cluster is that B flat that I mentioned. M87 also has them, and it's lower. I don't know what the actual note equates to. But these supermassive black holes do make these sound waves, right? They're not seeing exactly. They don't have vocal cords. But they are, by that sort of burping out into the area around them, it's all the environment that black holes live in, right? That's going to give you the interesting, whether it's a burp or some other kind of thing that we're detecting.
And a big part of that question was, is it the swirling of gas? And the answer is yes.
Yes.
Because the black hole is otherwise not talking to you. Right?
Exactly.
Chuck has the best ever imitation of a black hole.
Oh.
I don't know, but sound like this? Yo, what's up?
There's not someone hanging out in the shadows ready to mug you.
Rachel Ambrose says, "Hey there, this is Rachel from Austin, Texas. First, I wanted to say that the Chandra X-ray deep field soundification has been my ringtone for over a year now. So thank you so much for that."
That's cool.
Do you have downloadable ringtones on your website?
So I don't think we put them into ringtone format unless someone on my team did that and I didn't notice.
No, she just made it for you. You can make a ringtone.
But we have little snippets of the sound available on our website to download. So I guess if you can make your own, I never thought to do that. It's so lovely.
Okay, very good, very good.
She says, "My question for Kim is, if you could soundify one cosmic event that hasn't been done yet, something you think would blow people's minds, please tell us, what would it be?"
That's tough. My instinct, because I just love every data set pretty much, but I think something in the time domain, something that we're seeing change over time, that's something that I would really like to do some of more of. Like supernovae changing over time, gamma ray bursts clicking on and off, tidal disruption events, just anything that changes over time on like a human scale, if you will, that we've been able to capture. That's something that's kind of been on my list for a while. I don't know if it would blow people's minds.
Is that because the imagery would be composing for you?
Close.
Yeah, so it's already giving you like a sort of temporal flow, if you will. Like the data is changing at a rate that you could track and then represent in some interesting way. And I don't know, I think that would be very cool. I don't know if it would be mind-blowing, but it's definitely something I would like to try. That would be high on my list to work on with system sounds.
The time dimension is really what you're referring to there. As
Definitely.
yeah, okay, nice.
Hearing data can like draw your attention to different patterns, like we talked about that a little bit already, that your eyes can overlook. And so being able to sonify that changing data, I think, could be really powerful.
All right. Well, thanks, Rachel. What did they call it? It sounded like scat music, like, you know, a little alto would be kind of cool.
Would be very cool.
Yeah. Yeah. This is Colin Zwicker. He says, "Hello, Dr. Tyson and Dr. Arcan. I'm Colin from Switzerland, and I have a question for Dr. Arcan." Well, thanks, Colin. That's what we're here for.
Okay, nobody any slack.
Has there ever been a moment when a visualization revealed something that surprised you, something that you might not have noticed if you only looked at raw numbers?
Yes, for sure. I mean, and that is the kind of beauty of not just visualizing, but like thinking about how to visualize and what method, what platform would be best for your data. Because in supernova remnants, particularly, we've got 3D models of quite a few of them now based on observational data or computer simulations constrained by the observational data.
So close to being able to smoke some more pot.
Specifically, that there are some asymmetries.
That's a supernova remnant. Yeah.
Beautiful.
I forgot to count.
The Chandler's looked at a lot. Some asymmetries there, and the
6,
the
7,
image itself
8.
looks like so perfectly spherical and lovely, but when you break it down into the 3D model, there are some interesting asymmetries, and it also helps show that stars like Cassiopeia A can turn themselves inside out when they explode, because for explore amounts of starlight that explodes, the iron is kind of really built up at the core, and when you look at the distribution of that in the supernova remnant, the iron now is actually quite far out towards the perimeter, much farther than you would expect. And so researchers were able to figure out that that star turned itself inside out. And the use of 3D modeling is really really important, that type of result. So yeah, having different ways of looking at your data can be a very powerful tool for curiosity and discovery.
Very cool. Wow. Great question, Colin. All right. This is William Warren. He says, "Hi, I'm William Warren from Abingdon, Maryland. You've created immersive VR experiences of space data. Do you think future astronauts could use technology to prepare for deep space missions?" Which is cool because every sci-fi movie, when they talk about going to another galaxy, they like reach and throw something into the ceiling, and then the whole galaxy opens up, and then they actually take their hands and like spread it, and they get zoom in like we pitch on a computer screen.
Yes, that is to me like the exciting future. Like I actually dream about whether it's astronauts, researchers, non-experts, like being able to do that type of work, right? Being able to go into an extended reality space of some sort and learn about things, train about things, and whatever. But astronauts are actually already doing that. They actually use virtual reality and other kinds of extended reality technology applications in order to learn about spacecraft and like where they're going to be docking, how they're going to be docking, where things are located in their spacecraft. Special kinds of like training modules have been done with VR. It's already a very useful tool because especially if you think about astronauts having to do a spacewalk and to do some kind of complicated procedure out in space, being able to walk through it in extended reality would be a very powerful tool to help kind of fire up some of those neurons differently because there's tactile memory involved if they're doing it in a very simulated environment. There's been a lot of military studies about that type of work with simulated environments, which is why I think that idea of bringing it further out into astrophysics research and communications and all that is such a great idea. So yeah, it's a great question.
So do you think they learned anything from Pokemon Go?
Oh.
Where they insert virtual reality creatures out there?
Yeah, I honestly think Pokemon Go is a great tool. Like that was such a brilliant XR application that people picked up on such a massive scale. And I think having that kind of learning opportunity for different scientific and engineering activities would be fantastic. I mean, I'm not saying aliens, but like, different kind of experiences would be great.
It got people off the couch. So
It did. It did.
It clearly did something good because people were out, and it created a whole community of people because people would meet up to find the characters and meet one another. Like, oh man, you're a total nerd too. My God, I thought I was alone.
I love that. So great.
Yeah, super cool. All right. This is Alan Keyser who says, suppose you get one perfectly synchronized week on Chandra, James Webb, and an event horizon style array.
Yeah, okay.
Okay. What single measurement would you make to decisively test how local feedback regulates galaxy growth? And what exact observable or statistic would you publish so the rest of us can tell if you're right? Alan from Santa Barbara.
Jeez.
And he says, P.S. I am another show off.
Yes, is that a question? That's amazing. First of all, again, I feel like you might already know the answers to that question.
Yeah, I got a feeling Alan knows an answer to a lot of questions. Alan's sitting up in his classroom just like, these kids are stupid. Let me ask them. These dumbasses I'm teaching all day long.
Yeah. I feel like I'm trying to re-stump them, which is totally fine. First of all, I have to say it has to be a large community collaborative thing. There would be no magic wand to give me any of those superpowers with my super friends. By the way, the listing of Chandra and Webb and HT together, like that is a very cool group, I think, to be a part of. So major props to that. But all of these types of scientific observations with these massive telescopes is truly highly collaborative and all very peer reviewed. So no one person is ever making that kind of decision. I feel like I'm being a bit of a party pooper there. But I would say with the type of object I would pick is probably probably Centaurus cluster or a similar type of galaxy cluster with a nice active supermassive black hole at the center. Chandra could map the black hole activity. Chandra could map the surrounding environment of the black hole, the X-ray cavities, kind of carving out into the gas by those black hole jets. Webb could definitely provide the sort of map and history timeline of the star's evolution throughout that area as well. That would give you some really great constraining information. And then the Event Horizon Telescope, which is another amazing telescope, has already taken some incredible images, would hopefully be able to get us that jet launch point, I would say, from the black hole. That would be really cool. So being able to figure out, what I love about supermassive black holes is that they're responsible for the care and feeding of the galaxy, and I love that Alan's question, I believe, is kind of getting at that point, like how can we get even more data about it? So that would be my suggestion.
And if I say something just about people,
yeah,
my community of astrophysicists, unlike the example that Kim is describing, because that's just, you want to collaborate with people who will be on the various telescopes with a peer-reviewed project. However, if something goes down in the sky that no one saw coming, and I discover it first, and I see it first, I can set out a notice that night for any telescope where they can peel off an hour of their observing program to get data, because each telescope is going to be different focus, different bandwidth, different, and if the object sets for me, it rises for somebody else in the world, right? And so my community is very
So freaking far.
a phenomenon that comes and goes, and you got to get it in the spot.
I go on telescopes. I go on telescopes.
Yes, Chandra does it all the time.
That's exactly.
We have a co-brand.
That's exactly how that would play out. So that can happen for events that occur in the sky. But something so organized as the black hole in the middle of a galaxy trying to get the best data, that, like Kim said, that's a peer-reviewed, group organized activity. Yeah. So Kim, your Chandra deep field, is that a deep field unto itself, or did it do the same deep field that Hubble? Okay.
So Chandra did its own deep field, the Chandra Deep Field South, but it also did coordinated campaigns with the GOODS Deep Field that both Hubble and Chandra have looked at, and there have been additional campaigns as well. So deep fields are an area of really rich research for Chandra and Hubble and other telescopes, and you kind of can't have enough of them.
Yeah, you know how the first deep field was obtained?
No.
The head of the Hubble Institute.
And now I just remember it.
With his discretionary time.
Yes.
Every director gets a little bit of time, and they can do whatever the hell they want.
Right.
And he said, find me the emptiest area of the sky you can.
He was flexing hard.
That's play and creativity at work.
Yes. And he said, let's burn some telescope time
Looking at nothing.
looking at nothing.
And then something was there, and he was the luckiest director ever. Because if nothing was there,
He would have been in trouble.
you know he would not have been the director the next day.
Yeah, but it was the same for Chandra, because Chandra has less time to kind of give, right? It has to look at objects longer than Hubble has to. It was still in the position, but they looked at this one spot, the Chandra Deep Field South, which was seemingly empty, and they looked at it for 40 days and 40 nights, and they found this massive population of thousands of black holes and galaxies with black holes at their cores. So it's lovely when you can be creative.
Let me ask you about this. Whether there's empirical evidence
Bella?
or just your opinion.
Did you want up here, sweetie?
Is there anywhere we can point a lens?
Bella, do you want some
and
lap
see
time?
something in the universe?
With our
Yeah,
current
go give you some
telescopes,
kissy
In your
cuddles.
opinion.
Oh,
I know
take
we
my
haven't
girl.
looked at every place. In
Yeah,
your
oh,
opinion, is there
stay
any
away.
place we can
Oh,
point a lens and not see something?
yeah.
Look, go ahead.
That's my sweet girl. You my sweet puppy. You are. He's peaceful. Oh, thank you. Yes, I love you too, guys. Yes, I know. You guys do the best.
No reason to exist. We don't keep that in there, so I have no reason to exist. That's, you can't get mad at me.
So I'll give you my
It's a long train ride.
So I think the better way to say telescope that did not previously exist, and you put it anywhere, it's going to make a discovery because it's looking at the universe beyond the fence that was set up by everything else you've been using to look at the universe. Right now, but the universe is so vast. Kim, I don't think there's a place where there's nothing happening. What do you think?
So
Oh, I agree.
free.
I mean, like what Hubble did for the optical field, what Chandra has done for the X-ray field, what Webb has done for the infrared field so far. Like each time we launch these new telescopes, we're finding those things deeper, earlier, back further in space and time. And so it really is, I think, mostly at this point, a limit of our technological achievements.
Farthest
I
tracks.
don't know. It's a great question. It's a very exciting thing to think about. Props to you. Props to you.
Thank you. I'm going to say that the original answer was better than my question.
Here we go. Here's the desert.
So Kim, I think we got a book. It's there, but you better know that book. Tell me the name of that book. How to Freak Out Your Kids. What is it? Sorry.
Yeah, no, I hope not. Boy, space will freak you out. Just tell me I'm excited.
It's wondering about really freaky things in the universe. And what do you think about that? It's a long overdue book. It's a lot of fun.
I think it's fun, like Lemony Snicket for space kind of thing.
There you go.
Like, yeah.
Nice analogy there.
That's
Great. Yeah, the series of unfortunate events. Is that what that was?
Yeah, yeah, I love that.
So it's really a nice book. So congratulations on staying with it. We're in the same biz.
Not quite. I tried. Not quite in the same business as you, but I tried.
So Kim, this has been a delight.
Thank you. It has been so fun. As always,
There's the
I'm still waiting for my jacket.
I said Masters Gold Jacket, but the Masters Jacket is grade Hall of Fame. And that's what you get.
The gold sounds nice.
We'll work on that, Kim. Yeah.
All right.
So good luck. Sometimes that helps too, I'm told. But you're at it, and you're at it strong, and we're delighted for this to have been your fifth appearance on Star Talk. For anyone who wants to catch our prior episodes with her, just check our archives, vibrant archives of past episodes, and it's all there for you. In case you're a new joiner, for who and what we are. All right, Chuck, always good to have you. Always. And Kim, we all love you. Stay strong.
Thank you. So nice to be here.
This goes all the way.
Cosmic Queries.
I still gotta build all this out too.
As always, I bid you to keep looking up.
Badlands. And then all the way over here. Yeah, I know there's some cool stuff. But I gotta go all the way this way as well. And then build all this over to here. Hold on, let me find another.
Hi everyone, welcome back to On the Line.
Thank you to Display for supporting PBS. The multiverse pops out of quite a few theories of physics
All
as
the way.
a solution to certain vexing problems, but it's also been argued that the very idea of a multiverse is just bad science.
And then I've got
That it's unfalsifiable and a dead-end inquiry and as bad a violation of Occam's razor as you can imagine.
a
But
witch.
the multiverse can also be real. Can something that exists be bad science?
Creepers.
Hey everyone, a couple of quick announcements before we get started. We're running our algorithm experiment for the next couple of episodes. Our algorithm sharing our episodes with the full space-time community again. So we're trying to determine whether likes or comments are more influential. For this phase of the experiment, we want to see what happens if we can get 60,000 plus likes per episode. If you want to be a data point in this experiment, just hit the like button, and of course, feel free to comment as per usual. Finally, we have our July merch available. This is a special one. Retired scientist Dr. Jim Slater is a fan of spacetime and the creator of this incredible image of how the Earth and the Sun
Oh my goodness.
through the galaxy. And
Yeah.
gave us his blessing to put it on a t-shirt and a sweatshirt. So you can show everyone in your local patch of space-time a scientifically accurate movement of the Sun and Earth. We also have two new black hole logo space-time caps, one with a white hole and one with an all-black hole. Links in the description. In recent episodes, we've talked about how the fundamental parameters of our universe are apparently finely tuned for the production of entities that can speculate about the fine-tuning of the
Here's another
universe.
one.
One possible explanation that we've teased several times now is that there exists a preposterously large ensemble of universes spanning all possible parameters, both habitable and uninhabitable, with the latter being the extreme majority. We are, of course, in an habitable one by necessity. Some would say that this anthropic principle, this argument of an observer bias, actually predicts that a multiverse exists. Others say that the multiverse is just bad science. Before we decide one way or the other, let's review the types of multiverse and where they come from. And before we review multiverses, let's remind ourselves what we mean by universe. The original meaning of the word was just the totality of all existence, which makes the idea of multiverse nonsensical. If it exists, it's in the universe. But in modern usage, universe tends to mean this particular continuous space-time that traces back to a particular Big Bang. For that reason, we have more concrete terms. For example, the observable universe refers to everything we can see in that space-time given the amount of time light has had to reach us, whose outer boundary we call the particle horizon. But if you could teleport just beyond the particle horizon, presumably things would be pretty similar. More stars, more galaxies, etc., whose light just hasn't reached us yet. And we typically think of those regions beyond as being part of our universe. So maybe the universe is everything connected to the space-time that we live in. But there are conditions that might justify calling some distant but connected region a different universe. For example, if the laws of physics change over extremely long distances, there could be regions of a fast connected space-time that operate very differently to here. This is often called a quilt multiverse. A related multiverse comes from the eternal inflation hypothesis, where the main greater space-time is expanding vastly more quickly than our universe. Bubbles of more gently expanding space appear and become universes like our own. In this case, these bubbles may also have very different laws depending on each other. Other ways to generate universes with different physics include birthing them inside black holes, as in Lee Smolin's cosmological natural selection, or various cyclic universe options in which the laws shift between cycles. There's also the multiverse of the many worlds interpretation of quantum mechanics. Some of what I get to today is relevant to that, but I'm going to focus on the multiverses that allow varying laws of physics. There are concrete reasons that the laws of physics might change between universes. For example, changing the quantum vacuum state changes the physics. In our universe, the mass of the Higgs boson, and hence the masses of all other particles, depend on the slightly non-zero energy of the Higgs field ground state. But the ground state of a given field may be a local minimum, and other ground states are possible. Changing the Higgs ground state changes the Higgs mass, and how the universe looks very different. For almost all random choices of a Higgs mass, the universe is uninhabitable. Another example where the laws of physics change depending on the configuration of the underlying fields is in string theory. There, the machinery generating all particles and forces is in the form of compactified extra dimensions coiled into something called a Calabi-Yau manifold. the geometry and topology of this manifold and the corresponding string vibrational modes determine the properties of particles and the strengths of interactions. This leads to an enormous number of possible configurations for the ground or vacuum state, at least 10 to the power of 500 of them, in fact, each producing a universe with different physics. This is the string landscape, a colossal landscape of possible universes that may or may not actually exist out there. String theory can't tell us why our universe forms another young atom, and
So
vacuum state that generates the particles and forces withstand the quantum. Nor can standard particle physics by itself tell us why the underlying quantum field is going just isn't. Whatever all possible vacuum states can happen, we just happen to one of the versions capable of producing life. That's the anthropic principle. In its most reasonable form, it argues that we shouldn't be surprised to find ourselves in an unusual part of the unit/multiverse, because we ourselves are unusual. At some level, this is not in the least controversial. For example, we find ourselves in a very
good morning. Just a heads up. I've got clean shop towels here at the house.
very rare environment in our universe, a habitable biosphere. Even though habitable biospheres are more likely to be universe, that's a fraction of the volume of the universe. We're not surprised to find ourselves in one. I mean, we could have heard somewhere that we haven't emerged. Extend it to the multiverse for this one. It should be equally unsurprising that we emerge in a universe that can produce habitable biospheres, which in turn require a very specific configuration of laws of physics. And our universe's laws of physics change the strength of dark energy or mass of the universe, or even the number of dimensions of space-time, and our universe likely will not. But coupled with the anthropic principle, the multiverse gets us out of having to explain why these specific laws, and in a way also gives an explanation for why the physics of our universe seems finely tuned to allow life. It's a selection bias, just like the bias that leads us to observing the universe from an unusually warm, wet biosphere. Some take this much further. Some say that this apparent fine-tuning of our universe's parameters in favor of habitability is actual evidence for the multiverse. So now we have the multiverse and the anthropic principle very loosely defined. So let's decide if this is bad science. We're going to break this into two broad categories for criticism. One is that the multiverse is unparsimonious, Occam's razor. And two is that the multiverse is scientifically useless in various ways. It's not falsifiable and/or an explanatory dead end. Let's start with one. The principle of parsimony, or often called Occam's razor, can be stated in several ways, but let's start with one of the phrases.
I'm gonna be getting up and doing shop towels here momentarily.
Never posit plurality without necessity.
You can lay down over there.
Well, a multiverse is about as plural as you can get, so maybe we've already annoyed Occam's edict has been refined over the years. Another common phrase is, entities must not be multiplied beyond necessity. Again, it sounds damning, but we can at least start to pick this apart. What's an entity in this context? Isaac Newton offers some guidance. We are to admit no more causes of natural things than such as are both true and sufficient to explain their appearances. Well, this is a critical refinement. We're told to limit the plurality of causes in an explanation, which is very distinct from limiting, say, the plurality of predictions. Now, way before William of Ockham, we have some enlightening phrasing by Aristotle. We may assume the superiority, other things being equal, of the demonstration which derives from fewer postulates or hypotheses. A more modern and parsimonious version of that is, all else being equal, simpler explanations should be preferred over more complex ones. So, the thing we we are advised against multiplying is not the outcome or predictions of a hypothesis, but rather the number of entities in the explanation, the causes, not the predictions, according to Newton. But what are these entities? Well, they are the number of postulates or assumptions, basically the number of new things required to make a hypothesis work. These could be principles like law of physics or an initial condition of the universe, or they could be physical stuff like a new quantum field or a multiverse. In general, Occam's razor wants us to be reductionists, to minimize either the complexity of the underlying theoretical framework or to minimize the number of fundamental building blocks to seek theoretical or ontological parsimony. In fact, these two things may ultimately be the same thing. Occam's razor basically warns against overfitting. If you want to find a mathematical description of some arbitrary curve, you can always do it if you have enough degrees of freedom in your function. For example, a Fourier series with an arbitrarily large number of terms can fit any continuous curve. But the resulting mathematical form has no explanatory power. It's not a general law of nature that can make predictions beyond its overfitted curve. We could equally describe the universe as a vast map of points indicating the location of all particles, but that's complex and useless compared to the relative parsimony of the standard model of general relativity and some initial conditions. So, with that refinement of Occam's razor, where does the multiverse land? In cases where a theory predicts the existence of a multiverse, it seems that Occam's razor doesn't apply, especially if the theory was concocted to do a different job and the multiverse just popped out. In that case, the multiverse is not a prior assumption of the theory, it extends from it. So things like the string landscape, the eternal inflation multiverse, and honestly, even the splitting timelines of many worlds shouldn't be considered a problematic plurality when it comes to assessing these ideas. When we bring in anthropic arguments, the situation is muddier. We could say that the multiverse is predicted by anthropic arguments in that fine-tuning plus selection bias demands many untuned universes. But we could also frame the multiverse as a cause or an assumption in our argument with the fine-tuning because there's a multiverse. In the latter case, we need to pick apart our principle of parsimony a bit more carefully. If we propose or assume, postulate a multiverse as an explanation, have we multiplied entities beyond necessity? Have we overfit? Some would say yes. I don't agree. It's tempting to want to assume the least extravagant universe possible, but the size or the number of universes doesn't necessarily map to the number of new prior assumptions that we would use to weigh our hypothesis against Occam's razor. And the impulse to argue for the least extravagant universe has failed us in the past.
Oh, look, there is a path.
The ancients rejected the idea that the Earth is moving around the Sun because if that were so, then the distant stars should appear to change position relative to each other in parallax. They didn't consider that it was even reasonable for the stars to be so far away that parallax was too small to observe. Their bias towards smallness led them astray. In the Great Debate in 1920, Herbert Curtis argued that the redshift of the spiral nebulae meant they had to be entire galaxies far beyond the Milky Way, while Harlow Shapley represents the status quo feeling that such distances would be an uncomfortably large universe. But now we're completely comfortable with an observable universe 93 billion light years in diameter, and a greater universe is hundreds of times bigger or even infinitely large. So as our measured boundary of the universe expands, so does our acceptance of the preposterous size of the sun. For this reason, it's no longer compelling to argue against the multiverse based only on a sense of excessive bigness. If that bigness encompasses regions where constants of nature shift or stretch to regions where inflation never stopped, that's not necessarily unparsimonious due to sheer bigness alone. Occam's razor asks that we seek the fewest moving parts, but it doesn't say anything about the size of those parts. So, the parsimony of a given multiverse theory is really equivalent to the parsimony of the theory that predicts the multiverse, which has little to do with the multiverse that it predicts. If eternal equation or string theory or cosmological natural selection or whatever are not too far-fetched as solutions to fine-tuning themselves, then neither is the multiverse. Okay. On to the next point. Is the multiverse bad science because it's unfalsifiable or an explanatory dead end? I'm going to only touch on this one because there are details that warrant spending a lot more time on this, which now. So, the badness of multiverse science depends very much on your definition of science. If you adhere to a strict Popperian view that science is only that which can be falsified, disproved by durable experiments, then you could argue that the multiverse is not even science. But by the same logic, you could argue that hypothesizing that galaxies exist beyond the particle horizon is also bad science because you can't test those either. A more relaxed view would say that science applies logical reasoning coupled with a whole suite of tools to collectively find a consistent picture of what reality is. If something is potentially part of reality, then it's in principle approachable by scientific methods. So if the multiverse might exist, then it's very much in the realm of science. And in fact, it's not true that we can't test multiverse theories. There are a few proposals for direct tests for other universes that I won't get into here, although we've talked about a couple of them before. But there are also tests that involve predicting what we should see in this universe if its unusual properties really are a result of anthropic selection. For example, Stephen Weinberg showed that anthropic arguments gave a pretty clear prediction for the value of dark energy under the assumption that our universe should have the most likely value for dark energy that could permit our existence. The broader topic of anthropic predictions is deep and fascinating, and I'll also save it for another time. The fact that various multiverse ideas are testable given sufficient creativity means they also are not scientific dead ends. It's not true to say that by allowing anything to be possible, we no longer have a path to explaining our universe because all universes exist. In fact, the foundational theory that allows the multiverse to exist will make pretty specific predictions about the distribution of properties of the universes in that multiverse, and that concentrate on the likely properties of our universe under anthropic selection. So the multiverse doesn't have to be bad science, but it also can be. If the idea is proposed as a blanket answer to fine-tune without a concrete mechanism that can be used to make other testable predictions, then your proposition is indeed unparsimonious, unfalsifiable, and an explanatory.
It's not snowing.
Bad science. But that's not how
It must be getting to the outer edge because normally it's snowing.
Treated with due care, we can indeed science the prospect of the plurality of space-time.
Thank you to Display for supporting PBS. While space might be defined by its lack of walls, if you're watching this, you probably have walls. And if you've ever thought of merging your walls with your passion for space, there's Display. Display posters are high-resolution, vibrant metal posters, and they have thousands of space images. For fans of technical visuals, Display has images from JWST and NASA. For fans of creative imagery, they have hundreds of space-inspired designs. Some finish with Display's texture 3D application, which features a blend of tangible textures, 3D contouring effects, and selective matte and gloss finishes. Each display gets attached with an included magnet kit. So when you're installing your display, there's no drilling, no holes, and the magnets will work for any one of Display's 2 million plus artworks. Right now, there's a promotion where you can get between 75 and 37% off your order, depending on how many displays you order. When you use the code SPACETIME. There's details and link in the description below if you want to explore more.
There were folks who were going to measure the radiation left over from the Big Bang, the cosmic microwave background, and they were going to very precisely determine the state of the universe as it existed shortly after the Big Bang. And we have a new model of the universe, which goes by the sexy name Lambda CDM. How do I go from the early universe to the late universe? We get the dark energy shortly after the Big Bang in a series called conflations. Is there a way to reconcile this without having to invoke another tooth fairy? Yes. Invoke Santa Claus. This is Star Talk. Neil deGrasse Tyson, your personal astrophysicist. I got with me co-hosting. What's up? How you doing, man? I'm good, buddy. Good to see you. Good to see you again. Professional comedian. You got your own podcast. Yeah. Inside Out. Out and In. There you go. Giant Burgers. Yes. Do they sponsor you? Yes. For those listening and watching, this is how not to host the show. Have a guest and not know anything about it. Yes, it's called In and Out Burger. And the whole podcast is me interviewing people in the drive-thru. You want fries with it? Oh, you're an astrophysicist. The guy was on my podcast. I was. Along with Paul McCartney. Oh, okay. Okay, that's all you say. Name dropper. Yes. But none of that impresses me. As when you got like a Peabody Award and an Emmy Award. Yes. I'm writing you. I've been writing on the Daily Show. Yep. And on the Colbert Report. We love you, man. Hey, I love you too. Thanks for spending some time with us. Absolutely. Always great. Making us happy. You know what we're talking about? The cutting edge of cosmology. Because everybody's talking about cosmology all the time. But who gets in there? See, where's the edge? Yeah. Where people and stuff. Yeah. We like to mix it up here. Where can we get people at each other's throats? At each other's throats. Because that's actually, I mean, the history of science shows that's how discoveries emerge. Now, I have to say, I'm doing two of these with you. This one has, like, it's really cool, really interesting because there is a lot of back and forth on this. It's really yeah, that's good. And a lot of people, contenders, I think, is the way to think about that. So we combed the universe to find who would be ideal in this conversation. And we found an old friend and colleague of mine, Adam Reese. Adam, welcome to Star Talk. Thank you for having me. Welcome to my office here at the Planetarium. Excellent. Yeah. I mean, I was just wandering around the museum and you guys pulled me in. You were. He was with a bunch of children and his hand was being held by a teacher. Yeah. He might rebellion and have a Nobel Prize, but apparently he gets lost in large space with everybody. So you're at the Johns Hopkins University. Yeah. You're the Bloomberg Distinguished Professor there. And Bloomberg, he's a friend of my wife worked for him. He has a background in physics and engineering and came to Johns Hopkins. Yes. And donated a whole building called the Bloomberg Center for Physics and Astronomy. Yeah. Yeah, so there's some good Bloomberg action down there. And he ruined everything when he created bike lanes in New York City. I'm telling you, let's spend an hour on that. Mr. Nobel laureate, we fix that? Says the man who does not ride bikes. Exactly. Okay. Many people don't know that the Space Telescope Science Institute which was responsible for receiving all the data from Hubble and other telescopes, spaceborne, is co-located on the campus of Johns Hopkins University. So you also have a position there. That's right. That's where we have to do it. Okay. We're going to leave that right there. We have to add that you're a Nobel laureate. That's badass. Yeah, and I think if you have business cards, just have Nobel. You need anything else? No phone number. No phone number. You just think you want to talk to him. He's so smart, he calls you. So, everybody, what year you won that? We won it in 2011. You won the Nobel Prize, and that year was split three ways. So, who were the other two recipients? Brian Schmidt and Saul Solomon. Right, and Saul, I remember, was a West Coast guy. Right. He led the supernova cosmology project. Okay. With the same intent of making the kind of measurements you were making. That's right. With Brian Schmidt. Right. Okay. We were members of the IC supernova team. IC Very High Redshift supernova team. And it was given to you specifically for the discovery of the accelerating expansion of the universe, which today we just call dark energy. Well, dark energy is, we think, the driving mechanism for the acceleration. There's still a lot we're trying to understand about the nature of dark energy. We'll get back to work. Please. So, I'm going to say welcome to Star Talk. Thank you. Yeah, it's an honor to be here. Yeah. And so, you are co-discoverer because growing up, I mean, growing up as a kid,
A big ice pile.
school, in graduate school, we always knew that there was this term in Einstein's equation that it referred to like a negative gravity or something. It was mathematically legitimate, but no one had ever. What is that? Nobody accounted. No, what is this? It's a math thing. So every time we had a conversation about the expanding universe, we had to explicitly say we're going to assume this is zero because we don't. What are we going to do?
I think it's expanding at a constant rate.
Or expanding only according to what the galaxies are. Yes, this would be an extra thing going on. Okay.
And you were just too lazy to explore that?
No, apparently this gentleman was not too lazy to explore it. And he's saying, that is the thing. Okay? And there you go. Wait, so first, catch us up on being co-discoverer of the accelerating universe through these equations that I'm describing here. And you're getting data. What was your data?
Sure. So as you said, this term that Einstein had put in, which he actually put in for a good reason. At the time, he thought the universe was static, and so this term was needed to balance the attractive gravity.
Otherwise, the universe would collapse on itself.
Correct. That would just collapse. And then, so astronomers at the time thought that the universe was static because they thought the universe was the Milky Way galaxy. They thought that was already everything. Of course, it turns out there are galaxies out there. They're moving further apart. Hubble, and then Hubble the man. Yes.
Hubble was a man before he was a telescope.
That's right. It's more like the RoboCop version. But he would be mistaken for a telescope at a lot of times. Yeah, so shape of the body. The famous story is that once Hubble showed Einstein that the universe was expanding, in which case it was unnecessary to have this kind of repulsive gravity to balance things, and it was kind of dropped to the side. But as we know in physics, when something is possible, it is always there unless you have evidence that it doesn't exist. So,
very important bit of scientific wisdom there.
So let's jump to the 1990s, and astronomers are looking.
That was the 1920s.
That was 1920s, yes. So we're in the 1990s now, and astronomers think there's some matter in the universe, and the question is there enough matter to stop the expansion of the universe? Like, launching a rocket, does it have escape velocity from the gravity? Is that matter something that would later be called dark energy? Is that sort of... No, this is what we call dark matter. At the time, we knew there was a lot of matter. Most of it was dark. We knew this because there was extra gravity, the rate at which galaxies, stars orbited galaxies, the stars would have flung out if there wasn't this extra matter. So we knew all that, and then the question was, is there the critical amount, the amount that would halt the expansion, or would the universe expand forever? So by the late 1990s, the best way to do this was to measure the expansion rate of the universe in the past and compare it to the expansion rate in the present, and see if it was slowing down enough to stop. And this is where the distance ladder comes in terms of measurement.
How do you know how far away? I mean, it's hard enough just nearby. I guess we can use parallax on stars, but these stars are sitting on our noses. We have whole galaxies nearby and beyond. So, what method you had to really refine a method to do this?
Yeah. So parallax is great. Having a tape measure and running it out somewhere is great, but it just doesn't work.
Very
you get
long.
those at Home Depot. Yeah, I know, but not that long.
With your Home Depot tape measure, you get the things that are walking distance of you. All right, but there's stars out there that you can't do radar beaming to them. They're light years away.
You have to use parallax, a form of geometry that had its limitations because of the angles of the geometry.
You're just trying to make up for getting something wrong a minute ago.
I think.
But you did good. You did good. Man.
Yeah.
You did good. Yeah. So you have your two eyes. As you put your thumb, and you just look at your thumb with one eye, and then you switch eyes, and then your thumb's like moving back.
Yeah, I need a manicure.
Wait, what am I doing now? Yes. You look at one eye and switch eyes, and your thumb will shift back and forth.
Yes, right.
You shift.
Right.
It turns out the amount that shifts and the distance between your two eyes uniquely determines how far away your thumb is.
Which is then used.
So try to put your thumb here and do the same thing. So now it separates even more.
Yes.
So that's an angle. You can measure the angle. You know how far your eyes are. You know exactly how far away your thumb is.
Well, that works. Either way.
I'm blind both ways. So, what are our eyes? How do we do this astronomically? Well, you can take a picture of a star, and there's a background of the star behind it. And then 6 months later, take another picture of that same star. Now, the width of your eyeball is the diameter of Earth's orbit. Now, that's a good thing. Now you get that, and you see how much it varies. You know how the diameter of our orbit, bada bing, we get the distance to it. And we have sent telescopes into space to measure this exquisitely, far beyond what's even possible from Earth's surface.
Bubble and then web.
Very reliable. No, it's a telescope called Gaia. Gaia. G-A-I-A. So now, we trust these because it's like geometry. You got this. But now you have to go beyond that, and you don't get to use parallax.
Right. So then you have to use another method, okay? And there are methods that we use here on Earth, like a lighthouse. So you're a ship captain, you want to make sure you're far from shore. You want to make sure a lighthouse, which you know is very luminous, looks very faint, assures you, wow, I have to be far away. We can actually do that quantitatively by measuring how bright a lighthouse actually appears. So,
I had an analogy, so a good one.
in the past, there was a class of pulsating stars called Cepheid variables that have this wonderful property that they tell us whether they're a very luminous lighthouse or a not very luminous lighthouse, depending on how frequently they pulsate. And they're about 100,000 times the luminosity of the sun. So the big advantage is if you want to measure far, you better have a very powerful lighthouse.
Right.
So they were good for a while, but we had to go out much further.
That's a second rung distance ladder, right?
Yeah, I think so.
It is.
It's the third one after the Home Depot.
Okay,
Yeah, that's right. So you said something important there. It's 100,000 times brighter than the sun, which means the sun at those distances we would just never even see it.
Right.
It's not useful.
Right, that's right. So the name of the game at this point is to be able to measure truly cosmological distances very far out. We're really just in search of an ever more luminous standard candle, something that you can just see far away. If you can't see it, you can't measure the distance.
For me, explain the standard candle, and that my understanding is that we don't really know what that luminosity is.
So a standard candle is any object whose luminosity is uniform. So when we see a standard candle and it's uniform, when it appears dim, that tells us it's far away.
And we know that we know why they're uniform. That's
Correct. We know we start out with very good theoretical understanding, and then ultimately we have empirical understanding that shows us that. So by the 1990s, Cepheid variables are just not luminous enough. We really need things that are billions of times more luminous than the sun, because we now want to look so far back that the universe has changed, that the universe is younger, that it was expanding at a different rate. So this requires us to go back billions of light.
So it's like when you're a kid, you shoot up one summer, Neil's like,
Right.
or yes.
Or shoot up. It's kind of what you were doing. I don't know what you do. I don't know what kind of job this is.
I'm from the streets, everybody. I grew up on the streets. No, you shoot up in height. Like in one summer, you go from 4'9" to 5'9".
Okay.
But then as you get older, it progresses slowly. So that's sort of the idea here. In very rudimentary terms, when you're going back to the early stages of the universe, you're going
back to the younger.
yes,
Right.
where the expansion is fast.
We don't know that yet.
Well, it could be.
It could be slow.
Right. So let's not jump the gun. So by the late 1990s, we had known about supernovae. Gosh, going back to the ancient Chinese, that a star would suddenly appear where you had saw nothing, and we came to realize that these are exploding stars that are billions of times the luminosity of the sun.
In fact, the very word supernova, nova means new. It is Latin. And so a really bright new thing called supernova, and only we would later learn that the star died at the end of his life. Right. Yeah.
My wife calls me
Dying. You don't have to feel that.
But anyway,
He's full therapy. We'll
I didn't mean to look at her eyes when I said that.
so what we came to really realize in the 1990s is there's two completely different ways nature produces this kind of supernova explosion. That's very important. One way is you have a very massive star that loses its ability to produce energy at its core. And producing energy was the way to produce pressure that held back gravity. And so it's a very dangerous thing for a star like this to lose the ability to do that. It's basically lost its structure, and so it will implode followed by an explosion. And those are very bright, they're great, but the problem is they come over a massive star, or a medium star, or that could have been a star that when it collapsed turned into a black hole, in which case we'll see almost nothing.
So they're not as reliable as a standard candle.
So it's not going to be a good standard
Not a
candle.
standard candle.
It's not a good standard candle.
Yeah.
And then we realized hiding in this distribution of all kinds of different exploding things was a subclass that were all the same. And that is a completely different mechanism. It's called a type 1A supernova. And that occurs when you have the core of an old star, like our sun will become, called a white dwarf, which is in a very special state. It's holding itself up against gravity because of quantum mechanics. And it can only be stable up to a certain mass, known as the Chandrasekhar limit, after the famous Indian astrophysicist Chandrasekhar,
Yes,
who in the 1930s showed that a star could only sustain itself up to about 1.4 times the mass of the sun. So now imagine this. You have a white dwarf star sitting there. It's less massive than this Chandrasekhar limit. Maybe it's the mass of our sun.
And minding its own business.
It's doing nothing, and it would be happy that way. It would just cool off and live its whole life that way, cooling, radiating. But what if it has a friend that, with friends like these who need enemies, these are a star orbiting that star, and they get too close, we think, and mass starts to transfer over, we think, and the details of exactly how this occurs are debated. But somehow the mass transfers exactly. Whether it's like they actually merged or it was a gravity.
It's the same thing between Einstein and you guys. You leave a lot of stuff off to the side.
We're not sure, but we'll just go with it.
Well, because he's after the consequence
That's
of what
correct.
happened.
That's correct. That'll be clear in a minute. Okay?
Yeah.
So anyway, somehow mass transfers over, and when it reaches that Chandrasekhar limit, it's like boom, a thermonuclear explosion runs through the star. Okay, and what's so great about this is they always blow up at just about that same mass, very close to that. So this is a standard candle. This is something you recognize it far away. And how do we recognize it? It has a certain spectrum. It has a certain chemical fingerprint.
And this was observable within the Milky Way because that was a distance that we could observe this, or we
can observe these beyond. We can observe these at some of the most distant galaxies.
because of the telescopes.
Right. Now, they're incredibly rare. There's only one in a galaxy like ours per century, but there's no real limit of galaxies. So if we could take a wide enough image that contains hundreds of thousands of galaxies and then come back, a month later, what turned out to be, so unlikely to happen is like guaranteed to happen. Like winning the lottery because you buy all the lottery.
That's right. Chuck, last year we all went to your comedy show
Yes,
right here in Manhattan.
that's right.
And what was the title? What did you call it?
It's called Chuck Nice, Just Smart Enough, because I sit next to you.
No, we love you because you have a science literacy and you don't let anything by.
Yeah, well, I took that and I put it in a comedy special, and you were there in the audience, and absolutely. And just like if I were on the Tonight Show, I have no idea what it is. But check it out. I am too lazy not to believe in God. Okay? When you ponder the origins of the universe, that gets very, very deep. A singularity, just that by itself. Something that is infinitely hot and infinitely dense. How can it be infinitely dense? It's something you can't achieve it anymore. Like what? And at that point, I'm just like, God did it. December 30th, you'll be able to come to Star Talk and you'll be able to see the whole comedy special. So bring in the New Year with some science, dumbass. Please head to the Star Talk watch page on YouTube and tap Notify Me so you'll get a ping when we go live. And then we'll watch it together.
Be there. And you began this in graduate school, if I remember correctly.
Yes.
And that whole group.
Yep.
Who's the head guy of that group?
Brian Schmidt, and Bob Kirschner, and the Chilean group of Colantololo, which you know very well.
Right.
And so what changed the game was in the 1990s, we both came to realize that this class was special. It wasn't like the other supernovae. And the advent of large cameras by those standards on telescopes that had a big enough field of view that you could simultaneously stare at 100,000 galaxies and actually have a chance to do this experiment, actually find supernovae on demand.
Right. So you didn't have to wait around for one to show up and then look at it.
Right.
You would like, we're going to find 3 supernovae tonight.
Right. And it was actually quite amazing because back in the day, when the Hubble Space Telescope was a new thing and it was incredibly valuable to get time, we would propose for time and say, we'll tell you exactly where the supernova is on Tuesday so you can start observing it Thursday. And they were like, you're going to what? Like, you're going to tell
most capable facility, just like there's
This type 1A supernovae are visible halfway across the universe, but they're only useful as a standard candle once you can calibrate those that are closer, that have some overlap, maybe with the Cepheus. Is that right?
For the discovery of the 1990s, that the expansion of the universe, is here's the big spoiler alert, that it was accelerating, not decelerating. You don't even have to calibrate them because you're only using them as relative measures. You're saying how much was the universe expanding back then relative to how much it's expanding now. Even if I don't know an absolute number,
divides out.
it divides out.
there.
Well, yeah. Neil is handsome, but relative to me, not so much. Okay. So yeah, I've forgotten that that's important. That's very important. So the two stories we're going to tell disconnected that way.
Yeah.
And so by the late 1990s, even if I didn't know the true luminosity, was it 10 billion solar luminosities or 8 billion solar luminosities? What I can say is, oh, that distant one was so faint that it is, 10 times further away than this one. Whatever the true, and you've got history or experiments.
So you've got a whole string of pearls through time.
That's right.
And space.
So it's like you're a super sleuth in a way. It's like you're a detective using evidence. But within the distance ladder, you have these three rungs, and what strikes me is four rungs. Sorry, you have it. Right. But to be clear, this entire discovery of the accelerating universe only depended on one rung internally to itself.
Yes.
But if the Cepheus has sort of got a, so the dust affects its brightness, right?
That's important.
So now that rung is sort of there's some weakness in that rung which can propagate through the rest of the distance ladder. So how are we accounting for so much we don't know? Dust, right? Or other components that could sort of affect one rung of the ladder could then sort of throw off the entire calculation.
Or even dust even in your relative comparison, the dust would give you the wrong distance.
Right. So when I was a graduate student, this was the part of my thesis was to figure out how to contend with dust in these type of supernova observations. So it turns out that dust makes things dimmer, which would fool you into thinking it's further away. That's very bad. Okay, but it does something else too. It makes light look redder when the light passes through it. So look at a sunset, right? Not only does the sun look dimmer, but it also looks redder. So if you're seeing the red, then you know there must be dust. Exactly. But then how do you determine how much dust? You look at some supernovae where there is no dust, like it's way far out of the galaxy, or it's the bluest one you've ever seen, or something like that. So the power of the red
against the dust.
The redder it is, the more dust. Right. And in fact, if you really do this right differentially, all you need to know is it's so much redder than other ones, and then that affects how much difference it is. You're sort of you're getting these pieces of evidence and building. That's fascinating.
So much science happens that way. People think it's just one question and one answer and one experiment.
Yeah.
Techniques. Oh my gosh. So much.
Well, what's striking me in all of what you do, not so much Neil, but you, is you hit a roadblock and find a way around it. Right.
Yeah,
that's
also
most
of yours. Really clever people.
Yeah, exactly.
Team.
It's fascinating.
Okay, so now, if I remember correctly, the goal wasn't so much to measure this Einstein curve, was it?
No idea. No,
it
wasn't even on my radar.
It was just to lay it out. It's just to see what's going on.
It was just to measure how much the expansion was slowing.
Okay.
Right? And was it slowing enough?
Equations.
Yeah.
Tell me what.
So I wrote some down. Yes. Okay. So I wrote down some standard equations of what should have worked for the data, which is
anyone would know.
Right. And you were thinking it was slowing down. And not only that, I was so sure it was slowing down because that's what everybody told me, and I was in graduate school at the time. I said, okay, so the supernovae will measure the slowing, and I'll immediately convert that to what is the mass density of our universe, this famous number called omega n, and then apply that to our universe. Right away, yes, but right away that number tells you what we want to know. If omega n is greater than 1, there's so much matter in the universe it will recollapse. If it's less than 1, it will expand forever. Omega m equal 1 is called a critical universe. It's the mass it's the gravity and mass that the Earth would have to have. So is this to launch a rocket and have it be escape velocity? So is this the big freeze, the big rip, and the big crunch? We'll get to that. So can you catch up?
Yeah.
So anyway, I got stuff to do. universe that's causing the slowing expansion. So when I wrote my computer program, I said, hey, computer, fit that and tell me the answer. And the answer it spit back was negative mass. Okay? Now, there's no such thing as negative mass. That's not like a physics option. But, computers don't know physics. So you give them very simple instructions, measure deceleration, turn it to mass, and I hadn't yet noticed that the data was saying the universe was accelerating. So it was like, okay, you want me to make that equation work? I'll just flip the sign over here on matter. Now it's negative. And I'm like, that isn't right. We can't do that in physics. We can't import that. And so after doing a lot of checks, I was like, well, what could do that? And then, it was like all the classes we ever took was like, Einstein once had suggested something that could go the other way. You put that into the equations and it fit like a glove. Bada bing. Yeah.
And you've got it not just expanding, but it's accelerating in its expansion.
Correct.
And now it's y, and that gets you to dark energy.
Right. And so what is it? So, you made the measurement that it exists, right? Which is a separate thing from knowing what it is from the interpretation. Yeah. Right. And just to mention, people need to sink in. Yes. Because the universe accelerates, whatever's doing it. If we can make measurements of things, even if we don't know what's causing it.
Well, it's how some of the greatest things happen. So you're going for A, and then you find B, and this is going to sound like, as a writer in a room in comedy shows, you could give us an assignment, write a joke about, I don't know, airplanes travel, right? And nothing great comes. And then just out of that comes a great side bit that ends up being, that's how the Back in Black segment came about at the Daily Show. Because because we were trying to come up with great jokes on these little stories like a Florida man. And we're like, we don't know what to do with this. So like, give it to him and let him rant. So it's the same, it's obviously in the arts, but it's the same thing. You're going for one thing, and in a beautiful way, it's like a beautiful mistake in a way.
But it's also the thing that still to this day we don't know for sure or understand well. I mean, we could say the universe is accelerating. There's no question about that. But what is causing it? We're still relying on Einstein's cosmological constant, or more generally, dark energy. But we don't understand the physics of that at all. Get back to work, too. Yeah. What are you doing here? Yeah. You made the discovery. Yeah. I expect part 2 of it.
Oh, yeah? Well, actually, there's something funny about it.
What?
I've been sitting on it.
What?
It's bothering me. You ever get like a pebble?
Yeah.
Like, what? It's like, oh, man.
What?
Wow. There you go.
Wait a minute.
Did you put that on the street?
Wait, it's in the gift shop downstairs. I got a guy. Don't fight because it's Chuck Bling. It's bigger than this. That's a club. So, they didn't give us the Nobel Prize for discovering dark energy, but for discovering the which is
Accelerating. Right. That's why it would be bigger if it was more significant. It's just a little discovery, so they give you the baby Nobel Prize.
That's right. I'm sorry. I guess that's Alfred Nobel. Yeah, it is. It's over there. Very cool. Is this actually gold? Was it gold like 18 karat or something? I know it's worth a lot today. You gave it to me. It's worth a lot today. Have you seen the price of gold? It's 4,000. I'm worried walking out on the street. There's a funny story about Brian Schmidt taking his on the airplane, and the TSA agents were very confused because when they x-rayed his backpack, it showed up as a hole in his backpack because the gold doesn't go through the door. It doesn't go through. What is in your backpack? And he was like, he took it out. They go, what is that? And they said, it's a Nobel Prize. They said, who gave that to you? He said, the King of Sweden. What did he give it to you for? For discovering the accelerating expansion of the universe. They were deadpan.
Basically, this guy discovered that you wouldn't be here if I wouldn't be talking to you right now. Can I just say something? You're brilliant, and I'm impressed with that. But I'm more impressed that you're walking around New York City with that in your pocket.
I hear people are nice here. So it doesn't come with a thing around your neck like the swimmer,
Yeah. It's Mark Spitz. We had
Stay modern here.
No, I'm going with Mark Spitz. I was a swimmer. Michael Phelps.
Yeah.
This is heavy.
Yes, it's probably
Oh, nice.
Better give to Archimedes and figure out.
So nice.
And where did the gold come from then? Wait.
Oh,
my God! It's full circle. They said we want to give you something that really represents the work you did, and they was like, find a supernova by Tuesday.
do we know here at the American Museum of Natural History in our backyard? It's our yard, but it's run by the city. The city controls it, including the dog run. But there's a monument there, put there by one of the Swedish pharmaceutical companies.
In the Teddy Roosevelt.
In the park. Yes, in honor of all the American Nobel Prize. And my boy's name is on that.
Yeah, they're all park.
Chisel in.
Yeah.
My boy's on that bitch. Wait,
Oh,
there's a dog run.
I say John's wanted they.
So what? We live on 70 last year, right around
Yeah,
the corner from
yeah.
here. My dog pees on your name.
Really?
I'm sorry.
No, my name is actually pretty high up.
I have a very big dog. My dog is well endowed. That's all I'm saying. He can reach high.
So say what you said again because it's important. You got this not for knowing what dark energy is,
Right.
but for the discovery that it exists.
For the discovery that this phenomenon, the universe accelerating, exists, which everybody attributes to dark energy because normal gravity from matter doesn't do that. It goes the other direction. It's like
driving sign that shows
right. It's like having a car and like all you've ever done is hit the brake, and then one day the car just takes off, and you're like, how did the brake do that? And it's like, no, a different pedal, the gas pedal did that.
And I think you started to move towards the idea that dark energy determines the fate of our universe, right? And that's where it becomes, which makes you a real Debbie Downer. There's big freeze, there's big rip, and there's big crunch, which actually feels like Ben and Jerry's anxiety flavor. It's like, you would be the big freeze because you're closed off emotionally. You would be the big rip, you're strong, and I'd be the big crunch because I'm a baby. And everything collapses.
The big crunch, I think, is not in the cards.
Actually, everything's on the table still, to be honest with you. And in light of some more recent results on dark energy, where it may look like it's thawing or weakening.
Well, let's get into that.
So we will.
Let's get into that right now. We're all up to speed now.
Yes.
And we have like 3 minutes left.
Yeah. So the universe is accelerating, and we have a new model of the universe, which goes by the sexy name Lambda CDM.
Okay.
Which encompasses everything we know about the universe. The lambda part means there's dark energy.
This is the astrophysicist version of a standard model.
Correct.
I guess. Okay.
Right. And the CDM part is cold dark matter. It means there's a lot of dark matter in the universe, but there are other things in that description, like the universe is relatively flat, there's a certain number of neutrinos, particles. It's everything we know. It's an inventory of the universe, but 96% of it is still kind of unknown stuff. In fact, very unknown.
That's the dark matter and dark energy combined.
So by the early 2000s, it was recognized, well, we want to understand this more. And so there were folks who were going to measure the radiation left over from the Big Bang, the cosmic microwave background, with a series of satellites, WMAP, Planck, and they were going to very precisely determine the state of the universe as it existed shortly after the Big Bang. So the folks who were measuring the cosmic microwave background got a very beautiful baby picture of the universe that has a lot of fine-grained information about the state of the universe. And
excess radiation, for lack of a better term.
But it's a description of what the early soup of the universe looked like. How much were baryons, normal matter, how much was dark matter, photons.
A really important snapshot of what was going on.
Yeah. And so the great success was the picture they got of the universe was the same model that we were essentially seeing from these more local observations. There's a lot of dark energy, there's a lot of dark matter, everything fit except one thing didn't fit, which is it also predicts how fast the universe should be expanding today. And that number, called the Hubble constant, is something we also can learn by this route that we've been describing, where you measure parallax, and you measure stars, and you measure supernovae, and using that route, you can measure how fast the universe actually is expanding today. It would be like, having a 2-year-old kid, you measure their height, right, and you predict how tall they'll become, and then you measure them when they get to that little height. What if it was off by like a foot or something?
Right.
Say,
You disappoint the kid.
Yeah, you
disappoint.
Right.
He's still in family therapy.
Yeah, I understand. The fact that these two routes from the early or late side of the universe, on the one end, tell us the same rough, more than rough story.
Basic story.
Yeah, they're like doppelganger universes, except one is younger and expanding faster, and one is older and expanding more slowly.
That's the 71 and the 67.
73 and
76.
57.
Explain
Right.
The numerical values.
That's right. And this Hubble tension emerged about 10 years ago.
tension as in the two numbers are not agreeing.
As in the two numbers are not agreeing.
I have to butt in. I'm in graduate school, and we're fighting over whether the Hubble constant
Yeah.
is 50 or 100.
Yeah.
And so you're telling me you're now fighting over whether it's 67 and 72, whatever. And I don't have sympathy for that. You know, my whole time in graduate school, we didn't know the size of the universe by a factor of 2, and you're complaining about a few percent. So now,
Oh my goodness! So now I just gotta go all the way back to
so much more interesting than that was.
midway.
When people were measuring 50 or 100, they were measuring the same thing. They were measuring how fast the universe is expanding here today, often measuring the distance of the same galaxy, the same stars.
When you say here today, you mean within the Milky Way.
No, baby, I
don't have. I told you the length of this table is such and such, and Neil said, no, I get a different answer. The table has one length, right? And so this is something, it's not that profound. None of us is making a mistake. The big difference here is we are measuring opposite ends of the universe, and we are using our story of the universe to connect them. And so disagreeing in this case has the potential to teach us something profound about the universe, whereas disagreeing back then just meant people were making mistakes.
And when you say profound about the universe, it's our understanding of physics and the possibility of physics.
Right? Because how do I go from the early universe to the late universe? I need a function. I need a piece of math to tell me how do I translate from there to there. It's like that kid. You know, they were 2 years old, and they're an adult. How did you guess how tall they would be? Well, you had a growth chart, right? The growth chart is our model of the universe.
It's a formula.
But you know, with the growth chart for a kid,
But it's not precise.
well, you've seen a lot of kids grow up, right? So you have a lot of confidence in the growth chart because they follow that. We only have one universe, and most of it's made of stuff we don't really understand.
Well,
And so,
get another universe then.
well, so I work
a little harder.
Right. Yeah. So, you know, the fact that they disagree, and Neil makes a good point, it's not a big disagreement in absolute sense, it's like 9%, but our measurements have gotten so precise that it's 5 or 6 times the error bar between them.
Oh, I banned the term error bar because no one knows what the hell that means.
Okay.
The uncertainty,
Sure.
the measurement of the uncertainty of each of those two quantities does not leave room for overlap.
That's right.
Okay.
So,
there you go.
from someone who's not as bright as you, let's say, but no, could it be that this means that dark energy is shifting, like sort of like a petulant teenager, like it's calm and steady, and then all of a sudden, you never understood me, Einstein, and it's slamming the door on you, right? Like, is it that possibility? Is that happening?
Yes, I would say that we may be discovering that what we call dark energy is a general phenomenon that happens all the time in the history of the universe. So let me tell you this. We invoke dark energy shortly after the Big Bang in a period called inflation to inflate the universe, okay? We give it the name inflation, but it's dark energy, okay? We have the universe currently accelerating now. That's dark energy.
By the way, it was called inflation because the idea was advanced in the 1970s when we had like 18% inflation.
President Carter. We have something in physics that's important for physics called the Higgs field, which is a field in space that gives rise to mass.
Come on, Daddy.
That is energy, an invisible energy in space. So this is a regular feature now in physics, is to recognize that there are
Come on, baby.
invisible energy fields.
All right, lay down.
In Einstein's theory of gravity, an invisible energy field plus Einstein's theory of gravity automatically has this consequence of giving a push to the universe. And so I would say at this point we are sort of watching the universe to sort of try to learn when episodes like this may occur. Maybe
It did go
maybe
through.
There's only 2. Maybe there's 10.
Is that there's, from my understanding, there's 5 possible reasons for this Hubble tension. Is that the new dark energy theory, or is that the
yes? So there's an early dark energy theory which posits a third episode of dark energy, not inflation. That was the beginning, not the current one. So
is that the turbo boost one, or is it something different?
I don't know about the turbo boost, but it goes by the name early dark energy. But it's the same concept. Is that if you give it kicks somewhere along the way, then using the simple form of the cosmological model to connect 2 endpoints, you're not going to quite get things right.
Doesn't it have to be motivated to manifest itself? And so what would manifest a pulse of dark energy in a place unexpected?
Right. It usually ties to a particle, and it usually ties to some event, some symmetry breaking or something like that. And it becomes very theoretical. I mean, theorists argue that sounds reasonable. That doesn't sound reasonable. To me, they all sound kind of like la 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 la. You know, how many times have you invoked the tooth fairy in this conversation? You know, I've learned that like a close cousin of the tooth fairy is not a new invocation of the tooth fairy. It's just her cousin. You know, so to me, there's a big tooth fairy that we've already been living with for a long time, and these are like revisits of the tooth fairy.
So,
I'm an observer, so this is not, you know, I look at stuff.
is there a way to reconcile this without having to invoke another tooth fairy?
Yes.
You invoke Santa Claus.
Well, first of all, there are a lot of ideas. Better gifts. Yeah. And one way to play the game is to change the way the universe looked before its radiation from the Big Bang. So how do you change the way it looks?
To change our understanding.
Yeah, our understanding of it.
Change it.
Right. Radically acceptance of God. It's a perfect black soup. And so even something as subtle as saying if there was a magnetic field that could start this process of collapsing, like there could be new particles. There could be new particles. That is absolutely another possibility. It rearranges the way energy is distributed in the early universe. And so there are many ideas: electron, mass decaying, interactions between dark matter. See, when physicists start out with the quantum theory background, they have to build a model of what's going on in the universe. So this would be like some new matter going on there, or it could be something latent as dark energy emerges. It's not this cosmological quantity static launch, but it has some kind of
But you have your options in either make the early universe match the dark ages or
exactly
match the other more active one. Do something about it.
That's exactly right. That's exactly right.
Okay, so let's start with the DNA measurements. Those should be pretty easy to verify.
Yeah, so I would say now after 10 years of scrutiny, they're pretty darn good. What I can tell you is, having made a lot of those measurements with the Hubble Space Telescope, along came the James Webb Space Telescope, and it was like, I don't know, it was like riding your first little bike when you were a kid, and then like somebody gives you a 10-speed, and you're like, oh my god, and you're like doing laps around what you did. So I've been doing laps around the work that I've been doing over the last few years, and the images are pristine. The measurements are textbook, but the answer's the same. And so the fact that James Webb is confirming what Hubble is confirming that this is a real problem.
And that deserves, I got to emphasize this, because what he just said is you can make measurements with whatever precision your equipment allows. And then you extract from that an answer in the din of cosmic noise. So it's kind of saying this: if you have better data and you get the same answer, you're good.
That's right. And the signal to noise is 10 times higher for the measurement I'm making with James Webb than it was for Hubble. So if you get a full order of magnitude improvement and nothing changes, that's very compelling.
So for those at home, it's in simplified terms, there was a debate. Well, maybe the math or the way we're doing the math is off, and then the Webb telescope enters the picture and tells you maybe not. So now you have to go to the idea that maybe there's something about the world of cosmology that we're not understanding, or there's something new, or there's new physics.
I'm going to say, or some subtlety, something being lost in translation between the universe we see and how we transform it to these sort of mathematical models. Like, this is the sky, and the telescopes confirm that is the way the sky looks, but perhaps there's some subtlety in the way we translate that into math, or we translate to the beginning of time.
Let me go back 130 years.
Yes.
I think
That's you living in the past. Go ahead. When I was a kid.
Go back then.
Yeah, let's go back.
We were riding high on classical physics. And people said, look, there's not much left to discover in the universe.
Right.
We got this. We got Newton.
Right. It's all done.
We got thermodynamics.
Right.
We got this. And there's just a few clouds on the horizon.
Yeah.
That
the precession of Mercury isn't quite working out.
Yeah, but we'll solve that soon.
It's just another planet out there.
So don't go into physics, because it's about to end. Bada bing. Quantum physics comes up, and special relativity, and general relativity, and all that came with that.
Right.
Is there something lurking, in the dark in the woods, right, that will need a much bigger transformation of our understanding than just meddling in here and there.
Right. The answer is I don't know, but
That's
I
a
do.
good answer. You're a good scientist.
But I do
You know
know.
what? I was hoping for an answer.
I gotta be honest. I do know the process.
I don't want to die soon.
Here's the process.
Yeah.
We're very happy with the model, the science we have. We go out, we predict experiments, and we do things. And then you start to build up these cracks or tensions, little funny things. The precession of Mercury is not following Newton's theory. There's supposed to be an ether out there, and we're supposed to be traveling through it, so the speed of light should be different in different directions. We don't see that. What's going on there? You start to build up these things, and
Just like holding back the water in a dike.
right.
You'd say, you just
Right.
plug this hole.
Right.
Did that work?
Right.
And then it just builds.
Right. And when somebody comes along, let's say Einstein in 1916, right? He comes up with a brilliant reimagination of physics, which first does something very important. It explains your physics already. You can't go and lose it, right? And all these people get started. The first thing that Einstein did after he developed general relativity was he looked back at this precession of Mercury, this problem that its orbit is itself rotating very slowly around the sun, unlike the other planets. And nobody knew why. They thought maybe there was another planet between Mercury and the sun. Einstein
Called
shows
Vulcan.
because it would be hot.
Called Vulcan. And we were perfectly happy to say this is the real benefit.
Yeah.
You can't see it, but it's close to the sun. It's in the fire.
This was not unreasonable because the planet Uranus was not traveling over. It was filled with water. Same with the planet Neptune. Same thing. Like we're makes sense of it. You can't just play the game like you're studying history. You got to predict what's going to happen. Right. Sometimes the planet misbehaves because there's some stuff out there. Right. And sometimes it misbehaves because we have the wrong understanding of physics. And in that case, Einstein showed that his theory would explain Mercury's precession because Mercury was living so close to the sun, it was in what we call a strong gravity regime, where gravity was operating differently than Newton. So, to answer your question, we are collecting these sort of cracks and problems, and sometimes that is
So there's two.
a harbinger of some sort of new revolutionary thing. Sometimes it's the loose thread on a sweater.
Alright, let's correct this.
That annoying thread, and that's fine. Or sometimes it unravels the sweater, and it's hard to say.
Right, but we live in a society where we want answers to everything, right? And to the average person, we want an answer. But what this feels like is like you're assembling the universe using like IKEA instructions. And then you look at the manual, and it's like, it doesn't look like the manual. And you're like, honey, what's this extra part? I don't know, it's dark energy. And why is there another Allen wrench? Like, so you literally...
I think what we're saying is, A, we're not done because everything isn't fitting. And B, we have this wealth of new facilities which are now coming online that really should help us answer these questions. We have the Nancy Grace Roman telescope.
So that's specifically tuned for dark energy. Is that correct?
It's going to be particularly good with dark energy.
Okay, so it's not just another telescope.
Right.
We got smart people figuring we got this problem. Let's
What
design it.
I'm going to ask is what we probably both consider a stupid question. If we don't know what it is other than naming it dark energy, how do we know what to build to
That's
look
a great
like
question.
what it is?
It's a great. So I was actually on this panel called the Decadal Survey that once every decade recommends what to build next. And this is what we thought about, and we recommended this in 2010. And the reason is because it takes us decades to build these things. So what if the science questions change as you're building them? The techniques change. So we designed the telescope to measure the current techniques best that could be done, but also recognize that a telescope that didn't exist was a space-based telescope with a wide field of view. Remember I said earlier in this, you need a wide field of view to observe hundreds of thousands of galaxies, and that operates in the near infrared, which is very difficult to observe in the near infrared from the ground because the sky is very bright.
Behind near infrared.
Near infrared are wavelengths that are redder than red, so longer wavelengths than that.
But it's closer to the visible spectrum than the far infrared.
Got it.
So near and far is stupid words, but we're stuck with them.
Yeah.
So the whole infrared part of the spectrum sits adjacent to the sits adjacent to red, orange, yellow, green, blue, violet. Sits adjacent to that, and those wavelengths that are near, visible colors near, and then far. That's all. Right. It's not deeper than that.
So we both build a telescope. We say, well, today this is what we would want, and we think it'll be great. But also tomorrow, this will be the capability that doesn't exist. So there's a discovery space capability where you say, this has got to show us new things because we've never looked in that window, have never opened that door. So it has its own elements.
Got it. Very important here because that's why build something that only can see what you're looking for or expect. The breadth of those capabilities, that's what advances the field.
But what is it has to feel at times overwhelming to you is it's a constant moving target, right? So you've developed this telescope, but as you just mentioned a minute ago, around that, new discoveries are being made, new equations are being calculated, right? So it must be maddening because there's never a firm like, this is
But
it.
what I find very satisfying, when Neil and I were in graduate school, there were sets of questions about the universe, and those questions have either been answered or have changed to these other ones. So
Exactly. They're not even interesting anymore.
yeah, the story. I mean, we were all like, how much matter is in the universe, and is it going to recollapse? And that isn't even the right
One of our
thing
colleagues
to think about anymore.
wrote a book called Just Three Questions or something, or something, some title such as that. And it was because of that book that I now tell the world when they say, what question do you want to see answered about the universe? And my answer is, it's the question I don't yet know to ask. Because there's a vista that will rise up from research being done now, so that I will then ask a question undreamt of today. That's the question I'm thinking of.
Well, in our field of cosmology, right, used to jokingly, he said that we only had 2.5 facts in cosmology. So we have so much more information and such a great used to be considered closer to philosophy than physics. And now
there's hardly any data.
Right.
Yeah.
We knew the universe was expanding. We knew there was radiation left over from the Big Bang. We knew the sky was dark at night. That was fun.
There's several people thinking about this tension.
Yes.
You're not the lone wolf in this. So, are you converging at any point?
So we have a fleet of new observatories coming online. We have the Nancy Grace Roman telescope built by NASA to launch next year, which will study dark energy. We have the Vera Rubin telescope. She was the discoverer of dark matter, one of them. And that is a massive ground-based telescope that will cover most of the sky every 3 or 4 days.
Yeah, I don't see that one working.
A million supernovae, that one is already working. And
you contradict me all the time.
Online, it's discovered thousands of asteroids that we're not even counting.
Well, no one told me. We have new CMB experiments, the Simons Observatory. We have LIGO, which is still getting up and going and has great capability. We expect new results from Gaia. So there are a lot of facilities that really are well poised to give us answers.
So, but is there like a fight out there? Is there a cage match among you guys?
Right. So I would say 5 or 10 years ago, the folks from the CFP particularly were like, well, you local people are probably wrong because it used to be 50 or 100, and that seems like hard stuff. Okay. And maybe some of us were like, blank looks really good, but gee, I really would like some confirmation of that. So along came new facilities that allowed people to check the work. Okay. So from the cosmic microwave background, we've had these great high-resolution CMB experiments like ACT and SPT. One's Princeton mostly, one is more at Chicago. And they have replicated the cosmic microwave background measurements. Actually, they've even pushed the Hubble constant lower, not 67, but 66.
Are these observatories in Antarctica?
Yeah, one's in the South Pole,
right,
the South Pole telescope, and the other one's in the Atacama in Chile.
Okay.
And so you need very little water.
It's one of the driest places on Earth, right? The Atacama. As is Antarctica. It's one of the driest places on Earth.
And then nearby, we have seen the James Webb Space Telescope replicate the measurements, which was absolutely critical. We've seen other techniques developed that have cross-checked the measurements. And I just came back from something called the distance network. So not the distance ladder, but how do we combine all of these different measures simultaneously, taking into account their covariance. And what we've learned
is now a great name for that, because it all has to work together.
Correct. Yeah. It's not just a ladder anymore, but it's like, but what if I have this information and this information? Well, this information was calibrated the same way as this, but it gives me a unique measure to something else.
It reminds me of this stupid comic where the Transcontinental Railroad and the Golden Spike, the last spike, and the railroads come, and the tracks don't you.
Well, that is the problem. Hey, they're down there. I told you we were wrong. So we've seen a lot of cross-checking, and this problem is not going away. It's been getting stronger and stronger. So I think we have to think hard about what it means.
Has your position altered at all? Or at one point you said, I think the universe is giving us a lesson in cosmic humility. It doesn't seem to be following the manual we had.
Yeah.
We can rule out a measurement error as a cause of the public tension with very high confidence.
Yes.
There's people out there that would sort of say, perhaps not. And then,
Well, you're quoting him from some other program. If we had him here,
Yeah.
we could have quoted
he doesn't know what he was. He doesn't have the time. He doesn't know what he said.
Let me define error. Do you ever watch baseball?
Oh, yeah.
You know baseball?
Yeah.
So error in America. What do you,
Yeah.
error
You are.
in
There's a
baseball.
quarterback, there's a wide receiver. Yeah.
So I like baseball that they define an error as there was something that was supposed to be done. You know, you're supposed to field the ground ball, and you messed up, right? And it didn't happen, and they score that as an error, okay? But, you know, making some extraordinary play like climbing the wall and stealing a home run and not doing that is not an error, okay? So in our parlance, I would say we are convinced after 10 years of scrutiny that we're not making an error in the baseball sense, that everybody
In terms of measurements.
everybody appears to be following the manual carefully. Everybody appears to be measuring what they said they're measured. The data is public. This is very important. Unlike back in the 50 or 100 days, half the battle was people had their secret photographic plates in their drawer. And so you'd have a battle, and you were like,
Not the draws.
yeah,
In the drawer.
Depends where he had freaks. He's walking around with a piece of metal in his pocket. You got stuff in your drawer.
So what's important is all the data that I talk about is in a public archive. So I say this star is this bright. It's right there.
I'm sorry, back up in the 50
So I can verify that, and I don't have to think that I'm going to just take his
No,
word.
I understand, but
At back end of the day, what do you mean there was secretly you were not publicly
literally the guy, right? You would go to the 100-inch telescope, you put in a photographic plate, you take your deep exposure, and it was your plate. You took it home to your laboratory, and you told people what it said.
Yes.
But
there were lectures about it and so forth.
No one else had access to your data.
Right.
Now everything is digital,
Right.
and is
The point being, you've got a lot of people cross-checking,
So
checking,
this
and
is a democratization of science, very important facility. And so what I will say is, in the past, when errors are made, errors absolutely happen in baseball.
I definitely need to make the
Our
bubble
community is
bigger.
so good at jumping on those, right? But I would say within weeks or months, that is found. When something lasts 10 years, when the data was public, when people could scrutinize it, then those become the things that are real things. So
and you want to also watch out for whether there's groupthink. And if multiple teams who are otherwise competitors find agreement in what your measurements are, that's a good place to be.
like there were two groups in the last couple of weeks that were using JWST and this method called tip of the red giant branch, and they got 74 and 75. They're unrelated to the more traditional groups that we're working in. So the more you see these groups that are
So
independent,
the Hubble, the value of the Hubble concept, yeah, that's
Does the 74, 75 versus vis-a-vis 72, 70, does that trouble you?
no, it's closer to the 60.
no, right. I mean, it's look, the full range of measurements people make locally is about 70 to 75. So that's normal. That's kind of a bell curve distribution. So people, you know, the middle is probably around 73, but some people get 75 and some get 70. But the point is, why are that? Yeah,
Any
right.
grand
The question is, why is everybody getting something higher than the early universe at 66 or 67? And that, I don't see how that happens by chance.
Well, there is this theorist, Thomas Burke, and it sort of has another explanation for all of this. And I want to get your thoughts on it.
So he is a theorist. He's not making measurements. And he has had a theory for a long time that when we look out in space, we use this approximation to say everything's smooth-ish, okay? And we can use Einstein's theory of relativity as though if I have a certain amount of matter, it's kind of uniformly distributed in space. In reality, space is quite chunky. And he is saying that the mathematics of calculating Einstein's general relativity through chunky space won't be the same as calculating through the same amount of matter smoothly distributed. And I know a lot of people disagree with him. He's sort of on an island about this. They're devilishly difficult calculations to do do analytically. So people have done it numerically with computers. You just kind of trace the particle. You kind of go through all this. People who do that say they don't get what he gets this way. But I'm open to it. Look, I mean, if things are not fitting, you have to be open to a lot of possibilities.
Yeah, the more things don't fit, and the longer you're in that state, the kind of more, you know, you say, oh, who's got?
What do you got?
Yeah, what do you got?
I mean, like, for example, when we discovered dark energy, there was something called the age crisis, where there were stars that appeared to be older than the age of the universe, and that was a problem. And the solution to it was actually dark energy, because when we said the age of the universe, we were assuming that the expansion had been slowing down the whole time. And so when we said how long ago was everything on top of everything, we would get a young age for the universe, 10, 12 billion years. Once you realize, no, the rate we have right now is a fast rate. That's not the average expansion rate of the universe. Now let's do the proper calculation. It pushed the universe to be over 13, 14, 15 billion years.
Adam, I don't know if you're a betting man, but what would you bet would be the solution to this?
I wouldn't bet. And the reason is because
That's not fun.
I like to think of myself as part of the crew of umpires in this game, right? So we're calling the balls and strikes. We're saying, oh, this thing's traveling this fast. This is so far away.
You can't fix the game a little bit.
I mean, you know, that would be the problem.
Kids with little feet.
If you're a umpire, you can
I mean, I will say, this is an unusual game. This is not
Figure out the scales.
Yeah.
Not the election.
And so, my bet is that there's something interesting going on. But what it specifically is, I don't know.
Okay.
But it's like we've got two thermometers. You're taking my temperature. One says it's 98.6, and the other says I'm at a boiling point. And you're the doctor going,
I'm willing to go and say that. You're sick. You would be a terrible doctor.
One of the more fascinating dimensions of the moving frontier of science is when you don't have an answer to questions that have been posed, or you have data you can't make sense out of it based on our understanding of how things should be or even could be. Then you gotta scratch your head and say, do I have to give up some prior expectations, some prior assumptions that went into this understanding of the universe, because the puzzle pieces don't fit? Until Copernicus, our understanding of the world, the universe, had Earth in the center, and how does he explain planets going forward and backwards in the night sky? Forward in the retrograde and forward again. We got that. We got that explained. And then Copernicus comes along and says, I got a new idea. Earth is not in the center. That's pretty serious. The sun is moving.
Come on, get up here.
And we're all going the same direction around the sun. And you say, okay, the math is a little simpler, but the idea doesn't sit right. The epicycle thing, that's kind of matched with the data. And so now, what they do, they say, let's check the model. They check the model. And it turns out the planetary orbits were not as precisely predicted as they were for the epicycles. You can throw in the whole thing because epicycles are giving better predictions than a sun-centered universe. Just throw it all away. Or maybe there's a adjustment on the edges of this. Maybe the idea that the sun in the middle is what's fundamental. And Copernicus assumed that orbits were perfect circles. Why wouldn't they be? It's the heavens. It's where God is, and a circle is a perfect shape. The orbit, discovered by Johannes Kepler 50 years later, he shows that they're ellipses. You keep the sun in the middle, put the planets on elliptical orbits, you perfectly predict and understand the motions of the planets. We're in this interesting precipice in cosmology where, the Big Bang is pretty secure. In spite of what newspaper headlines with clickbait might have been implying over the last couple of years. Big Bang in trouble, man. I think it's pretty secure. If I'm betting we're going to have the Big Bang throughout this. But we're going to have to understand something else about how we interpret the early universe, how we're understanding the expansion of the modern universe. it's a piece of understanding that'll make the puzzle pieces of cosmology come together. In a resurrection of the challenge that confronted Copernicus, we kept the sun in the middle, and we found out what else needed adjustment. And at each turn of those discoveries, we had a deeper understanding of the operations of nature. And that's what makes us all so beautiful. That is a cosmic perspective. Adam, it's been a delight to have you come through town. I don't know how often you get through New York. I know there's a lot of good, fertile brain activity in the
My
Baltimore.
sister lives here.
Oh,
Shout out.
there's an excuse.
Shout out to her.
Shout out to your sister. And let that be an excuse we can exploit going forward to get you back here and catch up on whatever delays take them.
Can I have your prize when I show sometime? I'll give it back. Yeah, fine. Is he here? Please don't do me.
Dude, thanks for
Absolutely. So fascinating. I learned a lot and honored everything. Very cool. Yeah, great.
This has been Star Talk. Neil deGrasse Tyson here, your personal astrophysicist. As always, keep looking up.
Alright, let's change that. Do some.
Yo, what's up, guys? Chase the Bro here.
Chase the Bro.
Welcome back to another Elden Ring DLC build video. Today we're going to be using a build focused entirely around the Claymore. Definitely one of the most classic weapons throughout the Souls games. The Claymore is a great sword that has one of my favorite movesets because both its crouch attack and its heavy attack are actually a piercing type attack, so you can really enhance the damage on this weapon by using your talisman. The Claymore's moveset is also pretty ideal for roll catching, so a lot of Ashes of War that have great distance, like the piercing fang, are going to benefit its moveset greatly. Another good choice of Ash of War is the Stormcaller for the Claymore, since it kind of lacks in horizontal attacks. You could one-hand it, but then you lose the hyper armor that the two-handed moveset gives you. You also have much better damage output when two-handing your weapon on a strength build like I have here, which leads us to the two-handed sword talisman. This is going to buff your two-handed damage output by 10%, so I definitely recommend using it. The other two talismans are really up to you. These are kind of my staples. I like having decent poise, especially when I'm using a great sword or any hyper armor weapon. And the Urge Favorite Plus C gives you HP, stamina, and equip load, so you can't really go wrong with that. If you wanted heavier armor, you could throw on the Greater Arsenal, but I do like the HP and stamina that it gives. Moving on to the stats, this is a pure strength build. I do have 18 dex because I like being able to use my great bows, but if you guys just want to use the Claymore, you really only need 13. I always get asked what my favorite weapon in Elden Ring is, and I think the Claymore still holds that title. It's by no means the most overpowered or anything. Very balanced weapon. Really good for roll catches. I just have a lot of time spent on this type of weapon. I really enjoy its moveset. That's really everything there is to say about the build, though. Hope you guys enjoy the invasions. The Academy of Rhea Lucaria. What do we got going on here? Hello there, boys. Sea turtles. Hello. Oh. Hello, this is a rude entrance. Hello. Hey there, booty. Why did you not give me the booty there? That was rude and inconsiderate. I really wanted you to avoid that, but it is what it is. We don't have something to strike. I think I want Billy first. Seems fun to go after. Perfect. Billy on. Also, what is that guy's build? Just saying. We got Flaming Strike, but like a bunch of wizardry. 360. Perfect. Well, I don't understand. Flaming Strike with wizardry abilities is a weird mix. I get value out of your sword. It's got hurt. The trade, dude. Maybe we go sword dance to finish this. Sea turtle, come here. Oh, you got my bubble tear. Honestly, I'm surprised that I didn't trade him there. An R2. I think I'm gonna stick with piercing fang. Yeah. I need a gap closer. It's kind of making me come to him. And I'm trying to punish it. Fun fight, boys. Interesting. Volcano Manor. Nice. I heard somebody attacking this. Wait. Warhead. Oh my god. I see rivers of blood with the pot helm. Oh, they're camping that, huh? These guys almost got me hit, by the way. Let me just buff them up, though, in their honor. So they want to play a game. The game of camping. Camp that, buddy. I think I can get up. Can I get up a different direction? I don't really know. I'm gonna take the chance and go up the ladder, even if the host is camping it. He didn't really have a big burst Ash of War. Wait, I think the Phantom call. I might have. I think I did. I'm going in. 2. And 1 is a Bloodhound Bomb. Hello there, sir. Dragon, no. I had to stop that. There's no other choice. I'm coming for you, Phantom. No, hey. It's that. So you got the counterattack damage. Unfortunately for him. Do I parry shield? Yeah, let's go. Bonk. Come here. Come here, my friend. I blocked that. I wanted him to go for the follow-up. Why would you not go for the follow-up? You're silly. I believe in you. Goodbye, Mom. I'll be seeing you, man. Kind of a good bait. Base can be very common darts. Let's say, like hard spot to shield repair and go back to your weapon. But I don't see it much. Maybe that's a good way to fake people out if you're running 2 shields. They haven't seen it much here. The River Mouth Cave. Oh boy. Hey guys. Those look like some scary weapons to have, I have to say. How's it going? Shall we do Great Battle? I know I seen the scary gold weapon. Luckily, I think I was stunned by the host. I do have to stay out of range of that Ash Board. It's mildly terrifying. I thought you go for the follow-up. So we have 2 different gold weapons, huh? We've got a lot of weapons going on here, actually. Stay close to me, boys. It's okay. I know no one really used to think we're doing this, but they can do it. Oh, why would you do that? Odd choice. I'm staying. Oh, definitely saved his life right there.
What the hell? How'd you get up here?
Those chimes played Davey. It was not. Woo. Oh, that might be bad. No, we're good. I didn't mean to do that. I still haven't happened to this day where, like, the 2-handing option hits me hits. You're not safe at that distance. Piercing Fang exists. Yes, yes. I'll have to roll with that. You know, no one really does the follow-up. I can appreciate that. Oh, that roll catch combo is probably my favorite. Out of all the things you can run in Claymore. I love Stormcaller too, though. Don't get me wrong, they're all very good, but that's just so satisfying. The Greyside Plain, but it's so rainy. And I get one of the worst spawns because they're not actually near me. They're at the boss, so we're gonna teleport. Oh, what's going on here, boys? We have a duo. Oh, and a teammate, Red. Wow. Very rare. Hello. How's it going? Doing this. Chill out, sir. Chill out. That's a wall. Kelly's kind of panicking. I say kind of. Very much so panicking. I think he's gonna do like a retaliatory attack. There we go. Those just die. That's dishonest. The red died to a Billy? That's rare. Oh, this thing's in my way. Red, you died to Billy! You'll never be able to live this down. It's so sad. Now you left me dealing with double Billy. You know what? They're gonna get aggressive. I feel like Stormcaller can work here. I want to frostbite him so bad. Let's do the Ash of Warren for sure. Oh, that was like a hair away from hitting. Right about that. Ooh, very high latency with the Phantom. Let's get this going. The teammate's like right behind me. I don't see him at all, but I actually have to delay that with him. Because he takes the hit ability, so it doesn't look as clean. Okay. Oh god, he took that hit so late. Not gonna lie, I didn't think I was gonna get a hit there. I knew they both attack again though. What hit me? Which one of you? Must be the super high latency guy. Yeah, okay. I was gonna say, it wasn't even on my screen, that's how I know it's really high latency. Billy? Wow, he prioritized hitting me over healing himself. Okay, maybe it was actually a Blasphemous Billy host version, because did you see how late he took my running attack? Okay, now I'm like thinking, maybe Piercing Fang isn't the play against this guy then. It's a really tough call. It's like, it's a good gap closer, but when they're not getting stunned when they should be, there's a problem. Because then I can't set up my attacks, you know? And he's also hitting me from the other side of the planet. Okay, this invokes this. For sure. Hey man, I'm sorry, you shouldn't have been hitting me when you've been hitting me. That was just crazy, to be honest. I gotta look back at that last one that hit me. I was like a century away from the guy. Alright. Crumbling Ferrum Azula with large.Track, and they're definitely fighting the dragon. Well, you know, since I'm up here anyway, I may as well just go for some fun bow shots. I see no downside. Are you teabagging the dragon, sir? Are you joking? They're making a run for it. He's coming here. Prediction! Now he's gonna go over here. Now he's near light, so he's only gonna run up and right towards here. Or in. Taking all the fire of the team. Wow, dead and gravity kill. That's pain, man. I'll definitely take it though. I love getting to use my bow. I threw on some regen because I lost a little bit of health taking off those rings. They're over here, bullying the PV. Hey guys, do you like a pot downtown? Kind of funny to hit. Ooh, good dodge. They want me. Hey boys, bring your spear this way. Are you brave enough to cross the threshold? He is actually, but he didn't get knocked off. Oh, hey man. Honestly, what is this? It's like, here comes the friend, he's gonna try and protect me. I kinda did, actually, I'm not gonna lie. I thought I had Stormcaller on this. I was holding Piercing Fang most. Ooh, I lacked the length needed. So he's a madness build with bleed, huh? Seems like it. Crossbot! Push! Dodged it though. By the way, ooh, giant swing tape. Yeah, I thought he was using something else. Oh my god! No, I'm not. I don't know where the friend is. There's also a blue somewhere, so I have to take that into consideration. Gotta save him. You did kind of. The power of friendship. Why would you take that trade on 1 HP, man? I feel like people get way too used to fighting in groups that they don't notice their health, even though that host was like pretty adept. He knew what he was doing. Summoning another cooperator. You love to see it. Hello there, guys. Oh my god, it's literally a full goat. Hey man, I don't see that much at all. Booty. More in this, and I take a hefty hit for it. Oh hey, whoa whoa whoa. Listen, me and the full goat, we were having a bro off, okay? And you ruined it. Dishonest Vare enjoyer. What's up, man? What are you doing? I want to chill them. I want to chill out. I want to take a fall. Just a brief fall, you know. It's fine. Okay, now he's chilled. Now we can go for the long range punch. That was the fact that he kept rolling. You know, it worked out for him, but it is funny. Now he wants to return the favor to me. He's got his whole gang here. Ugh. Keep dodging. He's like, yeah, he's gonna keep doing the sword. It is what it is. Long range spell. Yo. That's right, I dodged your dishonest wizardry. And I leave it to the Vare enjoyer to sneak. That's his tradition. Oh, we got some wizardry coming our way. I have to run by Sir Bonk. I just see him in the corner. Okay, we get some cover from the wizard, otherwise it's too much pressure. Okay, so I may have to whittle down that wizard, honestly. He's just constantly casting that. I don't know how much FP he has, but I've been dodging this a while. Hey, Rivers of Blood Enjoyer. You're kind of isolated here. You're not used to it, I know. So you're used to having your friends here. But it's bad to be alone with you, Mr. Wizard. Mr. Bleed. He got very aggressive for me. Oh boy. And he aggroed the dragon. Did those just die? No. Took a lot of damage though, but now we can go for this. Hey Wizard, what's up? Let me get some FP back and then I'm good. Ready? Hit you if you got it alone. Stop, Wizard. I guess to stop. The aggression's forever when I'm alone with you. There's no pack to save you, Sir Phantom. Now, where's the host exactly? Oh, aggroing the dragon. Running in odd directions. Hey, Sir Hammer, what's up? Were you trying to take those down on your own? You're a warrior, aren't you? Hey, man. Everyone. Good, that'll save us from getting hit by the dragon. I'm gonna heal this in case the dragon does hit me. Oh my god. Oh, and you know what? I think my heal is the reason I lived. Well, that was a dangerous fight, boys. The Cave of the Forlorn. Hey, wizard, are you bowing at me from above? Wait, what? Oops. I meant to eat the crab meat, but you know what? They're pretty nice. You want to do great battle, wizard? Or shall I fight your phantom? Ooh, reverse blades, huh? Hey, man. How's it going? That was rude. I was waiting for you. I'll take it, though. You can have an advantage lead, my friend. I love the frost tornado. So good. Well, hello there, other fans. What are we doing, my friend? Ooh, the axe. R2. I'll take these trades. I don't think he was looking at his health bar. There's no way he would have continued if he was, right? Hey, man. What's up? What do you got? That's why? With Waves of Darkness, I'm betting, right? That's gonna be my bet. No, actually. I think Trumplet. Hey, I forgot the other one. I only see the old one, to be honest. I like how he just sits and crouch. Poke. Into... Hey, he didn't fall for it. He loves the poke, though. Let's get our Ash buff. What do we want? Sword Dance? R2. Red poke. R2. Oh, front flip and back flip. I like it. Oh. We both ended with a thrust. One fight, man. Now the Claymore takes that one, though. Is a mayonnaise an instrument? Seems like they went up the elevator, but they didn't fight any of the enemies here. Okay. They also haven't gone into the boss fight yet, which tells me they may be waiting for me. Oh, hello there, sir. They were indeed waiting for me. That's a big bonk stick you got going on there. Ooh, I couldn't take that. Wait. I'm going up with you? Oh, it's just me and you. You left your host behind, and you probably just died. Oh, no, you didn't. Damn, okay. Not riding an elevator, I guess. Let's get buffed up. I kind of want to send the elevator up top without them realizing it, you know? It seems like they want to fight them, which is good. I'll lead them away from the elevator, and then we'll go send it up. No, I knew it. He's cowardly. Oh, hey, we brought a friend up here. Ooh. It might have some length. It is known. Oh, I almost got a 2-for-1 right there. Sword Dance? Wait, did the enemy send it down? Because I didn't. Amazing. He's running for his life. Please let me off this death trap. Okay, we're going to send it up again then. Just because I don't want to have to deal with him running away. Yeah, there we go. Perfect. Alright, well, we know these are runners, so Piercing Fang is definitely the best choice. Come here, mayonnaise. Bonk. Oh, didn't want that grab. Honestly, being behind someone sometimes is a problem. You gotta stay like a little to the left. But then, you can't always catch up with them. Oh. Oh. Well, fun run, mayonnaise. I needed some cardio. The Shadow Key District, and we have Mamba. Oh, hello there, boys. What's up? What are we doing? Let me get some defense buffs. Thank you. Very kind, very kind. Oh, Billy, listen. Ooh, we're gonna keep parries on us for Billy specifically. Oh, didn't get the grab. This host, he's gonna die. So we don't want that to happen. There we go. This. Billy parry. Oh. Billy parry number playing hero roles. I feel like you're gonna go for your attack eventually. I think doing that and then not turning yours. I think it's a bad call. Hey man. Let's say we're gonna do it again. I feel like we are. Oh. Oh, that's so satisfying to parry. Is he alive? Oh. Well then random wrong box. First. With your host attacking me. That makes it so much funnier. This guy just loves attacking. By the way, the heavy attack does so good. Did you see that? It traded. Let's make this guy chill. There you go, man. Beautiful. Look at the mist. It's pretty. Surprise attack from the mist. Charge it. Oh, no. Okay. You know, what if we went full trade? There's so many of them. You have to get the most out of it. He loves just swinging that sword. You know, I never see anybody use the graphical blade. It's good for its ash. It's buffs you overall, but it's not the best to fight with. Alright, that wraps up all the battles that I have for you guys for today using the Claymore. I hope everybody enjoyed the battles. Once again, there's my stats on the right. Just a pure strength build, the armor that I wore, the talismans I used throughout the invasions, and of course, all the different Claymore ash support that I use. As always, if you guys have any recommendations for any builds, weapons, or theme videos, feel free to comment below. I do appreciate all the input that you guys give. Until the next video, this is goodbye. I will see you all next time. Thanks so much for watching. Goodbye. Goodbye.
The subject tonight is superhero science.
You go. Flash can run through walls. Quantum tunneling is a real phenomenon, and it happens all the time. But Flash is supposed to be so good at this that he can vibrate his entire body and go right through it to get to the other side.
So Superman, everything about him is super.
Yes.
And it got me thinking. He does eat food. You've seen him eat.
Uh-oh.
Here we go. So it occurred to me that this is another tool Superman would have in crime fighting.
Dr. Manhattan was created in the Watchmen universe by Alan Moore in the 1980s. But he's essentially blue, and he doesn't wear clothes.
I gotta tell you, it was pretty good naked. Welcome. This is a live recording of the Star Talk podcast here in East Hampton in Guildhall. Thanks for coming out on a Sunday night. Tonight, you probably came and didn't know what the subject would be. Is that correct? So, I feel the love. It comes no matter what. That's a good fact. The subject tonight is superhero science. Ooh. And we got the expertise for that because we found it. But let me introduce the rest of our panel up here. First of all, Gary O'Reilly. Gary, come on out. Gary. Thank you. Gary, former soccer pro. The wiki page on this. Actually, we got it again? I gotta say it every time. A former soccer pro in the UK, a soccer announcer, and he's with us for this branch of Star Talk that we call Special Edition, which focuses on how science and technology come together to enhance, augment, or adjust human performance. And when we speak of the science of superheroes, some of that might be just one day in terms of what may lie in our future. So, who else we have? We have Chuck Nice. Come on out, Chuck Nice. Yes. Yeah, this is a stage on the runway. That was me being a superhero. This is stuff. I'm out. I'm sorry. Mars is a superhero. He's an actor, a professional comedian, and my long-term co-host for the series. I love him because he's scientifically literate and cute. They'll be the judge of that. Okay. So we have an empty seat there because that's our special guest this evening. I don't know if you know this. Perhaps you attended this evening because you have a little bit of geek in you. But there's something you should know, that no matter how geeky you think you are, there's someone geekier than you. Okay? So I carry strong street cred in the geekiverse. But our guest tonight is geekier than I am. Please welcome my friend and colleague, Dr. Charles Bloom. Charles, come on out. Charles, a professor of astrophysics at the College of Staten Island in the City University of New York, and he's also recently the author. Check this out. Here's the title. Oh my gosh, the Handy Quantum Physics Answer Book. Is that geeky enough for you? Because you know you have these burning quantum questions that must be answered. So, Charles, welcome to the show.
Thank you.
This is not your first rodeo with us.
That's right.
But anytime we want to reach out to the geekdom, the geek universe, you are prime for that.
I don't know what to say.
All right.
Thank you.
I hope not later on, because we need you to stay. So Gary, conceived this show. So why don't you set it up?
Yeah, well, as you said, we always try to consider the human condition, and superhero movies aren't strictly science fiction, but they kind of are. And they've been long part of our pop culture. We've idolized them, we've scrutinized them, and we've wondered. And they've been riding the wave of quantum theory, that golden age of quantum theory. And tonight we'll kind of explore the pillars of science fiction and superhero science. Let's start off with the classics, Mara. We'll come to you, Charles.
Okay.
It's the OG, Superman, right? The damsel, once again.
But just to be clear, I think go back. Oh, okay. We were that far back. Legendary storytelling. Is Hercules any different to that? Superman is our version of Hercules.
Every culture has their own Superman.
Next from.
So, as I was saying, Superman's origin is from comic books. Yeah, Hercules was not in a comic book first.
Oh, I thought it was in a comic book.
Yeah. It's chiseled into stone.
Right. Got that settled.
Yeah.
So, as I was saying, the damsel's been pushed off the balcony on the 32nd floor again. She's hurtling. That's her. And so then he comes in, he swoops in, and he grabs her. But from a physics perspective, Charles,
well, the problem is, of course, if Superman is a man of steel, and the thing is coming down, right, and you're coming up with the steel, it's like hitting the concrete ground, right? So the poor damsel in distress would be quite rescued, but also quite squished.
So quite dead. Basically, he kills her.
Yeah, she's a bug on a windshield. Well, the problem is, of course, that moment of impact, right? And so it has been hypothesized that Superman actually has a way to absorb motion. In other words, the momentum and the energy, he actually not only can get there and stop the person from hitting the ground, but also can absorb the impact so that he himself is unharmed, but the person who is falling is also unharmed. It's because it's as if they had fallen and just stopped in midair.
So it's like airbags.
Like airbags.
Okay, so but that's the Superman flying up. He wouldn't have to do that. He could just wait until they fall. But typically, you see Superman flying horizontally. So that's quite a calculation to fly horizontally and perfectly intersect.
Yes.
When the person is where you are.
Yes, Superman's brain has to be at least as good as your average cleaner.
Right. So Superman, he's everything about him is super.
Yes.
Right. And well, I wondered. We actually got a question. A branch of our podcast that goes online are questions open to the public, our fan base. And one of them just simply asked, would Superman's physiology be the same as humans, even if he's sort of steel on the outside? And it got me thinking, if he's got super everything, but he does eat food. We've seen him eat, right? So the food digested in some super way. Okay, so what would that mean? And then I thought, so everything that's going on would happen in a super way in Superman. So you would digest faster, it goes into your intestines, and a lot of the actions in your lower intestine, where the microbial action happens anaerobically. Here we go. And gases,
Methane, sulfur compound.
yeah, sulfur. Yeah, Super Taco Tuesday. Yeah, sulfide. This is smell of rotten eggs. Methane.
That's just asking to be made into a large sculpture. I can do with, that looks like the Sphinx. I could sculpt a large Sphinx.
Yeah, that thing. I mean,
Make some pyramids. Got some sulfur mines down here. Looks like a big sulfur field.
Right? And methane, of course, is highly flammable.
Yes.
And in cities, it's the gas of choice for your stove if you still have a gas stove. Suburbs tend to have propane. These are varieties of flammable gases that you get from crude oil. So methane is flammable.
Yeah.
So it occurred to me that this is another tool Superman would have in crime fighting. Because he would just sort of load it up, okay? And put it in the pants and just lift it out. And he's got vision, laser vision, X-ray vision. Then he we get the X-ray jet. All right, he got
So there's a desert well there.
And so it would be a different kind of flame of a terrible death for those villains.
Some more salt.
It's physiological.
Yeah.
It works. Yeah.
You could never sneak up on Superman because there'd be a rear guard defense.
Oh, yes. Get close, get hit. Eventually, we'll be fine. Yes.
The only problem with this very peaceful is that when Superman came to be from the top, he did not have gut bacteria yet. He was still like pre-colonized. Okay, so any gut bacteria he has achieved from eating here on Earth has come from Earth. So this is a fascinating question, which I would love to hear your opinions. Okay, does Superman have super gut bacteria or just ordinary? In which case, right? If he has super digestion, which would be great. It might be so good as to eliminate all gases. In which case, Superman passes.
Alright, so Superman has X-ray vision. Alright. Right? There's a scene in one of the movies where Lois Lane walks behind a lantern. The CFO, if you have X-ray vision, it refers to
A large ocean.
and I don't know why would you stand behind a lantern? Because everyone knows that X-rays. And then she stepped down and says, hey,
That building up early.
X-rays should not be able to color clothing.
That's right.
That's right.
Yeah, but you're not accepting color glasses.
can stay in the X-ray world. As long as it's been N-ray or something. There have been some other things that he had. When you say X-ray, that stick with no.
But what you look it up, right? Superman was X, right, vision, and then Apollo is infrared. Going up the infrared. See? They didn't think of that. Well, if you think about it, that's right. Yeah. Y rays, Z rays, X rays, yeah, radio waves, yeah. Well,
How does you?
They go right through our bodies, and they go through different materials and wind up with different colors. For example, our bones look different from our soft tissues and things like that. X-ray telescopes that we're familiar with, the genre X-ray observatory, XMM Newton, things like that, they can look at the X-rays. But X-rays are also different colors. Some of them are hard X-rays, some of them are soft X-rays. And in the same way that we can take pictures in red, green, and blue and mix them together, Superman could be able to detect or even emit X-rays and come back and forth in these different bands, and thus create a three-color image.
Undeveloped feature he could have expressed.
That's right. This is an evolutionary superiority that he has, but instead of us having rod and cone cells, he has some sort of X-ray rod and cone cells.
We are limited to the visible spectrum, red, orange, yellow, green, blue, violet.
Yes.
You've got X-rays, there's a whole accessible part of the electromagnetic spectrum.
That's right.
And all he does is just see the walls.
Yes.
But it's way more
highly underdeveloped.
Honest, man. He probably could do all that, but he just doesn't want to let you know unless you're asking him about his opinions. Now, this thing about his gut.
Yes.
We know Superman came here as an infant.
Yes.
So I once got a phone call from DC Comics. You didn't trust the bus I work in. Right here. Next to you. That doesn't know anything else about me. That's where I was. And 10, 15 years ago, I had a phone call. No, it's our business. Yeah. This is DC Comics. We have a new comic book we're illustrating. So we want to know if we can illustrate and visiting the 8th planetary. Do you give permission? Yeah, I would say no to that, right? So I said, what's up? They said, oh, Superman, in this story that we're telling, is going to come to the planetary to use our special tools for visualization and telescope to see the destruction of Krypton, which is finally reaching Earth. And I said, oh, that's good. That's good. But I had to dig in. And I said, all right, Superman was launched Lotus style in a basket as an infant, arrived on Earth in that same basket as an infant. And anyone who knows infants knows that a month, 2 months, knows the difference between the baby, 2 months old, and 3 months old. This baby did not age. So there's only 2 ways. I'm telling this guy on the phone. Only 2 ways, and he's taking notes, right? He didn't argue with anything I was telling him. I said 2 ways you could have gotten. If you travel, because they're aliens, so they can do what they want. If you travel the speed of light to Earth, he would not age relative to Earth. Because that's Einstein's relativity. However, if he's traveling the speed of light, so is the destruction of Krypton. That light, those light beams from the destruction be right alongside, and he lands on Earth. You see Krypton destroyed. He couldn't show up later and then observe the event. So you can't be the speed of light. It was at this point the gentleman from DC Comics knew that he had made a mistake. So then I said, the only way you get him here and have all his work is through a wormhole. Okay? A wormhole. If you put him through a wormhole, he gets here instantly, long before the light beam. Okay, that's very cool, man. Yeah, okay? So to be honest, that's really cool. Okay, so now, hang on. So then I said, yeah, hang on. How old is Superman? And he said, he's eternally in his late 20s. So I said, okay, I can find you a star that's like 26, 27 light years away, and I can make sure it's red, because there are plenty of red stars in the galaxy, because the Krypton star is red. Right. And we can make that the star he came from. I can find an actual star. He said, And they said, we'll take this one. Well, I said, why? Oh, because it's in the constellation Corvus, one of the 88 constellations of the night sky. Corvus is a crow. And I said, well, why? They said, oh, the mascot of Smallville High is the crow. I said, oh, that's good. Whoa. So there it is. It's now Superman canon, this conversation. And so, yeah, they drew him, and then they called me back and said, do you mind if we have him meet you? And I said, yeah, let's do it, okay? So in this comic, I am meeting Superman. And there's a tender moment because he sees the destruction of Krypton.
Stop.
And he's sad. He's crying super tears. Yes, he's just sad. And I realized at that moment I'd never seen Superman emotionally sad. Right. And angry, sure, but not just genuinely sad. Right. And so I know a little more than usual about how Superman got here because of that conversation. So here's the takeaway, people. Neil deGrasse Tyson made Superman cry. Yeah, you did. Okay, so now they didn't show him opening up a wormhole. They just sent him here. Right. That. Yeah.
Okay, so you touched on wormholes.
Yeah.
Faster than light travel.
Yeah.
I think everybody in the room, me included, wants to know what are we going to be traveling by in the future if we actually get to do that? Is it going to be a warp drive? Is it going to be a wormhole? Is it going to be a transporter? What is it going to be?
You know, I was hanging out with William Shatner. As you do. Yeah. Who doesn't? And I told him, and I said, the day we have wormholes, you won't need transporters, right? Because you just pop a wormhole when the planet's surface and step through, and there you are. You don't need the lights and the sounds and the room and the Scotty on the switch. So this is important. Yes. Roy's here. So Charles, can we make a wormhole? No. Why not? All right, next. Oh, well, there you have it. No. Bill Shatner's going to be so disappointed.
Actually, in the original Star Trek motion picture, the Enterprise almost got sucked into a wormhole because there was a warp drive malfunction and they were forced to pull out. You guys all remember that? Yeah. Now, the story is with wormholes is it requires a great deal of energy to have happen. A transporter, supposedly, they could draw the energy from some sort of mystical warp drive engine or something, right? And so that was something that you could do person to person. A wormhole requires something much more supernatural, more powerful. A black hole, for example, or some sort of mystical creature, someone who could master magic and dimensional travel. So in that sense, the wormhole strategy is less likely to be our strategy than a warp drive type strategy, where we can somehow go faster than the speed of light through space through our controller engine.
But do we borrow this energy from another dimension?
Good question.
Because how much energy? If this is like the galaxy, like you warp it, right, and then you travel through the little bridge and the warp, unwarp, then you can cross the galaxy during the TV.
Okay,
and then you can make it.
Right.
Yeah.
The problem is, you would have in that scenario, you are warping space. That's a lot harder than warping cells.
That's warping the entire galaxy.
Right, whole galaxy. That's what a wormhole would have to do.
Yeah.
You see?
Okay.
So what happens is with warp drive, this is all sort of retroactively created after the television show, right? It was so successful. The idea is that you put the Enterprise or your spaceship of choice into a little bubble that is outside the regular space-time that we live in, but it's inside in a little pocket, right? So it's almost in its own extra-dimensional travel. And what happens is that bubble can move faster than the speed of light, even though you yourself cannot. So while you're in the bubble, that's when your warp drive is working. It's not warping space. It's warping you into, out of, through, and otherwise overly space.
Which would take much less energy than folding the whole space itself around it.
In fact, a Mexican physicist named Miguel Alcubierre used Einstein's general theory of relativity and actually came up with some mathematical equations that could make a warp bubble like that exist. So mathematically, you could do it. The problem is, once you've made the bubble, how do you move that thing?
The bubble itself.
Right. And you still don't have anywhere near the technology to be able to do that.
Okay.
What do you do with it once you've got it?
You go through space-time. And once you've done that, once you made the bubble,
yeah, and you travel, then what happens?
What you have to do is literally warp the bubble in such a shape that the space behind it is changing at a faster rate than the space in front of it. And that's how you get it to move through space. You keep warping in this sort of continuous way so that the warp pushes you forward through space.
That's not what he asked. How do you get out of the bubble?
Yeah.
Once you get to your destination,
Once you get to the top,
There's my answer. Okay, quite literally. Your dilithium crystal in Star Trek, right? Your dilithium crystals are shut off, and then the bubble just evaporates.
Oh, okay. It's good. So I have this dream of the future where wormholes, because now you're putting the kibosh on it, wormholes are how we get around. There's no one needs roads. Not only that, your back of your refrigerator could be connected by a wormhole to your grocer. And they pop it open, oh, the milk is that, and they put in fresh milk and eggs. And you just have a contract to have that loaded, and there's no truck, there's no Amazon out of business.
right.
Or the truck would drive it.
Wormholes, one end here, the other end there, and just move them around at will, then your scenario is completely likely. The problem is it takes so much energy even to create a wormhole with two stable locations that even if it were physically possible, which we don't know yet, when that happens, it's station to station.
Yeah, but we told the Wright brothers one day we're going to fly 400 people at 600 miles an hour across the ocean.
Yeah. So you're flying a bicycle right now.
So that is the challenge.
Where is your sense of time perspective in that declaration that you're making?
I would say that sometime within our lifetimes, we will be able to generate something that we have tried to do since the end of World War II, that is controlled nuclear weapon. We will, at the moment, there's some technology that's happening. We can develop all over the world. We can plant a site called
No, this is low bar. I'm talking about, like,
Wait a minute. I don't know if that's a low bar because when you think about it, what we're talking about here is the need for massive amounts of energy. So if we're able to control fusion, which, I mean, we know what kind of energy we have in the past.
yeah, I'm just saying, we should have had fusion decades ago.
Yes.
We're not there yet.
That's right.
So I want that to be a given, and now give me like Casper stuff.
Okay,
So
hold on.
so now, take the conversation a little different.
Okay.
So we're talking about warping space.
Chill.
All right. There's another feature that we've seen
Now I'm
in
going the right
different
way. There's the
villains,
village.
and that's becoming invisible. It's not disappearing,
Right.
but just
That's a different thing.
that's something different.
I know how you do that.
Get older.
Coming up on our
And then try to talk to young
arch
people.
roll to stop.
Yes. Invisibility played a very prominent role in Fantastic Four, the most recent superhero movie, featuring the Invisible Girl.
And
now Invisible Woman.
there's the invisibility cloak in
Harry
Potter.
You got Star Trek, the Romulan.
I spy him.
Yes. Right. So and also the original Predator movie.
Oh yeah.
He could go invisible, but in all those cases there's a little bit of jittery,
A shimmery
thing.
like silhouette.
Yeah,
A
exactly.
see-through shimmering silhouette.
I'll tell you what I know about this, and Charles, you might know more, that there is work on this. It is real. In fact, in the James Bond, I forgot which one, Quantum of Solace, one of those where his Aston Martin has an invisibility button and presses it and it just becomes invisible, but it shimmers into invisibility, of course. You can still shoot it, you just can't see it. Continues 2-year cycle as though you were not there. So what you do is instead of walking away, they have a series of reflectors that apparently move the light around your body and then send it forward as though you take this beam and you're sitting on the other side of me. You just see the wall behind me and you don't know that it's there. There are demos of this online. There are YouTube videos. You can see this. Authentic. It's not AI fake. The problem is now it works only if you're exactly aligned. And if you go offline, then the effect collapses. So, but that's a start. And you're functionally invisible when you can pull that off. Yeah.
I was not aware of the technology, but there's they've only got.
Yeah.
If you look at a stealth bomb,
Yes.
right, it's visible on the radar, but that's only in that particular area.
Very important fact. So the stealth bomber has a radar cross section of a bumblebee. Okay. So a dangerous bumblebee, right?
Yeah.
Right. And that radar, like, okay.
thing.
So it's more trying to detect planes.
build up
Radar. So just at the risk of stating the obvious, the radar hits your intended object, and it reflects back to you in the shape of what the thing is. And you can look at the blip, and if it's got any kind of detail, then we put some AI on it. And how you put the plane in. The stealth bomber is designed very specially so that any incident radar reflects in a different direction than straight back. Okay. And can we get a version for this? Speed traps, because to try to send, then it doesn't go back. It doesn't go back to a whiz by. It'll just say there's nothing there.
Exactly.
Right. So if you look at how the surfaces of the stealth bomber and other stealth technologies are shaped, take a line and hit it, and it'll never send you back in the direction on any surface. Okay.
That's all faceted and
Correct. Yeah. Correct. And just a side fact, the earliest of the stealth bombers, the F-117, used now decades ago, had some flat surfaces on it. Okay? Take a look at the fascinating history of this. You know why it had flat surfaces? Because the computers were not powerful enough to perfectly solve the equation to have a continuously curving surface. So it had to approximate it with flat surfaces. So that still reduced the radar cross section, but it didn't take it to as low as the bumblebee. Once we could fit it with high performance computing, you could curve the surfaces so that hardly any signal goes back. So here's the problem. Exactly your point. Its radar cross section is a bumblebee, but we just step out and look up. There it is. Okay. Its optimal cross section is the full plane. Okay. So where you are in the electromagnetic spectrum, exact matters here. So, yeah.
Well, invisibility isn't all that great of a superpower by itself. Let's face it.
Okay.
If you can just hide, that's great, but you got to do something other than hide, right? And so, in fact, with the superheroine, the Invisible Woman, the Marvel Comics back in the 60s developed an extra power for her. Not only did she have the ability to turn invisible, she also could project invisible force fields. She could actually do things invisibly to you without even touching you. All she had to do was to envision a shape of something made of force that was invisible, and then be able to lift you up as if you were sitting in a chair, or to move you around, or to push you back. It had the ability to protect and be invisible at the same time.
So that's effective even if the force is not invisible.
That's
right. It's a field around you.
Right.
To do that. Now we know in quantum physics there's an effect. Quantum is spooky, weird stuff. And that's why everyone, it attracts people because they want to understand it. And quantum physics is not there to understand. Charles, correct me wrong. No one comes out of a quantum physics class and, oh, I understand that. No, you don't. Okay? It's just what the universe on the small scale, we can describe it, we can calculate, but we scratch our heads every single time. And one of the effects, fascinatingly, is if you take two very smooth, very flat metal plates and evacuate the space between them, so it's a vacuum, you start making them closer and closer to each other. There is a point where there's a whole new force that pulls them together. It's not electromagnetic, it's not gravitational, it's not a strong nuclear force, it's some new thing. Maybe they just really like each other. Good point. They pull each other together. And that discovery won a Nobel Prize. And so
The Casimir effect.
yeah, the Casimir effect. Sure,
That's the Casimir force.
the Casimir force. So
Yeah.
tell us, what causes that?
The Casimir effect is caused Because there are things called quantum fluctuations in our universe. Even when things have apparently no energy or no change at all, at the quantum level, levels far smaller than atoms, with energies far tinier than a single, say, electrical pulse, there is a little bit of this happening all the time, all around you. So if you are getting a smaller and smaller space between these two plates, you get to a small enough point where the quantum fluctuations are actually bouncing off of those plates. And so you create an attractive or sometimes a repulsive force that kicks in only just before they touch, because the quantum effects, small as they are definitely there. And so you can imagine actually influencing something without actually pushing on it or pulling on it. It's actually just the quantum work that's being done because the universe is shimmering on that level.
Really close. Super. So I'm a villain, just an average villain, but I want to upgrade to super villain.
Ooh,
How am I using
the Casimir effect?
Casimir? Yeah. I don't think it is like stuff.
Yes,
Right?
great point. If you somehow were a superhero or a supervillain that could take advantage of quantum fluctuations, you might be able to say, I hereby declare that the quantum fluctuations in this part of the universe are going to be reduced. In exchange, the ones in this part are going to be increased. All of a sudden, you have all this extra energy over here and much less over there. So you can imagine something moving something from here to there due to quantum effects.
Because the object naturally wants to go from higher to lower.
That's right. So you could move something without doing anything other than just changing the quantum function. Creating that radius. And the problem, of course, is that this is a much larger space than the quantum fluctuation space. Anytime you have a quantum fluctuation, you're talking things that are billions of inches, right? Going from this part of the room to that part of the room. If you wanted to carry me from here to there, that's many, 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 many billions of inches. By the time that happens,
Yep. So there's a
not yet.
there's a physicist, George Gamow. He's a hero of mine because he was an active physicist and he wrote for the public.
And he was one of the first people who hypothesized the hot Big Bang theory.
Yeah, that's right. That's right. And so he had a series of books called Mr. Tompkins in Wonderland. And each book, it's fanciful and he illustrated it with cartoon illustrations. Each book was you living in a world where the universal constants have different values. So, for example, instead of the speed of light being as fast as it is, the speed of light is 60 miles an hour.
Oh, wow.
So you drive down the street, he's describing this.
Yeah.
And as you go 30 miles an hour, he's describing how all your scenery changes. And so it was such a world to jump into, which has me wonder if you had real power over the universe, you could adjust the value of the physical constants that control quantum physics. Maybe you could dial that up so that we respond to quantum physics in the way particles do.
There is an episode of Star Trek The Next Generation called Q, where this exactly happened.
Really?
Yes. The great creature named Q, who was being punished by his other fellow Qs, had been punished. Yeah, right, because he was being too mischievous. So what happened was that they were having a problem on a planet, trying to solve that problem, and they couldn't figure it out. And so they asked Q, said, what would you do? He said, well, it's obvious, change the gravitational constant of the universe. And all the rest of the humans are like, we can't do that. But the engineer, Geordi LaForge, said, hey, maybe we could. Right? That's the superhero you're talking about. Somebody who could actually change the gravitational constant of the universe, and boom, suddenly your planet is as light as a feather.
Just because you change the force
Just
of gravity.
because you change force of gravity in that.
That's a badass power right there.
Right.
So you're thinking like a supervillain now. No, don't bring me into your category. So what intrigues me about, I think most about what has happened in this world is there's some writers who know that matter is mostly empty space. We think we're solid objects, and we're just not. And you can say, how empty are we? Well, let's go back to Ernst Rutherford, who's a New Zealand physicist, turn of the previous century, around there, I think, or a little later.
1900,
Yeah, around there. experiments where he hammered gold very steadily. Gold is very malleable, so it's the most malleable substance on the periodic table. So you can hammer it. That's why gold makes very good leafing. Gold leaf. Yeah, on cake. What's this word for it? Gilding. Right. Yeah. Oh, I wonder how that happens. Gild. Yeah. Okay. So anyhow, when you gild the statue, you take gold leaf, and using very little gold, you can greatly shine something up. And that's why the Oval Office totally everyone. Absolutely. How is Jim? Okay. So he hammered it really, 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 really thin. Okay? So the gold leaf is just dangling there. And he fired particles into it. 99.999% of the particles went through as though nothing was there. And occasionally one would bounce back the other way. And when he did the math on this, he realized that atoms are mostly empty space. And it is rumored that the next day, he alone on Earth knew this, that he was afraid to step onto the floor from his bed out of fear he would fall through. Just like the nightmares of a classical physicist transitioning into the world of the quantum. Believe me, I have been that. So it's one physical example. The nucleus of an atom is to the size of an atom as a Cracker Jack kernel of corn is to the entire stadium in which you may purchase it. You certainly got the right analogy here. You said one Cracker Jack to the size of a stadium. Yes. It's the nucleus of an atom to the the structure of an atom. Yes. Yes.
I'll give you another analogy.
Please do.
If we took all of the Hamptons,
Okay.
took the space out of it, all of the Hamptons, including us, would fit in my fingernail.
Man, you just messed up a lot of real estate value.
No, but it's true. The universe is 99.99999.
Okay.
999999% empty space. And that
Now I just have to work that way.
Double-edged question. Okay. First of all, why don't we just keep falling through stuff or putting our hands through
Almost there.
things? And yeah, exactly. Is this a serious probability?
Such a long ride.
So, having asked that question, I know the answer to it. So, how is a superhero using this to their advantage to walk through? We've got the Flash can run through walls, and
the Flash can run through walls. I thought he just ran fast.
He can ran fast. He can vibrate.
He can vibrate, and
you have Dr. Mangal who can just move through things.
Wait. So the Flash can do what?
He can. He's like.
And then get through a wall. And he can get through a wall by shimmying, vibrating. Wait, Charles, is he moving through the empty space of the atom?
He's quantum tunneling. Yeah. Okay. Quantum tunneling.
Here we go.
Yeah. Okay. Here's somebody behind. See, because you have this 99.99999% emptiness, the reason we don't keep falling to the floor is because those itty bitty bits of material actually produce force fields. So there are fields of force, mostly electromagnetic, some nuclear, some gravitational, around the particles that make us up. So, for example, when I'm clapping my hands together, it is the force fields of the atoms in my fingers that are touching each other. And that is what's creating the sensation in my hands. That's right, because they just tap each other because the fields are there. But it was shown 100 years ago that every once in a while, because there's all this empty space and there are fields involved that make this ball not fall through, that every once in a while something will go through just by accident, because the shimmering quantum fluctuations every once in a while will shimmer just right so that a little particle will actually go right through. That's called quantum tunnel. And this can happen, and in fact happens all the time, and I was so surprised to find out when I was writing the handy quantum physics answer. It was part of electronics technology.
I don't want your mind.
There's a thing called a quantum tunnel diode that was in many radios and other transisting products that were for sale in the 50s, back in the day, 1970s. They are now obsolete. This is quantum technology that's now older than our non-quantum technology, our cell phones, for example. But quantum
Whatchamacallit.
is a phenomenon, and it happens all the time. But the Flash
Come on, get up here.
is supposedly so good at this.
Lay down.
He can vibrate his entire body.
Lay down.
All of his trillions and trillions of molecules.
Okay, good
and
girl.
go right
Good
through
girl.
and figure out exactly the jigsaw puzzle way to get through the other side.
Oh, it's like a game show where the wall comes out and you have...
Yeah, It's exactly that. But he's able to do it with every single atom in his body and every single atom in the
And he
world.
doesn't leave the body hole to the wall.
So is this basic probability that this continue working out which molecule is in quantum? That's what goes
5, 6, 7.
The odds of any single molecule doing something like a quantum tunnel is tiny. Now you add it up and multiply it by every single probability of every single and you have a number that's so beyond anything that even our current supercomputers can't even compute it for one tiny lake.
But the Flash.
But the Flash.
So is this the same thing as quantum teleportation?
Yes.
Okay. Do so.
Quantum teleportation is not being the upside. Okay, the term quantum teleportation actually predates the idea of teleporting, say, a human from one place to another using some sort of machine. But it was the idea of communicating information from one place to another. So, reading a message perfectly, and then sending that message perfectly to a different location without any kind of degradation would be what we used to call teleportation. Okay, so
know that. So you're saying material objects.
that's right. It was this information. So actually a way of teleportation, because your dots and dashes here could be translated exactly as dots and dashes there, with very low error. Quantum teleportation is different. You want to move quantum information from one spot to the next. And then when you do that transportation, there is always a massive amount of noise and energy lost, and your information gets lost. But if you can quantum teleport, and you can get this information from one spot to another without losing, you literally have an unbreakable code, a way to transmit information that nobody else in the universe can actually ever intercept. And that's what quantum teleportation is really cool about.
And that's its way of
At this moment, that's right.
It would be a perfectly secure internet.
That's right. Yeah, that's right.
So what's our energy source?
The energy source is merely the fluctuations that are caused by the quantum system itself. You're sending bits of information, bits of quantum information called qubits, and then you package them in whatever physical system you want, whether it's an ion or an electron or some other set of particles, and then you send them either in a beam or along a wire or a fiber or something like that to another spot. And you want to preserve the coherence of information inside that qubit for sparks.
All right. And Scott, mate, is that happening tomorrow?
Right now, people are actually able to quantum teleport the little bits of information for actually many moments. So you can do pretty well, like send just a few pieces of yes, no, up, down, and so forth, without losing coherence. But the moment you have too much noise, the moment the temperature goes up above a few degrees above absolute zero, you start losing information.
Because things vibrate and that's rate of
Those quantum fluctuations overwhelm what you have.
absolute. It's not good for testing.
Depends on what you're testing.
Guinea pigs.
That comes up quite a lot in quantum, doesn't it?
That is true, it does.
Do things actually have to take place at absolute zero? If it is,
Oh, that's
then
a great question.
we might just be out of the equation.
Yeah.
Absolute zero is 459.16 degrees below zero Fahrenheit, give or take. Okay, at that temperature, no motion of atoms or molecules happens above the quantum fluctuation. Okay, that means that the reason we are warm is because the different atoms and molecules in our body actually vibrate and move and rotate and things like that. When all of that stops, that's the temperature known as absolute zero.
Well, can you blame them?
No.
I mean, it's pretty doggone cold.
It is pretty doggone cold. And at that temperature, see, what's interesting is it has been shown let's go with that temperature. The coldest temperature we've been able to achieve is actually colder here in a laboratory than out in space. Here in the laboratory, we've been able to get down to a few millionths of a degree above absolute zero. But out in space...
Oh, what a failure. Right.
But out in space, we have the leftover heat from the Big Bang. The cosmic microwave background radiation. It's everywhere. And that's about 3 degrees above absolute.
It's still damn cold.
Yes, you don't want to go out there.
Where did Jeff get?
But it is
So
very...
the Big Bang itself is hanging around in such a way that it's warming space to a point where we can't get to an absolute zero.
That's absolutely right. And that heat is actually very important in the universe because we have these cold clouds of hydrogen gas floating around in the universe. These clouds would be doing absolutely nothing and having no emission of energy of any kind, except the cosmic microwave background warms them up just enough that once every 10 to 20 million years on average, the hydrogen atom floating around in space will do a spin flip and release one single photon.
Oh, it's flowing water.
At a wavelength of...
That's what it is.
And so
that means what? It's like the two of them are just like, what? And it releases and it feels just like,
it's
what the hell are you talking about?
It's the best inside joke in the universe.
Okay.
See, we tried hard not to laugh. But as Neil could explain better than I can, because this was actually part of the area of research he was doing more than I was, 21 centimeter radiation is what tells us where the hydrogen material is in the universe and how it's moving to make new stars, new planets, and new galaxies in the universe.
So the excitation of these clouds, that's the right word. Yeah. What? That alone, is it now a chain reaction?
Yes. Okay. You create that bath of 3-degree Kelvin cosmic microwave background photons, which in turn causes these gas clouds to do something. And that allows us as astronomers to figure out how the universe is aging and what its processes are going on millions of light years away.
But just to put this to bed, if absolute zero is the coldest possible temperature, then you need something to draw the heat away from what's there. And as you do that, it's still kind of in contact with what's doing the drawing of the heat. So, in principle, it may be physically impossible to reach absolute zero. Because it's always, like you said, it will always be in contact with something that's not absolute. Because otherwise everything is absolute zero, and it's not.
Right.
Okay? There's some enclosure. So no matter how good your Yeti is, okay? You're standing the all right? No matter how good it is, the ice in there eventually melts.
Right.
Okay? Because there's heat transfer, however slow. It's not a perfectly, if it were perfectly insulated, it would never melt. But that's not how the actual world works.
That's right. So even without quantum effects, you will wind up with thermodynamic losses. Plus, even at absolute zero, we're now pretty sure that there are quantum fluctuations. That's it.
So what about that breathe fire or something? Or whatever, they make fire. They put dragons.
You mean like Godzilla or something?
I don't know. Any of the ones that...
Or when Superman burps.
Oh, back then when they... Sorry. I'm just wondering, thermodynamically,
yes,
the fire has energy, so that energy has to come from within.
Yeah. Oh,
Fantastic Four.
Yes,
Yeah,
the Human Torch in the Fantastic Four supposedly is able to convert chemically. Like fire is basically a chemical reaction, right? Something like a nuclear detonation, or say the interior of the sun, that's a nuclear event. And so somehow that energy gets converted to heat, depending on what the processes are in the sun, or in the person, or in the campfire.
Okay, so the fire superheroes don't need quantum effects.
They don't.
It's just simple burning.
Yeah.
Okay.
Even thermodynamics is extremely powerful. A lot of us don't understand just how powerful, but you know how there was this industrial revolution based on the steam engine? take an 18-wheeler and drive it right through the wall, from that side to that side and all the way out. You have so much kinetic energy from the thermal motions in the air alone that it's easy to see how you can have tremendous superpower, even if you don't have quantum power.
This is coming out of the Industrial Revolution.
That's right.
Yeah. Let's keep this going with the fact that we know if most of matter is empty, yes, most of the universe is empty space, and most of matter is empty space on top of that. If you had the power to collapse particles down and then restore them, okay, you get
a smaller version of yourself, and then a bigger version of yourself. That's Ant-Man.
Exactly. Ant-Man.
Yes.
By the way, worst name for a super. It is. It is really bad.
Well, but he's pretty powerful.
But that's the quantum mechanics.
That's exactly the
mystical pin particle, right?
Yes, that's right.
They are borrowed from another dimension. So are we looking at quantum mechanics being able to enlighten us and our understanding of higher dimension?
What a great question.
Thank you.
Great way to
It won't happen again.
The so-called pin particle is a fictional thing invented by Marvel Comics. There's a scientist named Henry Pym, P-Y-M, and by using these, harnessing these particles, which are sort of super dimensional, you're able to make things big and small. You're literally, in a sense, taking something like this, making it small, and then making it big or making it huge, because you're taking advantage of the space in between your molecules and your atoms.
So this fictional particle is exploiting known physics.
That's right.
Okay.
Yeah, but this fiction.
But let me ask you this: what you just said, if you keep the same mass and you make these super big, I'm this Stay Puft Marshmallow Man.
That's right.
Yeah, I'm a big ball.
And so therein lies the extra dimensional part. The only way that these particles can work in our world, as if they were actually in our world, right? But if they were really working, you would have to add mass to things as you were growing them, and you would have to reduce the mass of the things that you were shrinking, right? Otherwise, if you shrunk down your vehicle and put it in your pocket so that you could ride it later, you would not be running very fast.
It would still weigh thousands of pounds.
That's right.
In your pocket.
Right. So
just because it fits in your pocket doesn't mean it belongs in your pocket.
That's right.
Okay.
So somehow these pin particles.
What? It's kind of deep, actually.
That's just because
that covers so many problems in life. Doesn't mean it belongs there.
Yeah, I love it. Yeah. So this material, this matter, had to either go into some dimension that doesn't weigh anything in our space-time, or be drawn from somewhere that previously didn't have any weight in our space-time and suddenly become having weight. So you're really shunting these things in and out of space-time.
Otherwise, your challenge would be the creation and destruction of mass in our own space-time.
That's right.
And we know what happens when that happens. Those are nuclear bombs.
Right.
If you take mass and make it energy, that's the end of your situation.
Yeah. Sorry, I don't know why I got all excited just then.
Yeah, that's
okay.
Worries me, Charlie.
No.
Okay.
Because nuclear fusion also powers the sun.
Yeah.
It's a very benign thing. We often think about it on our world as being dangerous, but in fact, without it, we wouldn't be here.
Okay. We talked about quantum mechanics.
Yes.
There's another term that comes up, and I think of a superhero. I go back to Dr. Manhattan. That's the superposition, where I am simultaneously in different parts, in any part of the world, wherever I want to be.
Yeah, Dr. Manhattan could be in many places at the same time. He would be on Mars and the moon and in his laboratory and, all at once.
Wait, is that correct? That way?
Well,
you said he had an accident.
Wait, yeah, first
Dr. Manhattan.
we're geeking out here. This has turned into four guys at a bar. Does everybody know who Dr. Manhattan is?
Yeah, Dr. Manhattan was created in the Watchmen universe by Alan Moore in the 1980s.
Yeah.
And this is a superhero which didn't really want to be a superhero. But he's essentially blue, and he's played by Billy Crudup, and he doesn't wear any clothes. And he just sits around in his blue.
Is that your most obvious fact about him?
Yeah.
Well,
the man is the most powerful entity ever created, and he's going to say he doesn't wear clothes.
I got to tell you, looks pretty good naked.
Anyway, the idea is that he is, by himself, a kind of quantum. he has no problem doing anything that quantum particles do, but he is the size of an atom. And therefore he has an unbelievably large amount of power, because he can do all the things that can happen on microscopic scales, but out on the scale of us and our size.
But for him, his personal quantum constants are just larger.
That's right. It's as if George Gamow
As I
himself.
was talking about earlier, he's got he's Mr. Poppins in Wonderland.
That's right.
And he is the Wonderland.
That's right.
Right. So I would think it's that he was simultaneously in those places. He's just like a particle has a probability of having any one of the places in it. What we call the functional wave anywhere quickly. He can say, well, I'm going to be on Mars, I'm going to be on Mars right now. And then he's on Mars.
And now, he's travel there. He's already there all the time.
All the time.
Right. Because he's entangled with himself.
Yes.
But is it entanglement or is it manipulation? Great question. Let me try to break that down a little bit, okay? You guys might have heard of quantum entanglement lately. It's in the news. It's very exciting and so forth. But actually,
It's not in the Hamptons news.
no?
Okay, I heard some people on the beach the other day talking about it.
Quantum entanglement is the idea where you can take a particle and literally split it into two identical particles, and they can be as far apart or as old or as new or as kept or as they want, and they will still stay the same particle. Okay? So you
And know about each other.
That's right. So you have something that could be the size of a solar system, and yet if you got information on one particle, you would instantaneously get the information on the other particle, as if they were entangled. When in fact, in the quantum way of thinking about it, they are still one particle. They just still happen to be connected as both a particle and a wave that keeps changing size and shape. So you have this particle, and we in the classical world think of particles as like a piece of stone or a rock or a piece of metal or something, just a particle, right? But in fact, if you think quantum, the particle and the wave are interconnected, and so the concept of size and the concepts of age are very, very different. And as long as you can keep that coherence and make sure that there isn't noise or static that interrupts the connection between these pieces, they are one particle, no matter how.
There's a contest who can create the most distant particle pairs in this exercise. And the leaders in the world is China. China has the farthest separated particle.
It's not for long. I mean to say that I'm going to take care of this 2 weeks. 2 weeks. And China will lose.
So the contest, we don't know, like, it's like an arms race, but we don't know why what's good.
Right. At this moment, physicists are still trying to figure out whether entanglement is a perfectly normal thing that happens all the time, we just never noticed it, or whether it's actually something profound that can be used in a way, for example, for instantaneous communications or other kinds of storage of information and so on. What we do know is that if you entangle some things, you can create this thing called a qubit, which is a piece of information that's not just 1 or 0 that we use in our current computers, but that's right, they're called bits. But these qubits can take positions between 0 and 1, doing strange things in between until such time as you read them out as a 0 or a 1. Okay, this is a very odd concept in our heads, but what it is, it means that we as particles, or conglomerations of particles, could in fact communicate or otherwise interact as waveforms of energy in ways that we can't imagine now, but might be able, for example, to break computer codes instantaneously, or allow us to do any kinds of computations or communication.
The future of quantum computing.
Yeah, very, very.
We're on the doorstep of it.
It's doorstep of it. We're way, way, way on the doorstep. But we are at the doorstep. Yes.
So what you're describing is in the lingo, the collapse of the wave function. Because the particles are waves, the waves are particles. But when it's manifesting as a wave, the wave occupies all the space that you're describing. When we think of particles as here or there, the wave is whatever you calculate the extent of the wave to be. The particle can manifest at any point within that volume. And so then you collapse the
That's the manipulation. Yep. There you go.
If we've gone through the collapse of a wave function and we understand the duality of particles and waves, where does it go when there's a many worlds theory? Because you're not quite, are you certain about that one?
The many worlds,
Many worlds theory.
ask Charles.
Because you don't know.
No. Neil knows, he just doesn't like it as much. We've had this conversation a little bit before, but maybe we can expound on it. See, here's the thing. About half a century ago, some physicists noticed that the mathematical equations that describe wave functions and quantum physics and so forth don't necessarily have to reflect our universe alone. In fact, those equations are consistent with the picture that every time a quantum particle does something or doesn't do something, a whole new universe is spawned. Okay? Imagine if, for example, I go out there and I get hit by the jitney. Okay? All right. I would have a good lawyer. Thank you. Okay. In most cases, I would not be in good shape. But you could imagine a scenario in the universe where I'm hit by the jitney and I'm fine. Just that one tiny possibility. If that happens, then that universe has me in it just fine. And then all the other universes, they continue to coexist, but I'm not fine. Now imagine tomorrow I get hit again by the jitney. And then that process happens all over again. There's a tiny little possibility that I'm fine. And that person survives. If I keep following the surviving me in front of the jitney, I am in a universe where I live forever. Ooh, man.
Yeah, but you keep getting hit by the damn sauce.
Yeah. Right.
That sounds like hell.
That ain't so good. I agree. But you see, the vast majority of other universes that exist, right, in this mathematical many worlds, I'm not fine. And that's the one that we are most likely going to share, right? Because the chances of me being fine after being hit by the jitney are very small, right? But you can see the problem with this many worlds hypothesis of quantum physics, right? You're generating essentially a nearly infinite number of new universes every single second that the universe is around. It's not quite infinite because the universe isn't infinitely old, but in every single circumstance, you can imagine literally anything to happen.
Charles, isn't this kind of a cop-out? What it's saying is we have the wave function, and the wave can collapse here or there, and we don't know until it's tilted or until it does collapse, but it might have collapsed over there. In fact, maybe it did collapse over there, and you're telling me it did collapse over there, and that's a whole new universe. So
It is not that.
what you're seeing our statistical ignorance and trying to step out the back door by making multiple universes so that we're no longer statistically
Significant. Yeah.
And why should I embrace that?
You should.
Okay.
You don't have to. This is actually
That's one of the universes.
right. In one universe.
In another universe, you're just like, I love many worlds.
Chuck is exactly right. You can literally imagine any kind of universe, and it has just as good a chance of existing, assuming the laws of physics are the same in that universe as in your universe, as your universe. Our universe, the one that we share right now in this room, is a collective collapse of the wave functions. Our wave functions that make up who we are and where we are have all collapsed to this moment in this place. That makes our universe right now unique. If we allow the existence of all those other universes, what does that make this universe? Right? Mathematically, those universes are just as valid as this one. But we're in this one. Some greater validity than those.
So, Charles, you're dead in this room. We've established this one.
Yeah, you're under the bus, buddy.
So, then what about the Marvel universe when they keep going in and out of multiple?
Yes, the quantum realm.
Yeah. Is this some of that?
Yes.
Was that some of this?
Here's the point. If you get that small, right, your wave function becomes pretty much melded with all the other wave functions in this many world universe. Right. As a result, if you figured out some way to navigate this quantum realm, which is far smaller than even what the Big Bang was just before it began to bang, This is a millionth of a billionth of a trillionth of a quadrillionth of an inch. Really, really, really tiny. This Marvel Universe fake quantum realm thing suggests that if you all you need to just be able to navigate this really weird quantum tiny space, and you can emerge in that universe where I'm living forever, despite being hit day after day, right? Then you can come get me from that universe and say, here's a guy who can't be killed by the jitney. Bring him back, navigating through the realm to here, and then bring me over there, and then you can engage in the most amazing insurance fraud in history. That's the quantum realm of Marvel. Okay, should we believe it?
I wonder just what's possible.
Yeah.
And we're not quantum size. You can't play in Mr. Tompkins' Wonderland. Fun to think about, though.
But you said the math works. The actual math.
Yeah, so curious fact is mathematics as expressed by the physicists is a representation of our models of how the universe works using symbols, which allow us to manipulate the ideas perfectly logically, right? You can argue what's true or not, but once you've set it up mathematically, then manipulate the math. And that's tantamount to manipulating your understanding of the universe if it's the correct model of mathematics. So everything else about this math is working in our universe.
Right.
So I step lightly towards these other realities that are so mind-blowing.
Right.
But again, is it more mind-blowing than what quantum physics might have looked like to the original classical physicists? And we live, there is no IT revolution without the exploitation of the quantum. There is no creation, storage, and retrieval of digital information without quantum physics. It's not some other thing that other smart people worry about in the lab. It is with us. We are embedded in it. There is no modern industry without it.
Yeah.
So,
And if you were to go back to like 1910 and show somebody an iPhone, like, they burned you at the stake.
if they resurrect the Richburn,
Yes, they could. They'd be like, we'll roll around with you.
So are we gradually inching towards the principles of quantum theory rather than it being able to be achieved with immediacy?
so I'm going to say that I want to get Chuck's reaction. There's now those parts of quantum physics that we need, that we want, that help us in our technologies, in our computers, and everything. Then there's the part of quantum physics that's just kind of floating out there that we have to take seriously because it's the extensions of what we know works mathematically and conceptually. So now you go to the edge and you explore the edges of those equations. Oh my gosh, you just gave me a whole new freaking universe. And what does that mean? And what is that going to take us? They got entanglement. They got all of this. That's why people are taking it seriously. Because the rest of it works. In fact, quantum physics is the most successful theory of physics ever performed. It has never been shown to be wrong. And that's spooky.
But that's because nobody understands it.
Let me try to land this plane here. Is what you're telling me that this sort of probabilistic understanding of a particle, the wave-particle duality, when it's manifesting as a wave, we don't know where the particle is. The question doesn't even make sense. It's the wave that takes up the space, and depending on how you poke it, it will manifest the particle here, there, or somewhere else. Okay.
Yes.
Now you want to create universes in which the particle can be in those places, turning what is probabilistic, statistical, and quantum into something that's deterministic. So Einstein's quit declaration even, because he was slow to adopt the weirdness of quantum physics, he said God does not play dice with the universe. And if you're in our realm, it kind of looks that way. God is playing dice with the universe. But in your realm, God has loaded the dice and knows exactly what roll is going to get. Because every roll is happening in any universe that's out there, spontaneously created in the act of the collapse of the wave function. Have I said that accurately?
You have. the same time. And
That's why the house always there. And it's just a matter of which table you want to roll. That's all. Beautiful, that is. Beautiful.
It's so, the casino, if this is God's casino,
Right.
they are. So, Charles, give us a thought to take us out.
When we first thought of quantum physics, heck, when I first took quantum physics in college, I was like, this can't be right. But that's only because I didn't have a good sense yet of reality as a whole. Today we understand, as I see more and more of reality happening, all the things that I don't understand, it's only what I don't understand, not how the universe works. So I'm hoping that as I continue to go on my journey of discovery and studying things like galaxies and supermassive black holes and things like that, that I am open enough to see those things which I could never conceive of, things that in my gut I know are wrong, and yet be able over time to see that actually that is reality.
And I'm still yourself short there. It's not that in your gut you know it's wrong. It's that in your gut, your life experience is insufficient to absorb that which stands far outside of your life experience. So it's not that it's wrong, it's just it doesn't fit.
It doesn't fit.
Yeah, that's not hard to stuff. I know.
Thank you. These guys are the most supportive students I can ever ask for. If I can embrace that part of me which I don't understand and don't know and perhaps even fear, then I'm going to be better off in this world. And I hope all of us would share that.
Thank you for that. Thank you for that. I'd like to do at the end of our show offer a cosmic perspective, the summation of what we've discussed, and perhaps a perspective on what it means for us today, tomorrow, and beyond. This is a scientist. It's kind of your job to stand at the frontier. You put a foot in what is known, a foot in what is unknown, and you sort of work your way out there. Now, what we do know is that, of course, as the area of our knowledge grows, so too does the perimeter of your ignorance. So we can feel good about what we do know, as Charles surely does. He's worked hard, his expertise. But as you walk the perimeter, oh my gosh,
Oh,
hard to know what we do. And for me, I celebrate things. As the German poet Rainer Maria Rilke noted, one needs to learn to love the question itself. Because those questions are not just, I don't know, and then walk the other way. They draw you towards the path of discovery. And what I enjoy about our world is that we have creative people who maybe took a few physics classes, maybe read your put them in the question book, whatever it's called, and sorry, want them in that. And these are people who are creative storytellers, cinematographers, comic book illustrators, people who are not content with just the world. Let's reach out to all the places science can take us and stoke our imagination beyond what is otherwise visible, just looking at what we know today. And so I celebrate the fact that we live in a world where science is accessible to enough other people who are not scientists that we can celebrate science as a fundamental part of our culture, and not just an activity conducted by pointy-headed intellectuals in laboratories. And that is a cosmic perspective. Thank you, Bill Paul.
Excuse me, Dottie. I gotta get up. Dottie, get down. Jesus.
Yo, what's up, guys? Chase.
It's more than a coaster.
Yo, what's up, guys? Chase the Burrow here, and welcome back to another Elden Ring build video. Today we're going to be testing out Light Roll, seeing how effective it is in invasions, and if it's worth using over some higher poise armor sets. One of the strongest things about Light Roll in invasions is the fact that you can kind of escape 3-man pressure. Usually if you're fighting a 3v1, you have to be pretty defensive, because if they stun you, they can kind of chain running attacks together and catch up to your immediate roll very easily. One will be stunning you, the other can just catch up to you while sprinting beside his teammate, and they can kind of infinitely pressure that way. While using Light Roll, though, you can escape that situation. If you dodge the running attack properly, they're not really going to gain any distance on you because the roll is that much further. So you can easily escape those 3-man pressure situations. The downside being your absorption is much worse using any Light Roll setup, so you're going to take more damage when you do get hit. So in the situation where you get hit by 2 or 3 people, they can almost one-shot you, so you do need to be careful. There are plenty of ways you can boost your damage negation though to make up for that. Oh crap, is when I have this, boost their defense is up to 33. So this is more in line with my natural armor set, and then you can push it even further by using the Opaline card here. Now we're sitting with a physical defense of 43, and if I compare it to our armor set, I have 53 physical defense, so it's not a huge loss, honestly. It's only about 10. As for the choice of talents, the Shard of Alexander is kind of a must on any weapon-focused build. You just get such high damage out of your Ashes of War. The extra HP is always a good choice on a build like this that has low defense, and I need both the great tools and everything for snipe with the big Light Roll easier with the athletic line to use. And I also get some nice fashion out of it as well. that's everything that I really have to say about the build. Let's just see how the labor works in patience. The area of the lakes of Kai. Alright, Kai, what do you do? I see what looks like a big ol' axe and a roasted axe. Hello, guys. How are you? Highlight. Cool roasted axe.
Big infrastructure.
Hello. How are you? This is gonna be a rough time for you guys. I'm standing on water and don't have lightning, so there's that. It's not yours. Oh, you're using lightning as well. Jeez. I'm actually surprised that he didn't win a race with that so much. It's terrifying. Oh my god, yes, yeah, but I got rolled out there by the running out one. Without my light roll. Just by keep jacking. Pretty interesting. The little aura that that gives off is kind of nice too, in the water. Yeah, close. Oh, that ain't my input. Oh, I don't want to get too used to doing that. I gotta do that on my regular builds and just get hit. But it's so good. You can just whip punish from your roll because they won't reach you. Oh, that is so strong, honestly. And the jumping L1s are terrifying. This is awful for him. I'm so sorry, Kai. Ooh, but yeah, the rolling L1, after I noticed that you went straight towards it, usually they chip you with the follow-up still, because you don't roll very far with medium roll. Well, absolute liminal. Who has not been here yet. Perfect, I'm ahead of them. Oh, they're right there. Well, I'm defensing up. I'm not the most tanky. Although I do have a very big ball. Oh, I gotta start this off defensive here. Hello guys, how are you? I run into Mr. One Shot. Well, oh no. The fact that he didn't kill himself is crazy, man. That is just ridiculousness. You should always consider yourself, man. Cool. Man, the crouch attack on Katanas is so crazy. Just two-shot that guy. But he was wearing cloth and didn't have a lot of defense. What's going on here? Where's the Doom Eater at? I know he's nearby. Hello there, sir. I sense backstabs in my future. Goodbye, absolutely. Oh my god, guys, calm down. Absolutely dragging our body. Well, hello there. Skilo, Dizzy. Oh my god, you guys were sprinting this way and then instantly turned around. Did it have something to do with me? I think it may have. Was it? Okay, now this is funny. Hang on, how's it going? That's hilarious. What is this tactic? I have a bow. Sorry. Wait, Blue? You slowed me down, but you didn't stop me. Of course. You know a great shield, Mr. Blue. Come here, Blue. Perfect. You know what? You've been using this with light rolls hilarious. Hey, wizards. Let's go for the back line there. Not what I expected. Alright, so we got a wizards, a fister, and the host hiding in the back is elite build. Hey, you leave that guy alone. Okay. That ant deserves love. Pretty sure this is the dead anyway, so we're not gonna go that way. Let's also make sure we're bugs. They are afraid of bugs. That is fair. Bugs are strong. Okay, I think this water eats the AoE sometimes. Sometimes. Depends. Hey man. Oh, you know what? Good dodge. Good working with you, man. They're trying to gang up on you, I'm here for you. Oh. Okay, well, my jump attack was actually used as a dodge there by accident, but, you know, nonetheless, it was. Whoa. I need it to be done so we can kind of trade. There we go. to stop those bugs because they're very annoying. And light roll, see like that, just no pressure from the fists anymore just because I have light roll. Oh man, the bug enjoyers, dude. They really love doing that. He's trying to maximize his bleed. I appreciate it for it, but we, excuse me, gotta run those. At some points though, they do hurt. We do that. Another phantom, cool. A wizard as well. Alright, this could be potentially good. If he stops with the flies, we can easily just use the hand of Millennium. That guy's almost dead. On his bubble as well. I could have the range of Star Shower, indeed. Hey, Blue. Sorry, I saw you. There was no sneaking there. Not Star Shower. Hey, Blue. You're kind of down here alone with me. I don't know if you want that, but... Oh, gosh. Not having a bit of poison tank is like a first downside. Can't do scary trades like that. Real. We could probably do this, though. He doesn't know I have range at all. It'll die in literally 2 lightning bolts. That is what he's so using that. Blue's a little bit late. That's okay. It's right there. Nice. Well, you know, I could have just been doing this all along, Kilo. You don't even know how to dodge. And then, you know, you hit in the back and survive. That's really the rule of Blue Phantom. Well, hello there. Hey, Dovakin. How's it going, Dovakin? And Faith support. Okay. So we have what looks like we built. A little scary, honestly. Bleed could be a problem.
Oh, so close.
It's weaker to status procs with the build. Okay, well, it doesn't really matter. Their damage is ridiculous. Hey, my bubble is so fire. I'm a fan. Fire hurts. Hey there. How's it going? It's kinda, I might get a little too used to the light roll. It's crazy that you can just get out of pressure instantly. Like, look at that. Normally that'd be able to pressure me, but the light roll just lets you escape every possible roll catch. And credit for hitting that. I never see anyone use that spell. I see just attacking. Yes, I'll jump right back into that, because that's gotta work. Hey man, how's it going? I wanna make sure my attack buffs stay though. And I do need to make sure I heal the bleed procs. Running heavy. Look, the fact that actually caught a fan pretty crazy, but thank you. I'd rather not be involved in any of that. I won't be trading into you, my friend. Not today. Not today at all. The Escape Danger 2000. Waterbender. Wait, Waterbender. Is that a name or Warbender? Oh, that was a mistake, man. Knives are not a good call. This could be fun. This is just my entertainment. Oh, I could get going. I think dodged it. Anyway. I have the length, my good friend. Unlike the voice. You know what? They stayed together. They kind of covered for each other. They did well. Gorgon. Alright, Gorgon. I see you're a little busy. But it's a wizard, so we're gonna have a little bit of fun. Oh, nice. Holy. Wizard got lucky. Hey, Mr. Wizard. Gorgon. Hello. You know, I'm just kind of running between you guys. It makes it a little bit more fair. This guy's behind me, isn't he? Dude, I can just like roll away from him. I love it so much. It's kind of addicting. Hey man, I thought you were going to be a little bit aggressive this evening. I'll be running by you. Do I things first, I must go for your wizard. And I... you know what, let's boost our attack. Alright, now we're boosting our attack. Oh my god, a blue! Hey, blue! Blue-bee-doo-bee-doo. Where are you? You know what, let's go quick step here. Hey there, how's it going? Ow. Say, why couldn't I quick step that? That was so weird. Reverse quick step? Yeah, you know what, I have more luck with the reverse quick step. Bye, Mr. Blue. We enhanced our damage again. And you know what? Need a little bit more magic defense. Actually, the wizard hasn't really done much, to be honest. It's been more the host actually attacking me. Oh my god, I missed. What is going on with the camera? Come on, Mr. Wizard. Yes, Stars of Ruin. Stars of Dodge, where am I? Wizard. Goodbye, wizard. Hello there, Mr. Rivers of Blood. It's hard to roll backstab with light roll. Alright, now we're gonna try to backstab him a few rolls. Roll. Do it. Do the roll. Okay, well, it's hard for me to roll while locked down. Oh, well. Goodbye, Goro. Can't escape the light roll. Oh, mausoleum, and they're up top, but the elevator's down low. Who would bother sending this back down if you were actually going to fight the boss? I feel like no. Suspicious. Okay, we're gonna go up. And then we'll throw one of these on. I sort of get the feeling that we're going to get ambushed. It's the feeling I have.
Oh, shit.
Hey man, so we're gonna do this instead. I knew you guys were gonna be pretty. I mean, you set the elevator down and everything. You guys were just waiting around for that. That's funny. Oh, beautiful. I love Stormvale. Okay, they're close by. Close enough that my compass is gone. So, let's get all our defenses going. Hey there. How are you? Oh my god, it's the other Agent Twin Blade too. See, no one expects it. Oh, that's a connection and a half right there. Ooh, boy, oh boy, oh boy. Oh, I don't have the dagger on, right? Oh my god, that's like the connection of the Oh, there goes Nazgul King. It just took a while. This is so fabulous and a half. Oh boy. Who's gonna do this and help? Okay, that works. We can run about, even though that was terrifying. Oh, Halleck Tree Hot tonight, Ringo.
More dirty dishes? Oh, okay.
But where are you guys? Oh, I see. And it's not too bad for you, man. I want to come up, but I'm going to need you to fix me on the way up. I don't know if I trust you, sir. I quite literally right
connecting my rail
hey,
system.
I could probably check through that.
Just get in it and go. I got this areas where to stop it. So I pull strap.
Oh, see you later. I thought you were sneaky. No, definitely not. Okay, if we're gonna go up there, it's definitely camping it. Let's get all that we can for the buffs. I get the feeling there's a wizard waiting to just go off up here. Well, I guess that's sort of a wizard. Oh, even that wasn't enough to get me out of range. Oh, that worked though. Well, that's one of the cool things about light roll with the katana. You get to roll so far away, and then you can kind of punish the roll catch attempt. Oh, nice. We've invaded.
Stopped at my first. First
Very popular in usernames, apparently. Oh, hello there, guys. Big hammer. Oh my god. Big bomb. You know, that makes me want to do this, yeah.
So much fun.
Dirty Bo. My bubble hasn't even finished yet. Your host is quite literally dying here. I'm trying not to kill him. You're making it really difficult. You're in my way.
Oh my god.
I'm almost named Yellow.
I can sightsee.
Hi, Dirty Bo. What's going on here? What is the plan, my man? Arnold. I'm gonna follow you. And then we're gonna back.
And I live streamed the whole thing too.
Heal you love to use so much.
Oh, okay, Christ. Okay.
Trying to heal again? I'm actually so sorry what's going on here. You know, I'm like, heal to all this DFP class. Hi guys, how's it going? Fellow enjoyers? Hello? Lots? Woo! Starting out strong here, I see. Might have length, you should be prepared for that, honestly. Sir, you need to just stop attacking into me. It's honestly, like, trade everything. I see you, Birdie. Man, honestly, you can just, like, roll attack. Just, like, roll towards them. You can also use the light roll for pressure. No matter what, like, you're out of range and you catch up to them. Hey there. Goodbye, saturated towel. I'm hearing the terrible sound of wizards nearby. Oh, there. There's one, yes. And they're not both wizards, that's fine. Ah, yes. The instant escape button. My favorite. So you're at the beat. Oh. Honestly, you didn't think that was gonna kill him. Hey, wizard! Oh my god. Mega Mind over there with like 900 HP. Alright, those are all the invasions that I have for you guys for today, testing out light roll. I had a good time, and I know maybe not good. If you're someone who enjoys high DPS builds and burst damage, or doom building in general, build might just be for you. You can get in, apply damage, and escape situations that you normally wouldn't with mid-roll. And honestly, it's just nice to mix it up. I definitely play different with this setup. I'm trying to just space a little bit better, get some high DPS and burst damage at Phantom while trying not to get hit, and then we use the light roll to get out of the bad situations. Once again, there's my stats on the right. Awesome plays throughout the showcase, and I did have a wide variety of weapons, but I definitely mostly use the dual katana setup. It's very powerful with this build. If you guys have any recommendations for any builds, weapons, or theme videos, always feel free to comment.
Going back to my main base.
Until the next video, goodbye. I will see you all next time. Thanks so much for watching. Goodbye. Goodbye.
But there are lots of interesting signatures of life that we can look for that go beyond oxygen. Look, what's in your hairspray? Exactly.
What you're saying is when people look for alien life, that's what you're telling me.
We're looking for aliens that have fly away.
At least
Like if they have unmanageable hair.
I've never seen an alien that had hair.
Yeah.
They're always bald.
None of them just having bad head. They must have bad head and they have some bad tentacle days. I don't know what.
This is Startup. The rest I see here. So, and physicist. I've got with me that person, man. Welcome back to
That's all. Thank you so much. It's nice to be back.
You're in New York.
So
I'm in
Brandon.
New York City.
No, thank you.
Right now. I made the trip.
So,
All across the country. It's been
Was
really
rain.
good. We lost a lot of people. There were attacks along the way, but we made it.
so we'll find out.
Is that lightning?
Yes, please. Yeah. I always love it when it's
Large.
listeners and viewers come
Mining
to see the show.
outpost.
Excellent, excellent. So today, we're going to exoplanets. It's been a while since we dipped into that ocean.
I love hearing about this because my understanding, and I'm sure both you and our expert will talk significantly
Getting closer to my main base, you can see all my beacons.
We knew almost nothing about this fairly recently in science fair, right?
I was using those for chopping down trees, clearing out. So this first structure here you see is my giant PvP, PvE Coliseum. Wandering Iron Giant, or Iron Golem. Yeah. Giant arena. Cow. There's my big tower. Here's my farm. Coming into the main station. Hey, don't bark. Come on now. Use your inside voice, please. And then world spawn, mushroom and ice. We can go in here. We're gonna go to world spawn.
So I was the only scientist in my cohort. There were 16 of us. The others, one of them's a one-star general, one's one of the first Congress
My giant
people. He's Native American.
rocket factory makes gunpowder. I got paper and automatic crafters for rockets.
That's right. It's usually one advisor per cabinet agency. So I took on the Agriculture Department and the Science and Technology Policy Office of the White House. And that was back 8 years ago.
Giant.
So many other things. Basically around the world, have been busy at this activity, finding exoplanets, studying
What
further.
happened?
So can you just catch us up?
Oh, that was a bit of lag.
Yeah, the last time I was on the show, Neil, was a couple years ago, and we were still, fresh off of being at about 5,000 exoplanets, and as of today, we were asking, we're at 5,921. So within about a month, probably by the time this airs even, we'll be at 6,000 in caution lights, which is pretty cool.
Hey, Bella, do you want up here, baby girl? Okay, you want some lap time? All right. Hey, I'm raising the feet. There you go. There you go. You can get some colors. Yeah, you can get some colors. Okay. Headed to world spawn.
So remind us who Nancy Grace Roman is. Was she the first NASA chief scientist? Is that right?
She was the first chief of astronomy in space science at NASA, and she, some people call her the mother of Hubble. She architected some of these big missions, and so we're really delighted to have this next flagship named after her.
And just to be clear, she's not going to be up there operating the telescope.
I couldn't tell you that, but that's not currently the plan. We've got some redundancy if she's not up there doing it.
Zero.
So the general habit is to name telescopes after Debbie. So she's not. There's one exception to that, but all the rest, that's the case.
So she knows she's up there right now.
That's correct. Totally no use. So, and also, give us a reminder of what it means for a flagship mission.
So we have lots of telescopes of different sizes and lots of satellites. We've got things down to CubeSats that universities can build. Flagship observatory is going to do lots of great science for dark energy and dark matter. It's going to map all of the structure, and we can see details so we can understand all kinds of cosmological questions. All sorts of queries are going to be answered there. But I'm really excited that it's not only going to, as it's staring at all of the maps out there, but for tiny changes in light that can tell us about thousands of planets using microlensing, right? How gravity is distorting light. But then it's also got this whole tech demonstration, a chronographic instrument actually block out light so that you can see things that are about 10 million times fainter than the stars that you're looking at. So this flagship means that it can do all kinds of science. It's not just focused on one specific question.
And it probably says the flagship is also defined by price.
So, this is just a little away from World Spawn.
I mean, they're the things that we're most proud of.
You play favorites, but this is your
There
most
we
special
go.
child.
Neil is everyone's personal astrophysicist here at NASA's Exoplanet Exploration Program office. We are the nation's, exoplanet purveyors. So
Okay, good with that. So you mentioned this coronagraphic capability. So right now, we don't actually look at planets, exoplanets. We're looking at their effect on the host star. So you're going to be able to directly image exoplanets with this telescope. Is that correct?
that's going to be how we're going to see some of them. Right now, you can get a handful of these with the James Webb Space Telescope. We've also directly imaged some planets from the ground with really big telescopes like the Keck telescopes in Hawaii. But this is going to be the first time that we actually fly a demonstration to actually get us down to see things because,
My first little
Jupiter is a lot easier to see
hobbit hole.
than Earth. So we're going to push on that a little bit, getting ready for some of our future flagship missions.
So our catalog is
A little bit of starter kits.
Those have been easier to find with some of these early techniques, but we have to find a lot of different types of exoplanets that are also smaller. So it's
Sheep, cattle.
Okay, very good. So tell me also about the roads observatory.
Yeah, so this is one of these missions that we're really excited to be working on. So the idea is that we now know that there are so many exoplanets out there. There should be enough nearby around stars that you could just go out and look and take a picture of them. And what you really want to do is not just take a picture of an exoplanet, but you really want to get a sense of what's in its atmosphere. So hopefully you can actually take a picture using ultraviolet, infrared, visible light, this whole wavelength range to get spectra and look for biosignatures.
So biosignatures, like on Earth, that would be oxygen. That's right.
Right now, that would be oxygen, but it's funny because if you look at Earth's past, the biosignatures actually change over time. So way in the past, over 4 billion years ago, up until about 2.5 billion years ago, if you looked at Earth's atmosphere, you would have mainly seen methane. And that was the metabolism of the earliest organisms. But then over time, oxygen built up. And then when you went into the Proterozoic, you would actually get, then 500 million years ago, you would actually see lots of ozone as the thing to look for in the atmosphere. And it's only when you get to the modern era, then you get the oxygen, all of this coming from photosynthesis and signs of life.
Okay.
3 planets long.
And you don't know when in the planet's evolution you were peeking in upon it.
Exactly. So you want to design a telescope that can cover all of those possibilities because we want to be sure that we're looking for life in as many options as we can.
Even presumably, you don't know that it would evolve in similar ways and produce similar gases.
We go a whole other direction. Could there be chemical signatures that could be signatures of life as we don't know it, and therefore you're not looking for it?
There's all kinds of things that if they produce life, we might miss it because we don't know how to look for things that aren't familiar to us. But there are lots of interesting signatures of life that we can look for that go beyond oxygen. We can look for nitrogen dioxide, which is an industrial pollutant. We can look for some of these other, like looking for what's in your hairspray. All kinds of things out there to look for life like we know it.
Fluorocarbons in the hairspray? Is it still in the hairspray? They still do that? I thought they took
I
it out.
don't know, but
But what you're saying is you could look for alien pollution. That's what you're telling me.
We're looking for aliens that have flyaway hair. At least, like, they may have unmanageable hair and/or toilets that need.
I don't think I've
They're a little on the smelly side.
I've never seen an alien that had hair.
Yeah.
They're always bald.
Let alone just having bad hair. They must have bad hair days. They must have bad hair days. I don't know what. They sometimes need controlling, and sometimes the things they use to control them have damaging effects on their atmosphere.
that would be great for us to see, right? Because we want to see those signs of pollution, of hairspray. I mean, even looking for the satellites that they've got going around their planets or looking for their city lights at night. All of those are things that we hope to look for with this telescope and to look for signs of life. So it's not just the oxygen.
Are you also looking in binary star systems where their planet orbit might be a little unstable?
So we'll look at some binary star systems, but so one of the tricks though about the World's Observatory is to find something actually like Earth. It's actually got to look something that's 10 billion times fainter than the star, right? So this is like a bird flying near the sun. If you're trying to look at Icarus, right, before bad things happen, it's kind of hard. You'll need some sunglasses, and so this telescope will also have a coronagraph instrument or a high contrast instrument that'll be able to dim that down. And so once you can actually do that, then it becomes possible to look for planets like Earth and to see all of the sort of variations in what might be there.
So tell me about the formation of exoplanets. So in my professional days, I remember the very first images of a protoplanetary disk, where it's a disk of gas around a star that hasn't made a planet yet. And is that big-time industry now within your community?
So I'm very biased, Neil. My PhD thesis was on protoplanetary disks, except back, 10 years ago or so when I did this, we were basically looking at blobs. It was the science of blobology. And we've come a long way since then, because now you can actually use radio telescopes like the ALMA telescope in Chile to look at, these radio wavelengths of the dust and these beautiful spiral structures. You can see gaps and rings. There's a lot of beautiful science that's coming out of it. So I don't know if it's as big time as looking for alien life, but it's something that's definitely advancing quickly. And I just love talking about disks because everyone gets really excited about planets. But I think that in the same way that you think, like, oh yeah, I'm going to be an astronaut, I'm going to go to space and I can see this beautiful picture of Earth, this beautiful picture of Earth. But, you might want the 23andMe of the astronomy world of, where did we come from? What else is out there? And you can get all that information from disks because if you look at a protoplanetary disk, all that material goes into forming planets. It's, left over from forming a star, and the gas and dust collapse. And, most of it goes into the star, but, about 1% or so goes into forming planets. And then long after that gas has dissipated and you formed your planet, you have some leftover material, right? In the solar system, we have this zodiacal dust where the planets are, and then further out we've got the Kuiper Belt, which we know is your favorite for giving Pluto a hard time there, Neil. So,
and one other thing about the disks, only 1% goes into planets. Where does the rest of the gas go?
So most of the mass, right, from that gas cloud is going into forming the star, right? And then you've got a lot going into forming the planets. So a lot of this is going to dissipate in time. If the star has UV radiation, that's going to interact with the material there. Some of it's going to flow away.
Oh, wait. So maybe I misunderstood. So the 1% number you gave, is that 1% of the disk mass or 1% of the cloud, the total cloud mass, the protocloud?
Right, okay, sorry. So I conflated two things there. So of the protostellar nebula, you have about 95% of that mass goes into the star, and the rest goes into the disk. And of what's in the disk, about 1% is solid material, right? So it's the little dust and grains, and the other 99% is gas.
Got it.
And so you've got these all stages of disks. You've got that protoplanetary disk early on, and later on, after that gas goes away, you're left with the planets. You have things fighting each other and colliding.
Come on, Dottie, get up here.
Gives you debris disks like the Kuiper Belt and the zodiacal light here in the solar system.
So now, update me on the latest with JWST, because that's been going like gangbusters.
It's so cool what we can finally see from space. So they were actually able to use the near-infrared superpowers of JWST to actually see water ice in crystalline form in this debris disk around a star called HD 181327. And this is really exciting that you can actually see water ice in a debris disk, because in the Kuiper Belt, we've got all of these dirty snowballs, right? We've got the comets, all kinds of icy material. And there's been hints of this from the ground before, but we've never actually been able to see it. So when they took a look at the light scattering off of this disk and compared it to what we see in the Kuiper Belt, it looked pretty similar. You've got these dirty snowballs. And And so what this tells us is that Kuiper belts are not just something that we only see in the solar system. They might be kind of common.
So you found a Kuiper belt in an exoplanetary system.
Exactly.
Very cool. All right, then that's with JWST.
That's right. And so it means that there's all kinds of icy material out there just waiting to form planets. So water might be more common in the early solar system.
But somewhere out there, there's another Neil deGrasse Tyson just missing another Pluto.
It's because it's a Kuiper belt.
Yeah.
We're going to have to have it there. No, I'm not. I'm an accessory to the device. I didn't pull the trigger on that.
Get ready to leave the world behind because on Paramount Plus, Star Trek Strange New Worlds is back for an all-new season of genre-bending adventures, romance, mystery, action, space zombies, special guests. This show is going where no show has gone before. One show, infinite adventures. Don't miss the new season of Star Trek Strange New Worlds, premiering July 17th, with new episodes on Thursdays only. Paramount Plus.
So this is fundamentally a cosmic queries edition.
It is.
We solicited questions from our Patreon fan base
They've sent in a fantastic assortment of
on
questions.
this subject. Well, let's bring it on. Go.
Well, I always like to start with, I think it's always fun when there is a young fan. So, Hugo Dart from Rio de Janeiro says, I'm giving my 7-year-old daughter Olivia, who is also a big fan of Star Talk. Here is our question. What do you find most surprising or humbling about the current state of knowledge of exoplanets compared to when you first entered the field?
So obviously there's so many more exoplanets now than when I started 20 years ago. And I think what's really humbling is the fact that we keep finding new worlds and places where we've looked. We thought, oh, we've already found what's there. But then you find another one. For example, James Webb's recently found some planets in a system where they're probably planets, Kepler 51. And suddenly they said, oh, there's one more that we missed. The Kepler spacecraft was up a while ago. And we're still analyzing that data and finding new information. And the fact that we can find worlds that are so different from our own, right? There are these ocean worlds, there's lava worlds. It's all just so spectacular that it's really exciting, but also kind of humbling to find that diversity of planets. It's like a zoo.
Did you not expect that diversity?
I think for so long we assumed everything looked like the solar system and Earth, right? Because it was all we knew. And in the solar system, we don't have worlds covered in lava. So the fact that that's great.
Well, while we're talking about different types of worlds, things that look different, Adrian Martinez from Houston says, my question is it possible for a planet to naturally form in a donut shape, like a torus? And if not, what are the weirdest or most unusual planet shapes we've discovered in the universe so far? Do we even know the shapes of a lot of these planets? Because a lot of the time you're just going on maps, like, can you see a shape even? I don't know.
So that's a good question, Adrian. I don't think it's possible to form a donut planet. Neil, correct me if I'm wrong, but that seems hard with gravity concentrating everything. And the easiest shape to be is round because it pulls everything in. Nice and tight.
I wrote an essay back when we opened the Rose Center for Earth and Space, because in the middle of this facility is a round thing. Okay? There's a sphere. So I wrote an essay called On Being Round. And it was all about how nature just wants to make things round. And when it's not round, there's a really interesting reason why it's not round. But I don't think we ever get anything of doing that. Because the gravity wants to put it all in one place.
And it wants to put it in the middle.
I was just going to say, though, there is, a really cool planet called WASP-12 Beta that's sort of egg-shaped, right? So I think that's pretty cool because it's really hot. It goes around its star almost, once a day. And because it's so hot, it's actually tidally locked and it's getting stretched. So not only do you have this planet that's like an egg, it's not perfectly spherical anymore, but it's actually giving off mass. And so we often find that planets can actually disintegrate a little bit and leave a torus of material from where they were. So you don't get a torus-shaped planet, but you have the leftovers in a torus, which is pretty cool.
And what about was it a comet or an asteroid that looked like it was two spherical pieces stuck together? It looked like a dumbbell, like there were two. So you can get that, but it didn't form that way.
So it formed just two round things, and then it sort of met.
I think that's the understanding.
Well, so you can get all kinds of weird shapes in asteroids and smaller bodies. Because one of them ends up to be a planet that has so much mass, then you're becoming round and forces.
Well, come on, get up here, Dottie. Come on, Dottie.
Come on, baby. You can get up there.
It stays out there.
There's a couple of questions here about habitability.
Wait up.
I like to combine questions sometimes if they're on similar topics. So William Warren from Abingdon, Maryland says, what exactly defines a planet as potentially habitable? Is it just being in the habitable zone where liquid water could exist, or should we consider atmospheric composition, magnetic field, plate tectonics, and more?
No.
And then also, Sean Browning from Hood River, Oregon,
Stop begging
when our
me
star
not to get
inevitably
down.
expands and consumes the inner solar system, what effects would that have on the remaining planets, and what planets would fall into the new habitable zone? Or would the expansion of the sun change the remaining planets' orbits, or would the mass not change, therefore leaving the planets in the current orbit? So what makes a planet habitable, and how will that change as the sun starts to swallow our worlds?
No, that's such a good question. I mean, right now we use the term habitable zone, but really that should, the long, the asterisk, read the fine print should really be region around a star where liquid water may be possible and seen on the surface. So just because a planet is in the habitable zone, that just means it's the right distance from the star where liquid water could hopefully persist on the surface. So sometimes people talk about the distance from Venus to Mars because, in the past these looked different. But people use different definitions, and part of how we think about habitability on a planet is involving liquid water, right? Because that's what life on Earth uses today. But there's so many other factors, right? So you need water, you need energy. So starlight, all that UV radiation is good stuff, right? Makes the crops grow, but too much, and that's a problem. So if you've got, the stellar wind and all kinds of stellar flares from your star coming and beating down on you, that's bad news. So you want just the right amount of energy, and then you of course need nutrients to make everything happen. So I think there were some questions in there about, what happens as our star changes, right? And our relationship with our world is not the same. And I think, where the habitable zone is in the solar system today is not where it was in the past, and it's not where it'll be in the future. Because it used to be a little closer into the sun. That's why Venus used to be wetter than it is today. It had more Earth-like conditions, and then of course you had this runaway greenhouse effect, and now it looks kind of hellish. And so in the future, we expect as the sun gets brighter and expands out, Mercury and Venus are actually going to be sucked into it and eaten up. But we should be okay. But out by Saturn is going to look pretty good for habitability. So maybe Titan, the moon around Saturn, could have a good day because it's got a lot of methane in its atmosphere, kind of like early Earth.
I heard this and I didn't believe it until I did the calculation. That when the sun becomes a red giant,
my
and
main
Earth
base.
is gone, so is Mercury and Venus, and
kind of a
Mars
grand
becomes
deal.
uninhabitable as a hot zone. Pluto becomes a habitable place.
Right.
I heard this, and I double checked it, and it checks out.
The numbers crunched correctly.
They crunched correctly to make a Pluto a place where we might all have to escape to survive. There'll probably be a picture of me at the immigration.
No entry. Just you get taken into the second room.
Aren't you going to be reconsidering your life choices
Go
at
to
that point?
Mushroom Island.
We found some things you've said, and we'd like to ask you some more questions. Speaking of more questions, Ben Grund from Detroit, Michigan says, I hear it's sometimes said that our solar system is pretty atypical in its constituency. Is every solar system a snowflake, or are there some common themes to their layouts?
Oh, I like that.
Well, I mean, we were just talking about the debris disk with water ice, so we do have some snowflakes out there in other systems, quite literally. But I think the thing that we originally thought was that everything was like the solar system, and then we found always these big planets like Jupiter close into their star, hot Jupiters, because they were easy to find. We discovered that actually they're nothing like the solar system. But over time, we're finding more elements that are pretty similar. So I think that we can say that we're not, totally unique, but totally dissimilar. So I like the snowflake analogy because I actually think that there's enough similarities and differences for it to work for us. Also, people just tell me I'm a special snowflake. I love the fact that you have exoplanets discovered all over the world, right? It's not just telescopes in one place. And so you have WASP, right? This wide angle search for planets that found exoplanets in its early days, and then they've souped up versions. There's Super WASP now. So I think there's even a Super WASP telescope in South Africa. They're all over the place. And this is just one of many. Many of them have awesome names, by the way, right? There's the Trappist ones that come out of Belgium that are making these great discoveries, and then we can keep studying them both from the ground and in space.
God, scientists love a contrived acronym. Nothing makes scientists happier than finding some acronym.
When I was in college, there was some computer scientist. This is early days, before that was even a title. There was some program we were all using, and its acronym was MAGIC. What does that stand for? What is it? He says, mnemonics are generally idiotic constructions. So ever since then, I've not overdone my mnemonics. So what else you got?
All right, so Ryan Gerritz from Pittsburgh, Pennsylvania says there are many different types of telescopes with a variety of sizes, but none of them have the resolution to actually see exoplanets. So my question is, how big would a telescope have to be to have the resolution to actually see a nearby exoplanet? Could we align multiple telescopes on Earth to make a telescope effectively as large as one of our planet's hemispheres? And would that even be big enough?
Does he? I'm betting, because we do have images of planets. I think this questioner wants to see continents and oceans and cities. What do you think?
I mean, because I'm right there with you, Neil, that we've seen exoplanets already, right? Again, they don't look like Earth so far. And just got a couple of pixels, although, as Carl Sagan's famous moniker of the pale blue dot from Voyager 1 spacecraft, and it's, out of the edge of the solar system looking back at Earth, you just see a pale blue dot. So we're not yet at the level of...
That'll be it for today once we get back to home base.
Habitable World Observatory, you might actually be able to get a sense of oceans because of how the light, you would have the glint coming off of the water. So to get to the stage of continents is pretty far off. I haven't done the math on what you would need to do that. It seems hard, but certainly we can take pictures of exoplanets now from the ground that are big like Jupiter. And again, with HWO in the future, we'll be able to see the planet itself without that level of detail.
So not to diss Pluto even more, but when you describe this pale blue dot image taken by the Voyager 1, prompted by the efforts of Carl Sagan when Voyager 1 exited the solar system, that picture was taken when Voyager 1 passed Neptune. That's the edge of the solar system.
Wow.
It was well inside of the orbit of Pluto. Yeah. So the idea was aliens would come upon our solar system and they'd see the first planet, and that would be Neptune. And that's when they take a picture of all the inside. So I didn't want people to think the edge of the solar, that they were way out there.
No, it means relatively nearby, right?
Yeah, relatively nearby, exactly.
Because you want to picture the family portrait, right? It was taken on Valentine's Day in 1990, right? It's showing the love, right? The love of a couple of pixels here and there.
Yeah. All right, time for a few more, I think.
Yeah, absolutely. So Jay Starks from Waco, Texas says, here and reporting for Cosmic Query duty. I've been thinking a lot about how planets in our solar system are impacted differently by the distance from the sun, such as temperatures and the number of days it takes each planet to orbit our Helios. Do all exoplanets follow this pattern with their stars too regarding distance? I'm curious if this is a universal truth for all exoplanets in outer space.
Interesting. I think he's asking, the laws of physics that describe orbits, does it change from one planetary system to another?
I mean, the beautiful thing about physics is you don't have to have a great memory. The same rules apply over and over again. So you just have to learn it once. But I think it's kind of interesting to think about the solar system because you know Bode's law, right? Neil, right? How back in the day when people were looking for, Uranus and Neptune and things, they would look at the distance from the star, from the sun, and say like, oh, there's a planet at these geometric distances. And so then they found the planet and they went, yep, that checks off. And then they said, oh yeah, we found Ceres, because back then Ceres' fourth planet was viewed as a planet. And then they said, oh yeah, there's these other things, and then it didn't quite work. And so we stopped. But the notion of distances from the star having planets is one that people have thought a lot about over history. And I think it's actually pretty cool that when we look out at these exoplanet systems, what we see looks nothing like the Earth and the solar system, and that's partly because they're different systems, but also even within our own solar system, everything moved around. Jupiter and Earth didn't just form exactly where they are today. They did a little dance to get there.
The planet migration.
Yeah.
What's going on there? Yeah.
Inside of my horse skulls.
When Isaac Newton first wrote down his gravity equation, and it worked for Earth and the Moon, it worked for the Sun and Earth, it also worked for Jupiter and its moons. So it wasn't just like a sun thing. It was, oh my gosh. And so that we correctly, though audaciously, said it's a universal law of gravitation. That's kind of bold, but I mean, why not? We're egocentric as humans, right?
Well, while we're talking about moons, there's a question from Fred Dog. That's patron Fred Dog. I don't know if you're from the Westchester Fred Dogs, any relation? But Fred Dog says, it was once thought that habitable worlds had to exist within the habitable zone and would require a magnetic field to protect itself from harmful solar wind particles. However, this has been determined to not necessarily be the case, as our understanding of habitability continues to grow. Now moons like Enceladus and Europa have become candidates for housing possible life, but fortunately, they also happen to be protected by the magnetospheres of their respective planets. My question, how has the inclusion of moons further complicated the search for life beyond our solar system?
I love that. And I'm going to add to it. Will there come a day where we just abandon this concept of habitable zone? Because if the conditions are right somewhere else and is not in the zone, it could have life. So maybe the habitable zone concept is constricting our creative thoughts of how, when, and where we might find life.
Yeah, so I mean, it's great that Fred Dog mentions these moons, right? Europa and Enceladus, where you might have this thick layer of ice, and you've got all this heating that makes a nice, cozy ocean underneath. So one of the things about the habitable zone, like I said, that fine print of liquid water may be found on the surface here, right? If there is life under the ice, you won't be able to see it from the atmosphere as we know of now, right? So when we talk about the habitable zone, it's about where could we actually look at our telescope and say maybe there's a biosignature for life here. So it's not saying that moons are out of the question. People are definitely looking at moons. I think David Cuping, who you frequently have on this show, your neighbor down the street there in New York, he's always thinking about exomoons. And so
up the street.
So here, if you flip this switch, it'll spawn regular zombies to go out in the arena.
And we're delighted when he's on the
armor and weapons.
So, I don't know if we can detect the signatures of life from a moon yet. But it's one of the things that we want to look for. And actually, the question of does it complicate things? Yes, because if you want to get the signature of a moon, now you have to get rid of all the information about the planet. You can't just say, oh, I'm only seeing the moon there. In the same way that when we study exoplanets, we have to get rid of the star to study the planet. So there's a different level of complexity. And to your point, Neil, maybe it's time for a new definition. I think it's just, you need something without the asterisk and the fine print of, liquid water surface here.
Those spawn.
Let me tell you how old I am. So when I was in graduate school, the Voyager mission was doing a grand tour. And everyone was in high anticipation of what it would discover about the planets. And when it started imaging the planet moons, oh my gosh, the moons became more interesting than the planets themselves. And now people care about Jupiter's moons are way more interesting than
skeletons.
By far. I don't know. I'm speaking out of turn here. Tell me, you got to agree with at least some of that sentiment here.
I think that moons are spectacular, right? I mean, I think the fact that, you can look around Saturn and see hundreds of moons, and they all, you've got ones that look like the Death Star, right?
Yes, it's got this big crater in it. It looks like the Death Star.
PvP kids.
The ray. Yeah. Don't you guys call it the Death Star moon?
I think we normally call it Mimas, but,
You see where they got a bunch of creepers.
When no one's listening. Wait behind closed doors when you're just a few pints.
Exactly. So there's all kinds of beautiful things there. But I wouldn't count, how awesome Jupiter and Saturn and the solar system
and then once the cushions are...
Because there are things we don't understand, like why does Saturn have a hexagon?
Cushions from my arena.
And why do all of these outer planets have rings, right? Saturn gets all the credit for, the hula hoops that shine. But, all of these giant planets do, Neptune, Uranus. So I think there's a lot going on there, and I can't wait to see this for other systems.
There's a nice question here from Andy L., who lives just up the road from Anjali and me in Thousand Oaks, California. My understanding of the two main exoplanet search methods, periodic stellar dimming and stellar wobble, is that they both rely on their star's ecliptic being in line with our line of sight. Does this mean that if a distant star's ecliptic plane is angled off our sightline, neither of these methods would work? Could that explain why some stars don't seem to have planets?
Don't our people ask good questions?
Your people ask great questions, Neil. I mean, and that's one of the best parts of getting to hang out with all of you is it's just the most fun. People say, like, it's a secret, I don't want to tell anyone. Not everyone should know how cool exoplanets are.
Oh, yeah.
And answers to the questions. Like, once we find life, we were joking earlier, Matt, like, I can't tell anybody in my ambassador role, but no, I want everybody to know, Call your senators, call everybody, tell them it's amazing. We have two methods for finding exoplanets that Andy L mentions, and it's exactly right that the transit method, right, where the planet is lined up just right to block out the starlight every time it goes around. You do need that geometry to be pretty close to at an angle. We call this sort of edge on. If it was so-called face on, 90 degrees off, you wouldn't actually be able to see that starlight getting blocked. And in the same way, the radial velocity or Doppler wobble method is where the mass of the planet tugs on the star and we go back and forth. And this only works, of course, if that star is moving back and forth from the telescope. So both of these don't work if it's at exactly 90 degrees or face on as we call it, but if it's even a little bit off, we can actually see components there. And this actually tells us some interesting facts about the mass of the planet because there's a famous system that was early on detected as a possible planet in the early days of exoplanets. And it turned out that they had that angle totally wrong. Later, when they had astrometry where they were actually able to look at the positions of the planets, and look at the position, of the stars, they could see it was actually the other way around, and this was actually a brown dwarf, actually even a little bit bigger than that. So the angle matters, but we can get there as long as it's not exactly 90 degrees.
And there's another piece of this where we know the statistics. If these systems are randomly oriented to our field of view, then we will know precisely how many systems we're missing. So I think just because you don't see a planet because it's tipped out of the field of view, we have a way of arithmetically compensating for that. So, in fact, we have this number of planets in our catalog, but again, like Andy L said, if it's not lined up, we don't see a planet, even if there is a planet there. So, statistically, presumably we know this, and we can scale up the number of planets we detect as if we would have seen all planets around all stars. So, do you have a latest planet count for that?
I don't have the exact numbers, Neil, but I'm totally on the same page as you and Andy L. that just because we don't see it today doesn't mean that there couldn't be planets in the system. And that's actually one of the really cool things that the Roman Space Telescope is going to do. Because it's going to be finding planets through microlensing, it doesn't care about the geometry, right? So it can actually look for planets that are farther away than what we do with the transit where it's nearby and we have to see it regularly. And so we expect we're going to see planets in systems where we thought, oh, didn't see that there, but okay, I guess I could have seen that coming.
Just to be clear, what you were saying a second ago, Neil, you can sort of just assume that planet's orbital plane is evenly distributed in all angles. So you can go like, we can see these angles and these angles, so you can then calculate, well, these ones must also exist.
Exactly. You extrapolate into the galaxy. And this is all see any planets at all.
Meat
Once you know
cows.
what fraction of stars have planets that you've detected, and there's all these other planets that don't, then just look at the statistics of the orientation, and you can fill in those missing numbers if it's randomly distributed out there.
While we're talking about that kind of detection and validation of things that are a distance away, Alan G says, hello, great and mystic diviners of the cosmos. How accurate do we believe these remote measurements of determination of atmospheres and life conditions are when we have no way of validating something 50,000 light years away?
Ooh, those are fighting words. No way of validating.
Show your work,
What
NASA.
Go there
dog.
and get a beaker, a sample? Like, no.
Question though,
You just indicted your whole community right there.
But I love this question because this gets at the very heart of what it means to do science, right? Because of course we test the heck out of our equipment so that we know what to expect.
Carrots, potatoes, wheat.
And so we can say that maybe we trust what's coming out of it. But the beautiful thing about science is you can make predictions, right? Like that you know when that solar eclipse is coming, so you can do the Kid in King Arthur's court. And so even though we can't go there and see it up close, you can make predictions about other things you expect to see, like maybe when that planet goes to another part of its orbit, what might you see? And so I think the fact that you can make predictions, you can test, and then you can get more data, that's magic. I mean, imagine that you could predict the stock market. So I think that's great. I'm not worried about not being able to go there and visit, although I would love to do that. I mean, I just have to wait for pieces of the solar system to fall to Earth, and then we can see them.
So I think it was in 1840s, somewhere around there.
Little vending machines
became a tool to understand the chemistry of something from afar. There was a philosopher who, in his thesis, first he asserted there will never be more than 7 known planets. Just asserted that. Okay.
Access the wall.
Quickly thereafter, we discovered more planets. But he also said that the
Oh my
stars,
God,
if they're really in the sky,
patterns.
we'll know their colors and their locations,
different tubs
but we
for
will never know what they're
dying
made of
if I need it.
because they're just too far away.
I haven't even used
That's
this
what
area down
your
here
manual
yet.
sounds like.
All right.
And within a few years, we turned spectroscopes to the stars, and we know exactly what they're made of.
Right.
So I'm not ever going to say we will never know, because I don't know that we'll never know.
If you look at these drawings of the solar system from long ago, right, and, they're still drawing, Saturn is the furthest we know about because, up until the time that America was a country, that was the furthest planet we had known about. But there are some people who draw all of these different orbits and saying there might be other worlds. And you might think it's kind of fantastical, but some people had that imagination, and of course the data bore us out. So I don't know. I get excited about seeing planets, about seeing disks. Like I said, when they fall to Earth, as long as I'm not a dinosaur, I'm cool with that. But meteorites are great. I mean, did you ever hang out with the meteorite at the White House, Neil? The little one that's there?
Where was that?
So in one of the rooms in the White House, there is on loan from the Smithsonian a piece of the Allende meteorite.
I've not seen it.
Okay, I called a friend yesterday to check. They said, oh yeah, the Smithsonian just came and cleaned it, but it's still here at the White House.
Not all of us just hang out in all the rooms of the White House.
That's just
let the record show.
I was just staffed, right? You're a fancy, distinguished guest.
I did spend a little bit of time at the White House. Yes, I know bits and pieces of the White House. I don't know all the time.
No, it's just cool though because people look at this and they go, that's just an ugly rock, right? Because it's like a little black rock with white dots. And I used to go and explain to people, like, no, this is amazing. This is older than the Earth, right? You've got more than 4.5 billion years here. And this is like if you were baking a cake, right? And you were messy and you got flour everywhere. You bake the cake, you eat the cake. Okay, in this case, the cake are the planets. But, you've got like little fossilized flour in this meteorite, and it's here that we can study on Earth and sort of observe at the White House. It's something that meteorite landed here around the time when we were getting ready to analyze lunar rock samples. And in the end, the meteorite ended up being cooler than moon rocks. So I'm just saying,
these are the switches.
I'm here for planets in all their forms. As long as I'm not a dinosaur.
To drop it down.
By the way, we might still be dinosaurs because we don't have a way to deflect an asteroid. And we'll be, if we go extinct from an asteroid,
start spitting it out.
Of intelligent life in the galaxy,
dropping it down
for going extinct, even though we had a space program. See, the dinosaurs didn't have a space program
that we know of.
Where?
We just don't know if the dinosaurs called their Congress people to say, "Hey, make sure you put more funding into that."
Yeah, they had the beginnings of it. It was going well, but then it got into trouble. They got into committees, and then they got bogged down with red tape, and you know how things go. And then
fake news.
And then money got redistributed, and somehow.
And so that drops down to here.
Be a kick-ass question.
All right. Well, I like this question. Hello, Doctors TNT.
Oh.
And it flows
This
down
is Nancy from Hell's Kitchen, NYC. Yeah.
All right.
Yes. Are we up or down or across the road from that? Which direction are we?
They're down from us.
They're down from us. Okay. So Nancy is down from us right now, and Nancy is wondering, have you ever had a simulation give you a result so strange you thought either this is a bug or the universe is trying to tell me something?
So I will first of all say, lots of bugs, no ChatGPT in my coding, so have seen plenty of those. But I actually don't think I've ever had a moment of thinking, oh, that's so weird, but instead, oh, that's so beautiful. Because I always think it's amazing that we can just code the laws of gravity into our simulation And then you can watch stars and gas form into galaxies, and you can look at these pictures, these simulations that are, cosmological in scale, and then compare them to real observations, and they look the same. So I think the universe is telling us, you're doing great, do a little better on that subgrid physics, but big scales, got it going on. And it's just amazing that we can see it on the computer. Because if you go back, have you ever seen those tomb ray simulations from the 70s where they actually use different characters like the letter Q and the number 7 as their particles in these really early computer graphics of galaxies coming together? It's so primitive compared to what we have now, but even then it was right. So I feel like at that point you would have been like, my computer is telling me.
Well, except generally when you have a simulation, when you are simulating, I like Anjali's point about the fact that you get to put laws of physics into code.
Shit.
If you've done that, the code is not going to show you something that is based on some new undiscovered law of physics. You should put the law of physics
until it stops back up.
And so, for me, the most interesting part of a simulation is if I simulate something with my best understanding of all the laws of physics, and it still doesn't match. That means something else is happening in the universe that I have not reckoned in my models. Would you agree that you're more likely to not match the real world because the real world has something more interesting going on in it than your simulation? And now you got to go back to the drawing board of your simulation and figure out what's going on.
I think there's always so much complexity in nature, and we always start from the ground up. And so you always think, oh, there's that more detail I could add. Just like when I draw, I'm not a great artist. I start with a stick figure, and you go, oh, okay, you can add some eyelashes and some more things, but it needs some color. It needs a little bit more. It's just the same way with our simulations. So oftentimes you can think about what's missing here and how do we add that little chef's kiss of color.
Yeah, she mentioned this experiment by Tumray. He's a very famous astronomer of the day. And we saw these galaxies out there that were very disturbed looking. And we didn't know why. There was even a catalog of disturbed galaxies. Okay? They act as a peculiar galaxy. And why do they look peculiar, but we look perfect? We have 2 arms, 5 arms.
Come on.
And are they a different kind of galaxy? And so we had to figure out that these are the products of colliding galaxies. And all the gravity, they distort because they all feel different parts of the gravity at all different times. And Anjali, do you remember how he figured that out? How he did the experiment?
I mean, I have the visual in my mind, right, of the Tomb Ray and Tomb Ray, because it was Haller and his brother, right, who were doing simulations.
Was it he the one, or was it someone before him? Because how do you simulate? You don't really have a computer yet to do it full blown. I don't know. It was someone before him.
I forgot who it was. First figure out the mergers.
Even before Tomb Ray's first computer simulations of it, as Anjali describes, Eric Holmberg, another galaxy guy, he figured out how to do it with light. Because gravity drops off as 1 over the distance squared. Okay? 1 over the distance squared. Now, if you don't have a computer, how are you going to simulate that on a table? How are you going to do that? You can move everything every moment and then calculate everything. That's too much effort. So what he did, he had light bulbs and light meters. Because light drops off as 1 over distance squared. The intensity of light.
That makes sense.
And so the light bulbs were the parts of galaxies, and he took light readings at what the intensity of the light was, and that was proxy for the intensity of the gravity. And you got to see the distortions in the spiral arms of the galaxies. You could recreate all the messy galaxies that look like puppy vomit on the sky.
Oh, Neil, galaxies are beautiful, right? I mean, cute too, so maybe you think anything that comes out of a puppy is cute, but
puppy vomit can be beautifully artistic.
Okay, that's pretty clever, right? You think?
I mean, it's amazing what people do in all sort of senses, right? It's not just looking at it on a screen. We did that actually this past year where we actually had a museum exhibit and we tried to make it multi-sensory for exoplanets. So I worked with a perfumer and a sound engineer, so we had the sounds and smells to get you in that world. We didn't do any experiments with it, but it helped bring people in with different ways, which is pretty cool.
So presumably some of these planets might have hydrogen sulfide.
We did not poison anybody, Neil. No, actually, the most interesting part of working with a perfume artist is when you said, oh, we wanted to get towards habitability and life. She brought me lots of smells of manure because she said there is nothing more lifelike than manure. So we didn't have the puppy vomit smells.
Eventually.
We had some other smells there that were very
Your perfumer brought you manure.
This is going to be a giant castle.
Aren't you glad you don't work at NASA with me smelling?
Yeah,
thanks for clarifying.
No, actually, just the little manure scent that you can just dab on your wrist and behind your ears.
Remind me not to buy that person's perfume.
Yes.
Right.
No, the rest of it though was incredible because what we ended up doing is we had smells like rose garden and horse stables and things like GNT on a Saturday night. It wasn't the TNT drink that we apparently need to come out with. But, you know, things that people would recognize. And then the other wall had these smells of, you know, what does lightning on Saturn smell like? Or interstellar space, or a rock garden on Mars, or a clean spaceship. Getting you imagining that one day in the future, those smells could be just as realistic and familiar to us as the rose garden where you don't have to read the plaque. And so going from there to then being immersed in the sound bath where the distances of these exoplanets were represented by pauses and then music, it just sort of brought it together. And even though some of the smells maybe were not what you would choose for, you know, going out on a Friday night, it was still pretty cool.
Well, thank you, Anjali, for participating in our Cosmic Queries.
It's so good to be back.
When you pass 6,000, give us a call. 6,000 exoplanets.
I honestly suspect it'll pass 6,000 by the time this airs. So.
Oh, okay. And you know what I do at every one of my public talks? I ask everyone to stand who was born since 1995.
Vertical slabs, I love them.
Discovered. And
Which is a lot of people.
A lot of people, yeah, a lot of people. And because they only known life with exoplanets in the catalog, right? Okay. So they're all standing up, and I say, raise your right hand. And they raise their right hand. And I say, I declare all of you to be Generation X exoplanets. And then they sit down.
I love that, yeah.
But again, that just hammers home how absurd you this spiral of science.
That's how you began the whole conversation.
Yeah.
Laura, I told all my friends at JPL, I said hi.
We'll do.
Matt, we'll see you on your website.
Yeah, I'm on tour, and on Probably Science, we will get you back very soon.
Probably that's your podcast.
That is my podcast.
Probably Science. Okay.
We're very happy to steal you.
I've been on it only once. Apparently,
we're making it happen again.
Near my phone the whole time.
Oh, you're a busy man. We need to pick up moments.
All right. This has been another installment of.
So, yep, that's my world.
This would be the exoplanet edition.
Time to get off of
I want
this.
to thank my guests, Anjali Tripathi and Matt
You all
Kirschner.
my other
Until next time, I bid you
normal shit.
to keep looking up.